Nothing feels worse than finally getting to the technical interview after months of cold applications and blowing it all just because you can't remember your data structures and algorithms fundamentals. Now, while the debate about whether LeetCode code style interviews are worthwhile or not continues to rage in full force, my attitude is still just, who cares? Whether or not you're going to be asked to invert a binary tree in a technical interview isn't particularly relevant to the question, should I learn data structures and algorithms? Because even if you aren't going to be asked those questions, the answer is still a yes, at least for me. And to be clear, it's not because you'll need to write heap data structures or quicksort algorithms from scratch day to day as a developer. After all, Claude can do that just fine. It's for two main reasons. So that you can understand the performance implications of all the code you write. Users always want fast applications. And to practice solving hard problems. The problems you solve day to day won't be these exact problems or these exact algorithms, but they will be hard. And learning DSA fundamentals will make you much more prepared to tackle those hard problems when they come. So in this course, we'll cover an introduction to algorithms, math for programmers, big O analysis, sorting algorithms, exponential time, an introduction to data structures, stacks, queues, linked lists, binary trees, red-black trees, hash maps, tries, graphs, depth first and breadth first search, and P versus NP. So yeah, this is a massive course, all for free here on YouTube. We've actually spent years building this course, and only after tens of thousands of students have gone through it over on boot.dev, we've now decided to immortalize it into this video. That said, this is a very hands-on course with exercises and quizzes every step of the way, and my advice is to not binge watch the video. Instead, bookmark it right now and come back to it as you work through the lessons on boot.dev yourself. Speaking of, make sure you create a boot.dev account if you don't already have one, and follow along there with the lesson explanations and example code. All the text and lessons are available on boot.dev for free. There's a link below so you can follow along. By the way, I should mention, I'm actually co-instructing this course with Travis Wagner, longtime friend of the channel. He's going to walk you through the first half of the course, and I'll do the second half. Now, if you really want to learn by doing and get the full interactive version of this course, you can become a BootDev member and use code TRAVI to get 25% off your first payment and support Travis directly. But again, this content is free, and a paid membership simply unlocks all the interactive features of the BootDev platform. Stuff like solution viewing, quests, achievements, the AI mentor boots, certification, progress tracking, all that kind of stuff. And one last note, if you like these massive course walkthroughs here on YouTube, please do subscribe to the channel, like right now. We publish these courses every month or two and can only do so because of your support, so thank you so much. Now, let's learn about algorithms.
Hello, I'm Tech Savvy Travi, and today we're going to be learning algorithms in Python. I'll be walking you through this course and trying to help you get unstuck the best I can, and we'll suffer together. So let's get started. Welcome to algorithms. The word algorithms was designed to scare young CS students into eating their vegetables. After this course, you'll come to see there is nothing to fear. There's a little bit to fear, but it'll be okay. The goals of this course are to learn to think algorithmically, to learn about performance optimization, and to practice solving hard problems. There's no way around it. If you want to be a great developer, you need to solve hard problems. If you want to be a paid developer, you learn React. And a word of warning, don't worry about memorizing this stuff. It's okay to memorize a little bit. I'll be honest. You can memorize a little bit. But in particular, don't worry about memorizing the algorithms themselves. My philosophy, I'm assuming that's Lane, is that it's mostly a waste of time to memorize anything that's a Google search away, unless you want to pass a LeetCode interview. Instead, focus on understanding how the algorithms work in the moment. You should understand what your code is doing and why, but that doesn't mean you need to memorize the code itself. Good luck. All right, so which one of these is not important? Which is not important? Is it understanding how each algorithm works as you learn about it, or is it memorizing all the algorithms in this course? Learning how to write fast programs, or getting practice writing code that solves tricky problems. Okay, all of these things are important except for memorizing all the algorithms in the course. We don't need to memorize every single algorithm in this course. You can do that later when you're cramming for your interview. But that's not the important thing here. All right, we're on to a Write in some code right off the bat. Nice. Find minimum. An algorithm is just a set of instructions that can be carried out to solve a problem. People use algorithms all the time without even realizing it. Yada, yada, blah, blah, blah. I don't want to, I gotta read all this stuff for you. All right. In this course, we'll be building pieces of a pretend product. Socialytics. Clever. It's a tool you need to track your growth as an Instagram influencer. We need to show users the accounts they follow with the lowest follower accounts. So this will help them know who they follow that isn't popular enough to be worth following anymore. All right. So we need to find the minimum. We need to make a find minimum. This is going to be easy peasy. And it tells us exactly how to do it here. So all we do is we're going to set minimum to positive infinity. That's a special value right here. So in Python, we do that by doing inf like this. In other languages, you might have like something like a keyword infinity, but not in Python. So all we're going to do, first things first, and I think if we look at the tip down here, it says, don't forget to account for edge cases in your function. Check the test code if you're not sure what to expect. We'll deal with that in a second, but we'll say min equals, so we need to float positive infinity, which we do like that. And basically that's going to make sure that while we're iterating, we're checking if a number is less. So if we check if a number is less than min, any real number is going to be less than positive infinity, which is what we want. We want that first iteration to always, give us our first number, basically. So for num and nums, we say if num, wrong language, if num is less than the min that we have set, then we're going to set min to that num. Right? And that's it. That's all there is to it. And then we're just going to return the min. Right? But now, if we run this, pass, it says we passed. But I'm sure since it gave us that tip, that if we submit this, we'll get the wrong. Yep, it says try again. And we can see what did we fail here. We can look at what we failed. Have our inputs pass, fail. So the inputs here was an empty list, right? And we were expecting none, but we got infinity, or we got inf, it's positive infinity. So what we can do there, we have our edge case, and all we're going to do is we're going to say if the length of nums equals 0, then we're going to return none. And that's our edge case. So if we have an empty list, it's expecting none. It's important to look at your problem statement or understand your problem very in depth, so you understand the edge cases you might have and that you can handle those. Like in this case, if we have an empty list, we want none. We don't want positive infinity. So now if we submit this after adding our edge case, yep, we're on to the next one.
An algorithm is just a good set of instructions. If you've ever assembled IKEA furniture, baked a cake, or solved a Rubik's Cube, you've used an algorithm. An algorithm must be 3 things. First, defined. There must be a specific sequence of steps that can be taken to perform the task. It must be unambiguous. An implementation of the algorithm cannot be up to interpretation. The implementation is either correct or incorrect with no in between. 3, it must be implementable. This means we need to be able to carry out the algorithm either with hardware or, more commonly, with software. In computer science, we want to write fast algorithms. Here's a Python implementation of an algorithm that finds the longest string in a list. It keeps track of the longest string so far in a variable. It iterates over all of the input strings and compares them to the largest so far. If it finds a longer one, then that string becomes the new longest so far. By the end, we're guaranteed to have found the longest string in the list. But how fast is it? Well, if there are only 5 strings in the input list, it's almost instantaneous. But what happens if we pass in 5 billion strings? These are the kinds of questions we ask when we're studying computer science.
Chapter 2, Lesson 3. What is an algorithm? In the context of computer science, an algorithm is a finite sequence of well-defined computer implementable instructions. Yeah, sure. But an algorithm it's just a set of steps that can be be taken with various inputs, various length inputs, very different inputs, but that's defined, unambiguous, and implementable. It's got implementables kind of given. That needs to be defined a specific sequence of steps that performs a task. So an algorithm must have a blank number of steps. All of these are different ways to say that you can have some sort of unbounded, uncountable, infinite. No, it needs to be a finite number of steps. And next, down here we see algorithms are usually written in pseudocode, pronounced pseudocode, because an algorithm is a higher level description of a solution. An algorithm doesn't care if it's implemented in Python, Go, TypeScript, or Java. Pseudocode is just plain English. So Python is really great here because Python is kind of, is somewhat similar to pseudocode a lot of the times, I think. So it's not a bad language to learn algorithms in. So it gives us some pseudocode for a mystery algorithm. And we start with an original string called S and a new empty string called R. So we loop through S from its last character to its first character. And for each one, we add it to the end of R. So if we have, say we have dog, it would start with G, and we have a blank string, and it would add G to the blank string. So a new string would be G. And then we have the next one is O. And so it would be, now we have GO as our string, R. And then D, it would add D as the last one. So now we have dog and we have GOD. And so what it does is it reverses the string. So what does the mystery pseudocode do? It reverses a string. It doesn't generate a palindrome. It doesn't download a virus. And it doesn't double the length of a string. It reverses a string. And we're on to the next one. Chapter 1, Lesson 5, Simple Algorithms. If you've heard usually exaggerated stories about LeetCode and whiteboarding interviews, you might hear the word algorithm and think it's synonymous with hard problem. It's not really the case, and believing it will only psych you out. Yes, fully agree. We suffer more often in imagination than in reality. Seneca? I'm not doing it. Okay. Algorithms, like anything else, can be understood by breaking them down piece by piece. Take a look at the following algorithm for adding two numbers. It's dead simple. We start with input variables A and B, and we add A and B using the plus operator and assign the result to a new variable called sum. And we return the sum variable. So for this one, we need to calculate the total reach of a group of influencers to estimate how many views a post will get if they share it. So we complete the sum function. It's a slightly modified version of the algorithm above. Instead of just two numbers, A and B, it accepts a list of numbers and returns the sum of all of them. The sum of an empty list should be 0. That's going to be, boom, edge case. Right? If we have, the function's called sum, so I'm not going to name our variable sum. We're just going to name it S. And sometimes in algorithms, you might see some like poorly named, not very descriptively named variables. And that's okay. So we're going to do n in nums. Then we're going to do s plus equals n. And we're going to return n. We're going to return s, sorry. And that's all there is to it. So we're going to loop through, and we start with 0. That's our sum, basically. And then we're going to add n to our sum. We're going to add every number to it. And we run it. And that's all there is to it. However, we have s equals 0 here, but we have an edge case here, and we can make this just slightly better. So we can say if the length of nums is 0, then we're going to return 0. We don't even have to loop through it. It does the same thing here, but just want to make you aware of that edge case. Not really a huge performance issue here, but sometimes if you know what you want and you have that edge case, and even if it might be the same if you loop through, sometimes you can make the algorithm faster by handling that edge case right at the beginning. Alrighty, on to the next one. Now we have some optional challenges here that are called average and median. We're not going to do those in these, but feel free to do those on your own if you would like. Chapter 2, math. Ugh. Right? Math, right? Ugh. No, it's not much math. It's just a little bit of math. Not too much. Just, I know you might have been told there wouldn't be any math, but we were lied to. So chapter 1, lesson 1, exponents. Oh, look at this little. Elaine says, I promise we'll get to how this relates to coding, but first we need to review some math stuff. Yeah, great. An exponent indicates how many times a number is to be multiplied by itself. For example, 5 to the power of 3, or 5 little superscript 3, is 5 times 5 times 5 equals 125. Sometimes exponents are written using the caret symbol, like 5 caret 3 equals 5. It's just easier to write with a regular keyboard, I think is why. So in Python, though, it's the double asterisks. So it's like 2 multiplication symbols. It says, why not the caret operator? Blame Fortran. I'm not clicking. That's a rabbit hole. So square equals 2 to the power of 2, and cube equals 2 to the power of 3. Yeah.
Exponents are super easy. Really, do not let the complicated, confusing name get to you. An exponent is just a mathematical operator that multiplies a number by itself a certain number of times. But before we go deeper into that, let's just review some even more basic math to make sure that we're on the same page. As you know, 2 times 2 is 4. We're saying that we have 2 2s. Similarly, 3 times 3 is 9. Again, we have 3 3s. It's really 3 plus 3 plus 3. This relationship between multiplying and adding is very similar between exponents and multiplication. 2 raised to the power of 3 just means 2 multiplied by itself 3 times. So 2 raised to the power of 3 is 2 times 2 times 2, which is 8. 2 raised to the power of 4 is just 2 times 2 times 2 times 2, which is 16. And 3 raised to the power of 5 is just 3 times 3 times 3 times 3 times 3, which is 243. So the results of exponentiation actually get really big really quickly. 2 to the 6th is twice as big as 2 to the 5th. Okay, now that you get that, let's go over just a couple of special cases. Anything raised to the power of 1 is just itself. So 4 raised to the 1 is 4, and 5 raised to the 1 is 5. This one's pretty obvious. This one's a little weird though. Anything raised to the power of 0 is actually just 1. So 5 raised to the 0, 1. 7 raised to the 0, 1. So how do we do this in code? We obviously can't use superscripts because code is just plain text. We don't have that kind of fancy formatting in our code files. Well, Python is actually one of the few languages that has built-in support for exponentiation in the language itself. And the exponentiation operator is just star star. It's like 2 multiplication symbols. So 2 to the 3rd in Python can be expressed as 2 star star 3, which will evaluate to 8, or 3 star star 3, which evaluates to 27, 3 to the 3rd.
Alrighty, let's get to the assignment. Our assignment says in the social media industry, there's a concept called a spread. How much a post spreads is due to reshares after all of the original author's followers see it. As it turns out, social media posts spread at an exponential rate. We found that the estimated spread of a post can be calculated with this formula. The estimated spread is the average audience followers times the number of followers to the power of 1.2. All right. In the formula above, average audience followers is an average calculated from each number within the audience's followers argument, which is a list containing the individual follower counts of the author's followers. For example, if audience followers equals 23219, then the author has 4 total followers, 1, 2, 3, 4, and each follower has their own 2, 3, 2, and 19 followers respectively. So we need to complete the get estimated spread function by implementing the formula above. The only input is audience's followers, which is a list of the follower counts of the followers the author has. Very straightforward. Very straightforward. Okay. So if the audience's follower list is empty, we return 0. Okay. So first thing we're going to do is we're going to get the number of followers. And that's just going to be the length of the audience's followers. Okay. And then it says if the list is empty, if the audience's follower list is empty, we return 0. So if num followers equals 0, then we return 0, handling our edge case there. And now what we can do is we can get the sum. And we're going to start with 0. We remember how to get the sum from before. So we just go n in audience's followers, and then sum plus equals n, right? And then next thing we can do is we want to get the average. So the average, that's going to equal the sum divided by the number of followers. Now that we have the average, we can go back up to our little thing here. Average audience follower. I guess I could have done that, named it better, but all we're going to do is we're going to return the average times the number of followers to the power of 1.2. The average times the number of followers to the power of 1.2. And that should be our answer. And it is. Look at that. And we are on to the next one. Cruising. I am kind of cruising through this a little bit, just because there's a lot of hard concepts towards the end of this course, and I want to make sure that really give time for that to explain some of those, because it does go pretty complex. All right, 2 to the power of 10 is just 2 times 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 2. You get it. And honestly, I pull out my calculator for this stuff. What are we doing here? But you memorize some of these, especially like powers of 2. For 2's, you kind of multiply the previous number by 2. So if it's like 2, 4, 8, 16, 32, 64, 128, 256, 512, and then 1024. So that 2 to the power of 10 is 1024. And moving on. A 10 to the power of 3. And 10, so 10 is easy. 10s are easy. With 10s, if you have 10 to the power of 1, that's just 10. But then after that, you just add a 0. So if it's 10 to the power of 2, it's 100. So basically, whatever it's to the power of, it's just how many zeros are after. So 10 to the power of 3 is just 3 zeros, which is 1,000. And that's it, and we're good. Chapter 2, Lesson 4. Exponents grow.
Say a company earns $100 in their first year of business, and then in the second year they earn $200, then $400, then $800, then $1,600, doubling every year. This growth pattern is an example of a geometric sequence. Each number in the sequence is calculated by multiplying the previous number by some fixed number, which we usually refer to as R. And in this case, of course, that fixed multiplier is 2. Let's take a look at another example. Let's say that we start with the number 3, first number in our sequence, and that R is 4. Well, the next number is 3 multiplied by 4, which is 12. Then we multiply by 4 again, getting 48. Then multiply by 4 again to get 192, and then again to get 768. Now, of course, there's an actual formula for this math that we're doing. A sub n, which just means the number that we are trying to calculate, the spot in the sequence that we care about, is equal to a sub 1 multiplied by r raised to the n minus 1. A sub 1 just refers to the first item in the sequence. R is that common ratio, the multiplier. And again, n is just the index of the number that we're trying to find in the sequence. For example, let's say we're trying to find the 7th number in a sequence where the starting number is 100 and the common ratio or multiplier, r, is 3. We can just plug that into our formula. A sub 7, the 7th number in the sequence, is equal to 100 times 3 raised to the 7 minus 1, which of course is just 6. And because 3 to the 6th equals 729, 100 times 729 is just 72,900. So that's our 7th number.
very large, very quickly. Let's take a look at an example of them doing that in code. So our assignment here is, while the influencers who use our platform are really great at taking selfies, most aren't super great at math. Yeah. We need to write a tool that predicts an influencer's follower growth over time. So we need to we have a get follower prediction function. So we have fitness influencers, that's follower count quadruples each month. And we have cosmetic influencers, whose follower count triples each month, and then all other influencers double each month. I got a little example here, but basically what we're going to have is our total equals A1 times R to the power of N. So what that's going to be is, for us here, that's going to be the follower count times the factor to the power of the number of months. So all we need to do is get the factor, which we know is going to change based on the influencer type, which you have here. So basically, we're going to say the easiest way to do it would just be to be factor equals 2, and then if the influencer type equals fitness, then we're going to change the factor to be 4, right? We could do else, but you don't really need to do else, because if it's, if the influencer type equals cosmetic, then it's going to be a factor of 3. We could also use a match for this, which I think might be better. I'm going to do that instead. Influencer type, match influencer type. And then we're going to do the case is fitness. And then for that, we're going to say same thing, factor equals 4. And then case is cosmetic. And again, it doesn't really matter so much how you change the factor. You could do it like in the Pythonic, for if influencer type equals fitness, else 3. That doesn't matter so much. Point is, we're changing the factor based on the influencer type, and that factor is going to be 3. And then all we need to do is return. Let's bring this down so we can see. We're going to return the follower count times, this is in parentheses, and we're going to do factor to the power of the number of months. Now we bring this up, we're going to run it. And it looks like we're passing. Let's submit it. And we're good. Nice. So we're on to the next one. Chapter 2, Lesson 5, Nonlinear Growth. Exponents are important to understand when it comes to the execution speed of an algorithm. If the number of operations grows quickly as the amount of input data increases, the algorithm will become slower and slower. Yes. And you got a little chart here showing you if you have 2 times x versus x to the power of 2, you can see which one goes up faster. That's the time it takes. So what does this have to do with code? We generally try to avoid writing code that causes the usage of a resource to grow quadratically or with an exponent. Sometimes that's a lot of computations, or sometimes it's a lot of memory usage. Sometimes it's a large storage requirement. Right. One notable exception is cryptography and security. We want to force attackers to waste resources trying to get at our information. Yeah, that's kind of going the reverse, though, where we're not writing algorithms. The point of that is we make it so that they need to write an algorithm that takes a lot of time, so they can't just guess the key quickly. The result of which operation grows fastest? Is it multiplication? No. Is it exponentiation? Yes. It's not division, because that would be dividing. So that would be. It's not even in the same ballpark. And addition would just be adding. Multiplication would be just multiplying by a given number. And exponentiation would be multiplying by itself instead of just a given number. So the answer is exponentiation. And on to the next one. Chapter 2, Lesson 6. This one asks, how much larger is 2 to the power of 64 than 2 to the power of 32? Now, you might think it's just twice larger, but it's actually 2 to the power of 32 times larger. That's not 2 times larger, because 2 to the power of 32 times 2 to the power of 32 is 2 to the power of 64. So the answer is 2 to the power of 64 is 2 to the power of 32 times larger than 2 to the power of 32. A lot of mouthfuls here, All right. Correct. And moving on. Chapter 2, Lesson 7. Logarithms.
A logarithm is the inverse operation of exponentiation, basically a backwards exponent. So we know that 2 to the third power, 2 times 2 times 2, is 8. And 2 to the fourth power, or 2 with a 4 exponent, is 2 times 2 times 2 times 2, which is 16. A logarithm is when the thing that we are calculating isn't the result of exponentiation, it's the exponent itself. In these examples, the 3 and the 4. For example, log base 2 of 8 is 3. Just like 2 raised to the 3 is 8. Log base 2 of 16 is 4, and log base 2 of 32 is 5. Now, in mathematical notation, log base 2, the base is typically written in subscript, of 16 equals 4. That's how we'd read it in English. And what log base 2 of 16 really means is, what I recommend you kind of think of it in your head as, is what's the power that I need to raise 2 to get the result of 16? And of course, in this case, the answer is 4. Now, the base doesn't have to be 2. In programming, it's really common for the base to be 2 because we work in binary. But we could also take log base 10 of 1000. And what do you think that is? Remember, the question is, what's the power that I need to raise 10 to get a result of 1000? Well, the answer is 3, because 10 to the third is 1000. Let's take a look at a bunch more examples. Log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of 8 is 3. Log base 2 of 16 is 4. Log base 2 of 32 is 5. You get the idea. Log base 10 of 10 is 1. Log base 10 of 100 is 2. Log base 10 of 1000 is 3. And log base 10 of 10,000 is 4. So it's important to understand that exponents grow very quickly. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 20th is 1,048,576. On the other hand, logarithms grow very slowly. Log base 2 of 2 is 1, log base 2 of 4 is 2, log base 2 of 8 is 3, log base 2 of 1,048,576 is just 20. And even more crazy, I'm gonna have to read this one off, log base 2 of 1,099,511,627,776 is 40. Now, because logarithms grow so slowly, they're really useful when it comes to coding and computer science. When we write a program that gets slower in exponential time, that means it's going to get really slow as its input size grows. But if our program only gets slower at a logarithmic rate as its input size grows, it's going to be a really fast program.
A logarithm is an inverse of an exponent. So 2 to the power 4 equals 16, and log 2 of 16, log base 2 of 16 is 4. So the log 216 can be read as log base 2 of 16. So the little subscript number is the base, and then the number that comes after that is where you're doing the log of. So it's log base 2 of 16. So that means the number of times 2 must be multiplied by itself to equal 16. So log base 2 of 16 might also be written as log 2 with 16 in parens. So we got some examples here. And then we have, we're getting into syntax. So there isn't a language level operator to calculate a logarithm, but we can import the math. It's just a function. You import a function from the built-in math library. Our assignment here is we create an influencer score. It'll be a small number, like less than 100, that will give influencers a metric for comparing their social media success against their peers. So we need to complete the get influencer score function. And influencer score is their engagement percentage multiplied by log base 2 of their follower account. That makes it pretty easy. It gives it to us right there. So all we need to do here is it's already imported the math library for us. Okay. All we're doing here is we have the average engagement percentage. So we're going to return the average engagement percentage multiplied by math.log. And now the first number is the of. That's what we're doing. So and then the it's just going to be num followers. Whoops. And then the second parameter, the second argument, is going to be the base. So this would be log base 2 of num followers. All right, and I think that should do it. Yep. All right, well, that took forever, but it was correct. There we go. On to the next one. Chapter 2, Lesson 8. We have a logarithms quiz. Exponents grow very quickly and logarithms grow very slowly. So you would need to have an exponentially growing input size to get a linearly growing time. Generally speaking, it's nice when we can write code that uses log n time to run, where n is the amount of data to process. For example, let's say we have a list of 1 million users and we want to write an algorithm that finds the user with the most followers. I'm not going through all this, but basically a quadratic algorithm, which is exponential, would take 1 trillion milliseconds or 31.7 years, but a logarithmic algorithm would only take 20 milliseconds. It's got a nice little table outlining the differences there between linear, quadratic, and logarithmic, and definitely suggest taking a look at it. But we can say log base 3 of 9 is what? So how many times do we have to multiply 3 by itself to get 9 is what it's asking. And that's just 2. So it's 3 times 3 is 9. And on to the next one. This is asking if log base 5 of 5 is greater than 5 to the power of 5. That is going to be false because log base 5 of 5 is just 1, and 5 to the power of 5 is 5 times 5 times 5 times 5 times 5. So the answer here is false. On to the next one. The result of which operation grows slowest? Is it multiplication, a logarithm, or exponentiation? We know it is a logarithm. Multiplication would be multiplied by a number. Exponentiation would be multiplied by itself. And logarithm is how many times you would need a exponential input for it to grow linearly. So the answer here is logarithm. Now we're on to factorials. We're almost done with the math that you'll need for this course. Just one last thing. Factorials. The factorial of a positive integer n, written n with an exclamation mark, is the product of all positive integers less than and equal to n. So 5 with the exclamation mark equals 5 times 4 times 3 times 2 times 1 equals 120. And it's important to note that it does include the number. The results of a factorial grow even faster than exponentiation. N with the exclamation grows faster than 2 to the power of n. So in this assignment it says influencers need to be able to schedule posts to be published in the future. We found that the order in which the posts are published drastically affects their performance. We need to complete the num possible orders function. It's our function right here. It takes the number of posts an influencer has in their backlog as input and returns the total number of possible orders in which we could publish the post. Factorials are useful when you're trying to count how many ways a collection can be ordered. For example, how many different ways can a deck of cards be arranged? Yeah, so if you're getting permutations of numbers, essentially. For this one, we need to have a product. I'm going to call that P. And P will equal 1. That's the identity for multiplication instead of 0. Otherwise, you would be multiplying by 0 and just keep getting 0. So instead of like sum for product, we start with 1. And then what we want to do is we want to get the range. And that's going to be, since we're starting at 1, we're going to get the range for I in range. And that's going to be start from 1. Again, so we're not multiplying by 0. So I is never 0. And then we're going to do num posts, and then we're going to add 1 plus 1, so that we're doing every item in num posts. Since we're starting at 1, we need to add 1 at the end there. Okay? And then we're going to say P times equals I. And we're going to multiply P by I. And we're just going to return P. And that's our product. And we can run that and see if it worked. And it looks like it did. And we did. And we're on to the next one. How much larger is 564 factorial, the factorial of 564, than the factorial of 563? It's actually going to be 564 times larger. These other answers don't make a whole lot of sense because it's the product of all positive integers less than and equal to that number. So it's 564 times larger, because the last thing you multiply by is the number itself. And so 563 would be all numbers below that, and the last one would be multiplied times 563. And then 564 would be the last thing you multiply by is 564. Next, which grows the fastest as n increases? Is it n squared, the factorial of n itself, or log base 2 of n? And we know that the factorial grows quicker than exponents even. And so the answer is going to be the factorial of n. All right, these are some optional challenges here for exponential decay and logarithmic scales. And you can complete those in your own time if you'd like. We are not going to do those today. That brings us to polynomial time. This starts out chapter 3, lesson 1, starts with big O notation.
Big O analysis is just a way for us as computer scientists and programmers to categorize different algorithms by how they slow down as the input size to the algorithm grows. Like, super roughly speaking, it's a way for us to talk about how slow or how fast algorithms can run. And to be very specific, we're worried about the worst case runtime. So for example, if I pass 100 items into this algorithm and I expect it to take 100 seconds to complete, what's the worst case scenario for when I pass in 10,000 items? How does it get worse as the input size grows? That's what big O analysis is all about. Take a look at this calculate product function. As input, it takes a list of numbers. And for the sake of argument, this is completely made up, but for the sake of this example, let's pretend that these lines take 2 nanoseconds to execute. And assuming that the list of numbers we pass in has just a single item in it, let's assume that these lines of code, the iteration and multiplication, takes just 1 nanosecond to compute. So we pass one item, say the number 5, into this function, it executes, we get a result. Let's just say that the total there takes 3 nanoseconds. Great. Now what happens if there's 5 items? Well, these lines of code, we actually still expect to just take 2 nanoseconds because they don't care about the size of the list that's coming into the function. But if one item took 1 nanosecond, it stands to reason that this iterative loop is now going to loop 5 times and take about 5 times as long. So 5 nanoseconds, leading to a total runtime now of 7 nanoseconds. Great. What happens now if we pass 10,000 items into the function? Well, again, these lines of code will still take about 2 nanoseconds because they don't care about the size. But the loop is gonna take about 10,000 nanoseconds. So we're talking about a total runtime of 10,002 nanoseconds. So all this to say, this function has a big O categorization of order n, linear time, because the amount of time it takes to run the function is linearly proportional to the input size, the size of the list coming into the function. If 1,000 items takes about 1,000 seconds, 1,000,000 items is going to take about 1,000,000 seconds. Let's take a look at another example. This function, just called length, takes a list object as input. And it's important to understand this is an object because we're just going to assume that this object has a property on it called object size, and that property is just stored in memory, and it's incremented and decremented by other pieces of code whenever we append or pop from the list. The point is it's pre-computed, so our little algorithm here that returns it doesn't have to do any additional math. Now with this function, if we pass in a list with one item, we'd expect just making numbers up here. It's gonna take about 1 nanosecond to return that property back. Great, what happens if there's 100 items in the list? Well, we're just using a static property that's been pre-computed in memory. So it's just taking whatever time it takes to return that field from the function. It's probably just like a memory copy. And so it'll still probably take about 1 nanosecond. If we have 10 million items, again, we're just returning a single number. So it's gonna take about 1 nanosecond. So this algorithm, the time it takes to execute actually is constant no matter what the input size of the list is. So this is order 1 or constant time. It's the fastest big O categorization, or at least the big O categorization that doesn't grow at all as the input size grows. Now let's take a look at this get full names function. It takes two lists as input, first names and last names. And we're just going to define n as the length of both lists and kind of just assert that both these lists always have the exact same length. It's going to create a new empty list called full names and then iterate over all the first names. And for each first name, iterate over every last name, creating all the possible combinations and returning those combinations from the function. So again, for the sake of argument, we'll just assume that if there's one first name and one last name, that means there's one iteration of both loops, and it will take about 1 nanosecond to return that single combination of first name, last name. But what happens if there's 2 first names and 2 last names? Well, now we're not talking about 2 iterations, we're talking about 2 iterations of the outer loop and 2 iterations of the inner loop for each iteration of the outer loop. So now it's actually 2 times 2. So we'd expect a total of 4 nanoseconds. And what if we bump n up to 3? 3 first names and 3 last names. Now we're talking about 3 iterations of the outer loop, and for each iteration of the outer loop, 3 nested iterations. So 9 total iterations, 9 total full names, which means about 9 nanoseconds to run this algorithm. So this one actually gets really slow as we start to increase n. With an n of 100, we're talking about 10,000 total iterations, 10,000 total combinations of full names that we're going to be returning. So you get this kind of parabolic growth in the runtime of the algorithm as the lists get larger and larger. Generally speaking, we try to avoid n-squared algorithms in our code where possible. They can do okay on like really small input sizes, but as the inputs get big, they can get hairy very quickly. Now, I'm not going to show you the code for this one, but there's a very famous algorithm called binary search. And basically what it does, in a nutshell, it takes a giant list, let's say 1,000 items, and it's searching for a specific item within the list. And what it can do is at each iteration, chop the list in half. So for a list of 4 items, we'd chop it in half to 2, and then chop it in half to 1. 2 total iterations. A list size of 8, we'd chop it in half to 4, then 2, then 1. 3 total iterations. A list of 16 items, chop it in half to 8, then 4, then 2, then 1. Only 4 iterations to handle 16 items. With a list of 1 million items, it would only take about 20 iterations to cut this thing down to size. Logarithmic algorithms grow incredibly slowly. Technically, they're not as fast as constant time algorithms, order 1, which don't grow at all. With a log n algorithm and an input size of 1 million items, we're talking about 20 iterations. Well, if we bump that up to 10 million, we're just talking about a couple more iterations. It is really like 22 iterations or something like that. I can't do the math off the top of my head. The point is, these input sizes can get absolutely massive, right? 1 trillion items coming into the list. We're talking about like what, 30 iterations maybe? So for practical purposes, you can think about log n as almost as fast as constant time. And the final complexity class we're going to brush on briefly is the exponential class, or order 2 to the n. These algorithms get so slow so quickly that they're basically never practical for real world use. Even just an n of 15, an input size of 15 items, you're talking about computing out to like 30,000 plus iterations. Once n is 30, you can forget about it. These things will take so long to calculate that it's never going to happen. In fact, cybersecurity actually kind of depends on the fact that some of these algorithms are so slow, because that means you won't be able to try all the possible combinations in a reasonable amount of time. So these are the main complexity classes to worry about. Order 1 or constant is the fastest. Order log n, almost as fast as constant time. Order n, or linear time. Order n squared, much slower than linear time. Technically, you also got order n cubed, order n to the 4th that are even slower. And then exponential time, or order 2 to the n, that is impossibly slow. Even with small numbers of n, your algorithm is going to take so long to run that it's never going to be practical.
There are a lot of existing algorithms. Some are fast and some are slow. Some use lots of memory. It can be hard to decide which algorithm is best to solve a particular problem. Big O analysis, pronounced big O, not big zero, that's the big O, is one way to compare the practicality of algorithms. And it is just one way to compare the practicality of algorithms. Not necessarily best always. And sometimes your big O, it might something that's seems faster in big O might be slower just because your input size might not be big enough to matter. So it shows us how we write big O. The constants, linear, squared, exponential, and factorial. Good to remember. And we have a complexity chart here, also very useful. You might have seen this before. Basically shows us that if we have factorial complexity here, that's basically just a straight line up. And then also exponential growth, almost as bad, but not quite as bad. Squared, still pretty bad. And then once you're here, you have n log n, and then linear, which is just n, logarithmic, which is log of n, and then constant O of 1, which is the best possible, but not always achievable. Not usually achievable. So which of these algorithms tends to run the slowest? Is that going to be n squared, n, the log of n, logarithmic, or constant? We can see here, if we go n, we have it right here, log n, it's all the way down here with 1. So we know it's n squared. Chapter 3, lesson 2, we have find max. So ON is very common, that's what it's saying. And that's basically just anytime, O of n is anytime we have to loop over a data set and we need to look at every element one time. And our assignment here, basically the same as the find min, except we're doing find max. Just like we did the first one, we're going to start with, it doesn't say anything about an edge case, so we're not going to worry about it for now. So we're going to say max equals, instead of float infinity and float inf, we're going to do negative float inf because we want the first result to always replace that number, and it'll always be larger than negative infinity. So now we can just go for n in nums, and we say if that number, we'll call this num, if that number is greater than max, then the max is going to equal the num, and then we just return the max. Basically the same thing, except just doing it the other way. Instead of finding the min, we're finding the max. And that's going to be O of n, because we need to look at every number in that list of numbers. And that's it. On to the next one. This is chapter 3, lesson 3, and this is about n squared. It grows in complexity much more rapidly. So if a common reason an algorithm falls into n squared is by using a nested loop, where the number of iterations in each loop is equal to the number of items in the input. So we have the same list here as the input, persons, but we need to loop over it twice. That would make n squared. We're going to write a not very fast algorithm to check if the name exists in this one. So what we need to do is we need to loop through the first names, and the last names. And in this case, we're going to say that the first names and last names increase in size at the same rate. So they're going to be the same size list each. Kind of important. So all we're going to do is we're going to check for first name in first names. And then for last name in last names. And all we're going to do is we're going to concatenate the string. We can do that in a few different ways, a couple different ways at least. But I'm going to use an F string here and interpolate the variables. And do last name. If that equals the full name, then we're just going to return, if that equals the first full name, then we're just going to return true, and we're not going to do any more work. So this is a case, one of those cases where sometimes, it might return very early. It might be the first one, but Big O uses the worst case scenario, and so they could be the very last name in first names, or the very last of last names, and we're using the worst case scenario. That's why it's n squared. So otherwise, we're just going to return false here. And that should do it for this one. Submit. And we did it. Moving on. What are the big O complexities of print names 1 and print names 2 respectively? So let's look at it. We have print names 1 that just got one loop. So that's just going to be O of n. And then we have print names 2, and we can see that in print names 2, we loop twice here, just the same as what we did basically the last lesson, but that's going to make it O of n squared. And that's right, so we're moving on. Which function will finish faster, assuming first names and last names are the same non-zero length? This should be pretty obvious, but if it's not, it's going to be print names 1 because it only has to loop through a single list. The other one would have to do double the amount of work. So the answer here is print names 1. Now we're on to O and M. It's very similar to O of n squared, but instead of a single input that we care about, there are 2. So if you imagine that you need to loop over all of the last names, but that those aren't the same size. So we have 2 inputs that we care about, or 1 input with 2 parts of it that can be different sizes, as is the case in this problem actually. So this says Socialytics needs a new tool that allows big brands to see how many of an influencer's followers are loyal to their brand. And we need to get the average brand followers functions. It takes 2 inputs. It's a all handles, which is a 2-dimensional list, or a list of lists. In that list, it's a list of lists of strings. It represents an Instagram user handles on a per influencer basis. And then it has brand names, a string. If we look at our example input, you can see we have like Cosmo fan, Cosmo girl, and then down here Cosmo Jane, and we're looking for Cosmo. The expected output here is 1.33. There are 4 handles that contain Cosmo, 1, 2, 3, 4, and then there are 3 lists. We get the count of them, and then we divide it by the number of lists that there are. Alrighty, and it says just wants you to observe that we have not just our n, which is the number of influencers, but the average number of followers for each influencer. That's the average length of the lists. So that's our M. We have our N, which is the number of lists, and then we have our M, which is the average length of the lists. For this one, so we're just going to make a counter. We just set a variable for the counter, and we're going to say for handles in all handles. And so now what we're doing here is handles is going to be a list of strings. And so we can say for handle in handles, and all we're going to do is we're going to check in with Python. It's pretty handy. You can just check. And I don't think we're doing any sort of normalization here, so don't have to worry about that. So we're just saying if brand name is in the handle, if it's in that string, then we're going to increase the count plus equals 1. And then now that we have our count, we can say our average is the count divided by the length of the original input list. It's all handles. And then all we do is return that average. Just like that. And we'll run it. And it looks like we're good. Let's make sure. And it is. This is chapter 3, lesson 7.
Big O notation only cares about the theoretical slowdown of an algorithm as its input size grows. It doesn't actually care about how long, like in seconds, this algorithm is going to take to run. So when I say if a linear time algorithm takes 1 nanosecond to run with an input size of 1, then it will take about 10,000 nanoseconds to run for an input size of 10,000. Like that is true, but whether or not it actually takes 1 nanosecond on an input size of 1 or 1 full second on an input size of 1 is actually completely irrelevant to Big O. All we care about is the proportional change from 1 item to 10,000 items. We don't care about how long it actually takes. And when I say we don't care, I mean we don't care as computer scientists doing this theoretical exercise. Of course, as software engineers, we care. No one cares if the Big O of your website's load time is constant. If it actually takes 5 seconds to load, that's a terrible experience. So as software engineers, we do care about constants, but when we're doing Big O analysis, we don't really care. We just kind of brush it aside. We hand wave it away. Say you have a function running in production and it takes 5 seconds to run on an input size of 10,000. Then you benchmark it again on an input size of 10 million, and it still just takes 5 seconds to run. Well, that's actually a constant time algorithm. The runtime isn't being affected by how big the input size is. But whether or not 5 seconds is actually tolerable by your users is up to your users, I suppose. But why this matters is that 5 seconds in big O terms, we just don't care. We don't say, oh, it's order 5 because it took 5 seconds. We just say it's order 1 because it's constant. So that constant can always just be reduced to 1. Let's take a look at another concrete example. Here we've got a function called sum. Takes a list of numbers, iterates over all the numbers, summing the result as it goes, and returns it. This is fairly obviously an order n algorithm. Now this is interesting. Let's say we take another function. This one's called triple sum. It iterates over every item in the input once, summing the items as it go. But this time, it does it again and again. So just looking at this function, you can tell this function takes 3 times as long to run as the first one. Instead of looping over the input once, we're doing it 3 times. So if the first algorithm is order n, wouldn't this one be like order 3n? And the answer is yes, but we don't care. We're doing big O analysis. Constants don't matter. So that 3 just reduces to a 1 and we get order n again.
Saying that constants do not matter. It's basically saying that the crux of this is any constant gets simplified. You can just remove it. So O 2 times n down here, that's really just O n. And O 5 right here, that's just O 1, O of 1. O log 2 times n, that's just O log n, really. So the only one we can't simplify is O2 to the power of n. We can't get rid of 2 because what would it be? It would be what to the power of n? We wouldn't know. So that's the answer there. Now, this is asking how we would reduce O2 times log 2 times n. Get rid of this one, get rid of this one, and we're left with O log n. Pretty straightforward. You just get rid of that entirely, get rid of that one entirely. And we're left with O log n. We have sum and double sum here. And they are both technically the same as far as their time complexity is big O, as far as big O is concerned. So they're both just O of n. We only loop through nums 1 time each. We might do a little extra work here, but we're really just looking at each number 1 time. So they're both O of n. Now this says, ignoring big O theory, which function will realistically take longer to execute? And this is probably a little bit trivial, but it is going to be double sum because it does more work. You can see, you're not just adding it double to the total or adding something to the total, you're doubling it beforehand. So double sum. Now we're on to O of 1. This is constant time. For this, it says no matter the size of the input, there is no growth in the runtime of the algorithm. This is a dictionary lookup, looking up at something by an index. Those are O of 1 constant time lookups. So our assignment here says we need to be able to search our Socialytics user base more quickly. Our users are complaining that the search bar is painfully slow. You'll notice that if you run the code in its current state, it will take a very long time. So the find last name function takes a names dict, which is a dictionary of first name, last name, and first name, which is a string. If first name is a key in the dictionary, find last name returns the associated last name. If the key is not found, it should return none. We're given right here an algorithm that is pretty slow. We don't need to loop through like this. We don't need to do all this checking. So we're going to get rid of that. And what we're going to do, and I'm pretty sure, like, so if you run this, it'll probably say, like, if you try to submit it, though, I'm sure. It fails because it took too long. So we need to make this faster. Actually, so we need to return none. So if we do names, there are a couple of different ways to do a dictionary lookup, but we're going to do names dict dot get. And then we're going to do the first name here. And the dot get will return none if nothing's there. So that's handy. We could also, it's because if we looked up by the first name like this, these two pass, but I'll bet if we run this, we'll get it'll throw an error. Yeah. So if the key isn't found here, then what we would need to do is do like a try catch based or try except. But with this syntax, it'll just return none by itself. So we should be good to go there. And we did it. On to the next one. This is order log n, O log of n. O log of n algorithms are only slightly slower than O1, but much faster than O of n. They do grow according to the input size, n, but only according to the log of the input. That essentially means that you would need exponentially larger inputs to make the algorithm run slower linearly. We're going to use a binary search algorithm. It's a common example of a O log n algorithm. And binary searches work on a pre-sorted list of elements. So it gives you the pseudocode here. So basically, we have an entire array, a sorted array. And what we're going to do is we're going to loop until we get the target, or the search is empty. And we get the median. It's the middle here, median. That's using the floor division of 2. And if the target is less than that, we're going to search the lower half. And if it's larger than that, we're going to search the upper half. And then we return false if we don't find it. So essentially what you're doing is I like to think of it like taking a book, and if you're trying to find something in the book and you flip open a page, you can kind of cut halfway through the book and see like is it there? And you wouldn't just you wouldn't start at page 1 and flip through the entire book. You would start somewhere in the middle, and then you would start breaking that into halves essentially to find what you're looking for faster. And that's what a binary search does. We have a popular Instagrammer using our Socialytics app, and she needs to be able to quickly search for posts from a particular day. This function will be the backbone of the search screen. So we're going to complete the binary search function. So we have a low equals 0. We're going to start with a low, and we have our binary search because we have a target and we have our array. So then our high is going to be the length of the array, actually -1. And then we're just going to create a while loop. And what we're going to do is while low is less than or equal to high, then we're going to create a median, which is going to be the low plus the high. And then that's floor division right here, or integer division, I guess you would call it, to get the median. And then if wrong language. If the array at the index of median is equal to the target, then we get to return true right there. We can just return right out of the loop. Why does it keep telling me bin mode? Am I hitting something, and maybe I'm hitting escape and it wants me to do that? But if the array at the index of median is lower than the target, then we're going to say the low equals median plus 1. And we're going to continue. So we could also do like else here, but we're just going to continue. So otherwise the high equals median -1. So kind of incrementing the low, decrementing the high to get the halves of each, and then search from low to high there. We're going to return false if we don't find anything. And you can look through this. You can look through this pseudocode to kind of understand what we're doing more. We're basically just following that. I want to go over something really quickly here, just so you know exactly what we're doing here. We're checking if it's right on the target, and if it is, we're returning true. If it's less than, we're going to search the lower part. And we search the lower part by setting the low equals median plus 1. And so because this is doing while low is less than or equal to high, that'll prevent us from going, just infinitely looping while we're checking all the ones in the bottom half, essentially. Otherwise, we're going to set high to equals median -1 for the same reason that we don't want to have while low is less than or equal to high. So if we keep decrementing high, eventually the while loop will become false. Okay, let's try that. And we're good. Sorting algorithms. Almost every action you take in a web app relies on sorted data. Just looking up a user's profile in a database likely relies on a sorted index, which we'll talk about in another course. Fortunately, most programming languages provide their own standard sorting implementation. In Python, for example, we can use the sorted function. We can see very, very easily here, 153 sorted 1 through 5. So our assignment for this one is we need to sort influencers by vanity. Complete the vanity and vanity sort functions. And the vanity function accepts an instance of an influencer and returns their vanity score. The vanity score should be the number of links in their bio multiplied by 5, plus their number of selfies. Links in bio are weighted more heavily. The vanity sort function should return a list of influencers ordered by their vanity from least to greatest. You can pass a function as a named parameter called key to sorted to control the metric the sorting algorithm will use for comparisons. So for this one, what we need to do, you see, we don't touch anything above list lines, so very good. What we need to do here is for vanity, all we do is we return the influencer. And we know that it has num bio links, and you know if we had types, it would tell us what's on it, but neither here nor there, right? So we don't. Oh no. Whatever. Dot num bio links, and that's going to be times 5 because it's the number of links in their bio times 5 plus the number of selfies. Num selfies. You can see that both these things are set up here in the class that we're not touching. Then we have vanity sort, and remember this key right down here is we have the sort function by using sorted. Then we have sorted influencers, and then we can set a key to tell it how to sort. And so what we're going to do there is very simple. We just return sorted influencers, and then which is a named key, is going to be vanity, like that. And we can run it and see we passed, and we can submit it and see we passed again. Awesome. So moving on. Now we have bubble sort.
Bubble sort is the sorting algorithm that everyone learns, but no one actually uses in the real world because it's so slow. We learn it because it's easy to understand, and once we appreciate how slow it is, the other sorting algorithms are just that much more impressive. It all starts with an unsorted list of numbers. Then we loop from left to right and compare each pair of neighboring numbers. If the number on the right is smaller than the number on the left, we just swap them. Otherwise, we just leave them be. When we get to the end, we just go back to the start and do it again. We repeat this process over and over and over until we go all the way from left to right without making any swaps. Here's what it looks like on a larger data set.
Bubble sort's very simple, very slow algorithm, and we're learning it for the sake of learning it, I'm sure. What if sorted function exists? Why should we learn to write a sorting algorithm from scratch? Why indeed? And the only reason is to learn how these algorithms work, how sorting algorithms work, and think more algorithmically in general about different ways that you can sort something and different ways you can solve a problem, and the implications and the trade-offs of each one of those approaches. And so what we're doing here is we're going to be learning bubble sort, and there's not a lot of reason to use bubble sort in a practical application, but it will teach you a lot about how these algorithms work and how to think about them, how to think about algorithms more generally. For this one, it tells you the pseudocode, which is we set swapping to true, and we set the end to the length of the input list. And while swapping is true, we set swapping to false. And then for I, from the second element to end, if the I minus 1th element of the input list is greater than the ith element, we swap I minus 1th element and the ith element. And then we set swapping to true. Seems pretty simple. I think we can actually do this without a temporary variable, but we're going to use a temporary variable in this one. Then we just decrement n by 1. We return the sorted list. So we're going to do the standard bubble sort algorithm here. The swapping equals true, and then the end is set to the length of the input list. So that's length of nums. And then while swapping is true, so we just say while swapping, we don't need to say equals true. And then we're going to set swapping to false. We're going to say for I in the range from the second element. So instead of from 0, we're going to start from 1. We go to the end. And then we're going to say if the I minus 1th element, so nums I minus 1 is greater than nums at the index of I, then we're going to, again, I'm just going to do this temp variable, but I don't think we have to, but that's okay. Temp equals nums at index of I minus 1, and then nums I minus 1 equals nums I, so we do swap, we're swapping the variable essentially. And then nums I equals temp, and then swapping equals true. And then we go back here and we say end minus equals 1. So we decrement end by 1. You can see that we're doing that step at the end of the while loop, but inside the while loop. And then all we do is return nums. I mean, I think we could do like this. And just do it like without the temporary variable, but I'm not positive. Put nums. Yep, I was right. But again, you can do it with the temporary variable if you'd like, or you can do it with this like unpacking, like tuple unpacking. Either one works. Alrighty. That is bubble sort. Bubble sort, big O, implementation reference. Cool. Oh, look, they use the temp. Okay. Best and worst case. Sometimes it's useful to know how the algorithm will perform based on what the input data is instead of just how much data there is. In case of bubble sort, the best and worst case scenarios can actually change the time complexity. So the best case is if the data is pre-sorted, bubble sort becomes really fast. Can you see why? Worst case is if the data is in reverse order, bubble sort becomes really slow, but it's still same complexity class as random data. Can you see why? So what is bubble sort's big O complexity? That's going to be O of n squared because we have that nested loop. I'm sure they're going to talk about the best case and why, but just in case they don't, that's because if it's pre-sorted, there are no swaps. You don't have to do any swaps. Swapping won't be set to true. Again, if everything's already sorted, you don't need to sort it. And if it's reverse sorted, then it's going to be that full n squared because we have to run through we have to swap every single time. Next lesson. What are its best and worst case runtimes? So the best is going to be n, where you just have to loop through and check if you need to swap anything, and then you find out no, you don't need to. So so O of n would be the best, and then at worst it's going to be n squared, which is what we use in big O notation. We use the worst case scenario. What is a good reason to use bubble sort? Let's look at this. We got a new little blurb here. It's famous for how easy it is to write and understand. However, it's one of the slowest sorting algorithms, and as a result is almost never used in practice. We cover it because it's a useful thought exercise, so you can appreciate why the more complex and performant algorithms are better. So a good reason is because you're studying algorithms. It doesn't do well memory, it's not fast, and it's not super efficient for space on disk. Nothing to do with that. Just learn it because you're studying algorithms and you want to learn some other algorithms too. That's a good reason.
First, let me explain the pros and cons of merge sort, and then we'll break down the algorithm step by step. Merge sort is much more efficient than bubble sort, which if you're here slogging through an algorithms course, you probably already know a little bit about. In big O terms, merge sort is order n log n, which makes it a lot faster than bubble sort's shameful order n squared. Now, order n log n is about as good as we can do when it comes to sorting unsorted lists. But there are a lot of things that affect performance on a smaller scale that are worth thinking about. For example, merge sort space complexity is less than ideal. It requires copies of the original list to work with, which means it's going to take up more memory than an algorithm that can sort the list in place. It's also slower than some other algorithms like insertion sort when it comes to sorting smaller lists. And that's because of the memory allocation, the copying, and even the overhead of the recursive function calls. All those things have a constant toll on the performance of the algorithm. So they don't really affect the big O, which is order n log n, but they do affect the performance in practice. And that effect is disproportionately bad on smaller lists. Okay, so how does merge sort work? Well, first we start with an unsorted list of numbers. We split the list into two parts, and we keep doing that recursively until each list has at most one item. Next, we start merging each of those lists back together. The process is actually pretty simple. We take two small lists, iterate over each item in both lists at the same time from left to right, and we just compare them, moving the smaller of the two into a newly sorted list. By the time we've moved all the way back up the tree, we'll have a fully sorted single list. It's a recursive divide and conquer algorithm. It uses a pair of recursive calls at each level to split the list into parts, all the way down until we have a single element in each list. Then it merges them all back up the call stack again by looking at each element in both of the lists one at a time. It's an n log n algorithm because it needs to be called recursively log n times. And at each level in the recursive call, all items in the list are compared.
So merge sort is a recursive sorting algorithm, and it's quite a bit faster than bubble sort. It's a divide and conquer algorithm. Oh, that's just going to give you to the Wikipedia page. Sorry for the flashbang. And you can learn more about divide and conquer algorithms there, but you basically divide the large problem into smaller problems and recursively solve those smaller problems. You conquer by combining the results of the smaller problems to solve the large problem. So in merge sort, we divide the array into two equal halves, which is the divide part, recursively sort the two halves, and then merge the two halves to form a sorted array, which is our conquer portion. I'm sure it's going to tell us the algorithm here. The algorithm consists of two separate functions, merge sort and merge. And merge sort divides the input array into two halves, calls itself on each half, and then merges the two sorted halves back together in order. And the merge function merges two already sorted lists back into a single sorted list. At the lowest level of recursion, the two sorted lists will each only have one element. Those single element lists will be merged into a sorted list of links 2, and we can build from there. In other words, all the real sorting happens in the merge function. The merge sort pseudocode for input A, an unsorted list of integers. If the length of A is less than 2, it's already sorted, so return it. Split the input array into two halves down the middle. Call merge sort twice, once on each half. Return the result of calling merge, sorted left side and sorted right side, on the results of the merge sort calls. And it gives us the pseudocode here, which tells us that we create a new final list of integers, so I and j equal 0. Use a loop to iterate over A and B. At the same time, if an element in A is less than or equal to its respective element in B, we add it to the final list and increment I. Otherwise, we add the item to B in B to the final list and increment J. After comparing all the items, there may be some items left over in either A or B. We add those extra items to the final list, and then we return the list. I'm not really going to go over too much of the pseudocode from here on. I feel like it's very easy to read the pseudocode. I'm just going to explain the solution while I do it. If you want to look at the pseudocode, and you should look at the pseudocode to understand the algorithm further. But it's pretty all spelled out there. So for this assignment, our Socialytics users are complaining that when they sort their followers by follower count, it gets really slow if they have more than 1,000 followers, because we're using bubble sort. Let's speed it up for them with merge sort. Got a nice little visual here. And so what we're going to do is we're going to implement merge sort. We can see back here, and merge sort is going to divide the input array into two halves, call itself on each half, and then merges the two sorted halves back together in order. So we can say if the length, wrong language. If the length of nums is less than 2, then we're just going to return nums, because we can get rid of that edge case if it's just one item. We don't need to do that. Then we're gonna get the middle point again, like we did in binary search. We're gonna say that's the length of nums, and that's going to be integer division with 2. And then we can say L, or left, equals merge sort. We're calling it recursively on itself, with the numbers from the middle, from the lower up to the middle, the bottom half, and then numbers from the top half. So we have mid, and this is how we get everything up to the mid. And then we have R equals merge sort, and that's going to be, this is nums, not num. Keep doing this. And then nums, again, the opposite side, mid, onward. And then we just return, and then merges the two sorted halves back together in order. So this is going to return merge LR. And so we have our merge function here. And all we're going to do here, like I said, we're going to create a result, and that's going to be an empty list. And then I equals 0. J is also going to equal 0. And then we say, while we loop over these at the same time, we loop over I and J at the same time, input lists are A and B. And so we have first and second, right? And so we're going to say, while I is less than the length of first, and J is less than the length of second, then we're going to check if the first array or first list at the index of I is less than or equal to the second list at the index of J. If it is, then we're going to append the result, not return, result.append. And we have first at the index of I, that element, and we're going to say I plus equals 1. And we're going to continue. Now, we're going to say otherwise, so we're continuing, but we could say else. It would be the same thing. Otherwise, we're going to append the second item, and we're going to increment J by 1. And then if there's still any in the first or still any in the second, we're going to append those two. So if I still isn't the length is still less than the length of the first list, and J is still less than the length of the second list, we're just going to append those elements to the result. So while I is less than the length of the first, and we're going to append results. Do I have a results or result? Just result. Okay. Result that append first at the index of I. Same thing. No semicolon, wrong language. I is going to be incremented by 1, and then same thing but for J. And while J is less than the length of the second, then same thing, result.append first at the index, second at the index of J, like that, and J plus E is incremented by 1. Now we return the result. 2 passed, 0 failed, right? So we have our base case, and we return the input. A single element or an empty list is already sorted, so we don't need to stop the recursion there. And then we have the divide step, where we slice the numbers at the middle up to the middle point, and then from the middle on into 2 left and right. And then we recall that recursively to make sure each subarray or sublist gets sorted by itself. And then we have the final merge, which combines the 2 halves. What this would be called would be, we have I and J, and we're using this first and second. And that's kind of like a 2-pointer approach. And what we do is it takes the smallest element from either array and makes sure the final result maintains the sorted order there. And then we have these cleanup loops, which just makes sure that if one array has leftover elements, then they're already sorted, and so we just add them to the end. This complexity of merge sort, actually, let's not talk about the complexity of there yet, because I'm sure we're going to get in the complexity of merge sort. But that is the solution here, I am pretty sure, and we can submit that. And yes, we are good. So, yep, first thing we did. I knew it. I knew it'd be coming. Okay, so merge sort is going to be O n times the log of n. So we have divide and conquer, which is going to be a log of n algorithm. And then we have the merge part, which is n. So that's going to be n times the log of n. And correct. So why merge sort? The pros are it's fast. It's much faster than bubble sort. And it's O n log of n instead of O n squared. And merge sort is a stable sort, which means the values with duplicate keys in the original list will be the same order as the sorted list. So if you have a bunch of the same key or same item, if you need to maintain that order, then you need a stable sort. So the cons are its memory usage is most sorting algorithms can be performed using a single copy of the original array. Merge sort requires extra subarrays in memory. So recursive, its merge sort requires many recursive function calls, and in many languages like Python, this can incur a performance penalty. In other languages, it might have tail call optimization, which can kind of reduce that performance penalty significantly. And look, we get they didn't store that in a variable. That's okay. And they use an else instead of continue. I might think about using else instead of continue. I think sometimes continue can make it more difficult to wrap your head around. But that's okay. So when might merge sort be a good idea? If we need a simple sorting algorithm for a small data set that can be written quickly, well, that wasn't really what we just did now, is it? Or if we need a fast sorting algorithm and memory isn't an issue. So we already know that memory can take up a little more memory usage. That's one of the cons over here. So, but it is fast. And that's going to be our answer. Chapter 4, lesson 9. Which function is recursive? That is our merge sort. It's our merge sort here. You can see in merge sort, we call merge sort, and that's the dead giveaway. Chapter 4, lesson 10. Insertion sort.
First, let me talk about when and why you would actually use insertion sort, and then I'll break down the algorithm step by step. Insertion sort is interesting because it's actually really slow in the average case, order n squared. But it has a niche use case where it's actually used in the real world because of how fast it is. And that's when the data is already mostly sorted and when the data set is very small. Some sorting libraries will actually use insertion sort when the dataset is small enough and fall back to a different algorithm on larger sets. So how does it work? Well, it's actually one of the simpler algorithms. We start with an unsorted list of numbers. We'll iterate over each index or each position from left to right, and we're going to keep track of two indexes, I and j. I will be the index of the current number that we are on, and j will start at that same position, but it'll actually move to the left. I'll show you in a second. Now, because it's a look back algorithm, we can actually skip the first index. We'll set I and j equal to position 1 or index 1, which is of course the second position. Now the number doing the swapping will be the number at j and the number at 1 less than j. I actually has nothing to do with the swapping. It's just kind of keeping our place in the algorithm. So we look at the number at position j, at the number at position j minus 1. And if they're out of order, we're going to swap them and decrement j. If they're already in order, then we can just move on and increment I. And whenever we increment I, we also move j back up to where I is. It seems really fast at first because I and j are close to the start of the list, so the amount of backtracking j has to do isn't very much. But you'll notice as I and j get larger and larger, we're gonna have to look back through more and more of the list. Now here's what a sped up version looks like on mostly sorted data. Here's what it would look like on completely random data. And here you can watch it be really slow on reverse sorted data.
Builds a sorted list one item at a time. It's much less efficient on large lists than merge sort because it's O of n squared, but it's actually faster, not in terms of big O, but due to smaller constants than merge sort on small lists. There's a whole explanation video here. Highly recommend going to it. Lane does a wonderful job with those explanation videos. So our influencers want to sort their affiliate deals by revenue, but none of our users have more than a couple hundred affiliate deals. So we don't need an O times log of n algorithm like merge sort. In fact, insertion sort can be faster than merge sort and uses less of our server's memory. So we need to complete the insertion sort function according to the given pseudocode. And you can check the pseudocode there. I highly recommend it. And the tip here says that in some languages, you need to use a temp variable to swap variable values. But in Python, you can do that in a single line. I said that already. I said it. All right. What we're going to do here we have an outer loop structure, and we have an inner loop. And that's going to be a for loop and a while loop on the inside. And so what we're going to do, we're going to iterate through each element, and we need to consider each element. So then we're going to have our inner loop, and that's going to use we're going to have I, and then we're going to set j equal to I. But then we're going to move j based on a certain condition, which is if j is greater than 0, and if the numbers at the index of j minus 1 is greater than the index of j itself. And so this will be much easier to show. And so I'll do that right now. So what we're going to do is we're going to say for I in the range of length nums. We're going to just check every number. We're going to set j equal to I, right? And j is going to be our moving pointer here. And then while j is greater than 0, so we don't want it to go out of bounds, and so we need to check if j is greater than 0. Then we're going to say if j is greater than 0 and the nums index of j minus 1 is greater than the nums index of j. You can kind of see the similarity in how we're swapping, kind of like we did in bubble sort, but a little bit different. And instead of doing the temp variable how we did initially, even though I changed it, we're going to set nums j and then nums j minus 1. That's going to be equal to nums, just the opposite, j minus 1. So we're just doing a swap here, and nums j. And then we decrement j minus equals 1. And that's it. That's our insertion sort. And we return the sorted list. Again, good to note that you have you're sorting in place here, not creating a new one. And so if we come up here and we run this, once again, I cannot stop naming this num. Okay, run, 2 passed, 0 failed. Checking that it's completed in less than 1,000 milliseconds. Great. So if we run that, we should be good to go. And so what we're doing is we're bubbling the current element left until it's in the right spot. And then we only swap when the left element is larger than the right element. And so that'll keep the order of everything on the left side, and keep sorting to the right. That will do it for insertion sort. Chapter 4, lesson 11. All right, insertion sort. That's hard for me to say. Insertion sort, big O. Insertion sort has a big O of O(n) squared because that is its worst case complexity. The outer loop of insertion sort always executes n times, while the inner loop depends on the input. Best case is if the data is pre-sorted, insertion sort becomes really fast. Same thing with bubble sort. In the average case, it's n squared because the inner loop will execute about half of the time. And if the data is in reverse order, it's still O of n squared, and the inner loop will be execute every time. So it's big O complexity. As we know, we go by worst case, but even in the average case here, it's the same. Is going to be O of n squared because the inner loop will execute every time in the worst case. Chapter 4, lesson 12. What is insertion sort's big O complexity on a pre-sorted array? That's going to be O of n, because if it's pre-sorted, all we need to do, just same thing as bubble sort there, all we need to do is check every element to see if we need to do, if we need to sort, and if we don't, we move on. So that means the inner loop won't run. Chapter 4, lesson 13. Let's look over why insertion sort. So if it's fast for very small data sets, even faster than merge sort and quick sort, which we'll cover later. It's adaptive, faster for partially sorted data sets, and it does not change the relative order of elements with equal keys, so it's stable sort. And it's in place, so it requires a constant amount of memory, and it's online. It can sort a list as it receives it. That's kind of a niche but useful feature. So why is insertion sort fast for small lists? Many production sorting implementations use insertion sort for very small inputs under a certain threshold, very small like 10ish, and switch to something like quicksort for larger inputs. They use insertion sort because there's no recursion overhead, has a tiny memory footprint, and it's stable sort as described above. So is it useful in production systems? Is insertion sort useful in production systems? The answer here is going to be yes, but only generally on very small inputs. It wouldn't be good for large inputs, and as we said, there's not a better option, and a lot of production sorting implementations or built-in sorting implementations will have a few different algorithms that they'll switch between depending on the size of the list and any other known factors. Chapter 4, lesson 14, which algorithm uses the least memory and which is generally faster, respectively. So for least memory, that's going to be insertion sort. And as we know, merge sort's one of the cons is it's pretty memory heavy. And generally faster is going to be merge sort. As we know that insertion sort is only fast on small data sets. Now we have our quicksort, chapter 4, lesson 15.
Quicksort is fast and efficient, and unlike some of the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you, bubble sort. Quicksort is a divide and conquer algorithm, just like merge sort. And while it technically has the same big O complexity as merge sort, order n log n, it doesn't require so much memory, and it doesn't have to copy elements from sublist to sublist. It actually sorts the entire list in place, which means that it can be more performant. All right, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. Next, we need 2 pointers, I and j, to keep track of things as we're going to be swapping them around. I will start at index -1, which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. Then j will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning j is not less than the pivot, we don't move I, but we do increment j. Now we do it again. We compare j to the pivot, 3 to 5, and because this time j is less than the pivot, we increment I, then we swap I and j. Now I understand that it's a bit funky. We're comparing j and the pivot, but actually swapping I and j. Just remember that. All right, and now we just do it again. So now we'll compare j to the pivot again, in this case 2 and 5. And again, because j is less than the pivot, we increment I, and then we swap I and j. Next, we compare 9 and 5. Now this time j is greater than the pivot, so no swaps. We move j forward, but we do not move I forward. 1 is less than 5, so we move I up, and we swap I and j. 7 is greater than 5, so no swaps here. 6 is also greater than 5, again, no swaps. 10 is greater than 5, no swapping. 4 is less than 5, one last swap. All of the numbers at or to the left of I are smaller than the pivot, and all of the numbers to the right of I are greater than the pivot. If we swap I plus 1 with the pivot now, then the pivot will be in its perfectly sorted place. Now, that's just one round of the partition function in quicksort, but frankly, it's the interesting part. The way we turn this partition function into a full-blown quicksort is by recursively calling this partition function. So we'll continuously partition, do this algorithm, over and over on each half of the list until the full list is sorted. Now, remember how I mentioned that quicksort is generally more performant than merge sort? That's true, but it does have a dark side. If we consistently pick the smallest or largest element from the list as the pivot, it gets really slow and will actually degenerate into order n squared in big O terms, which effectively makes it a bubble sort equivalent, which is something that no sorting algorithm wants to be. But honestly, that shouldn't scare you. There's pretty trivial ways to make sure that quicksort never degrades. For example, we can just check and make sure that the list isn't pre-sorted We could randomize the list before sorting it, or we could even pick the pivot at random for maximum chaos. Anyways, optimized versions of quicksort are used all over the place in the real world. Most languages' standard libraries actually do use quicksort, at least for part of the standard implementation of their sorting algorithms. Now, so you can properly visualize it end to end, here's a full animation of quicksort on a larger data set. And here's another full animation, but where the list is already sorted and the performance degrades. You'll notice that it's a lot slower.
Quicksort is an efficient sorting algorithm that's widely used in production sorting implementations. Like merge sort, quicksort is a recursive divide and conquer algorithm. A lot of good algorithms are divide and conquer algorithms. Divide. So we select a pivot element that will preferably end up closer to the center of the sorted pack. We move everything into the greater than or less than side of the pivot, and the pivot is now in its final position. Recursively repeat the operation on both sides of the pivot, and we conquer, then we have the array is sorted after all elements have been through the pivot operation. There's a nice explainer video, which I highly recommend going through. And I'll go through the pseudocode because it's not very long here. We select a pivot element, which we'll arbitrarily choose the last element in the list. We move through all the elements in the list, and then we swap them around until all the numbers less than the pivot are on the left, and numbers greater than the pivot are on the right. Then we move the pivot between the two sections where it belongs, and we recursively repeat that for both sections. So our assignment here says we now have two sorting algorithms on our Socialytics backend. It's a bit annoying to maintain both in the code base. Quicksort is fast on large data sets just like merge sort, but is also lighter on memory usage. Let's use quicksort for both follower count and influencer revenue sorting. Then we're going to complete the quicksort and partition functions according to the given algorithms. Note the process is started with quicksort A0 length of A minus 1. So, just it says the first, basically saying this, the first one is, it starts by having the arbitrarily choose the last element in the list. If low is less than high, we partition the input list using partition function, and we've recursively called quicksort on the left side and the right side. And then we set the pivot to the element index at high, and we set I to low. And for each index j from low to high, if the element at index j is less than the pivot, we swap the element at index I with the element at index j. We increment I by 1. We swap the element at index I with the element at index high outside of this for loop, and we return the index I. For our quicksort algorithm, we're going to say if low is less than high, then P is going to equal partition, partition nums, and we have a low and high. And then we run quicksort recursively on both of them, nums with low P minus 1, and we're going to go to quicksort, and we're going to put nums here, and we're going to do P plus 1, and we're going to go to high. We have our low here, and the high becomes our pivot minus 1, our partition, minus 1 point. Then the low becomes P plus 1 to high. And then for our partition function is a little bit more complex, but we set our pivots equal to the nums index of high. And then we set our I to low, the low point. See, we're just doing this pseudocode here. And then for each index j from low to high, so that's for j in range of low to high, then we're going to say if the number at index j is less than the pivot, then we're going to swap the element index I with the element index j, which is we saw how we can do that in line here, but nums I, nums j, and that's going to equal nums j, comma nums I. And then I is going to be incremented by 1. Then we need to swap the element index I with the element at the index high. So nums index I and nums index high equals nums high, comma, nums I, swapping those. And then we return I, right? And then for this one, we just say checking if it's low is less than high. P equals the partition of nums low to high. And then we recursively call it by going with the P minus 1 is the high here and P plus 1 for the low here, which means that eventually we will stop recursing. It's important to have your base case to make sure that you're not infinitely recursing. And we passed. So we submit and we get correct, and we can move on to the next one. I believe that's our last in sorting. Chapter 4, lesson 16. This says that on average, quicksort has a big O of O(n) times log n. And in the worst case, and assuming we don't take any steps to protect ourselves, it can degrade to O of n squared. Partition has a single for loop that ranges from the lowest index to the highest index, and by itself, the partition function is O of n. The overall complexity of quicksort is dependent on how many times partition is called. Worst case, the input is already sorted. An already sorted array results in the pivot being the largest or smallest element in the partition each time, meaning partition is called a total of n times, one for every element in the input. And the best case is the pivot is in the middle, is the middle element of each sublist, which results in log of n calls the partition. Let's check our work here, because now we can look through and see how we did. Okay, so what causes quicksort to break down to O of n squared? Is it an unusually large list, an already sorted list, a small list, or a randomized list? And we can see here, worst case is that input's already sorted. That would make the pivot be the largest or smallest element in the partition each time. I mean, we would have to call it n times. So a already sorted list is going to be our worst case. Chapter 4, lesson 17. What is quicksort's worst case big O complexity? Well, that's going to be O of n squared, because that's the already sorted list. So this is chapter 4, lesson 18. This talks about fixing quicksort. Well, the version of quicksort that we implemented is almost always able to perform at speeds of O of n log n. Its big O is still technically n squared due to the worst case scenario. We can fix this by altering the algorithm slightly. Two of the approaches are to shuffle input randomly before sorting. Can trivially be done in O of n time. I don't know if that's trivially affecting the algorithm, but actively find the median of a sample of data from the partition, which can be done in O of 1. So the random approach is easier to code, which is nice if you're the one writing the code. The function simply shuffles the list into random order before sorting it, which is an O of n operation. And the likelihood of shuffling a large list into sorted order is so low that it's not worth considering. That's a whole different kind of sorting algorithm. Or the median approach. It's the median of 3 approach, which 3 elements, for example, the first, middle, and last elements of each partition are chosen, and the median is found between them. That item is then used as the pivot. This approach has less overhead and doesn't require randomness to be injected into the function, meaning it can remain deterministic and pure. And if you took the functional programming class, you'll know how much we love pure. What does shuffling quicksort's input do? Does it slow down the algorithm, or does it practically ensure a runtime of O n log n? Or does it make the algorithm unsafe for production use, or does it make it really slow? And what it's going to do there is it's going to practically ensure a runtime of O of n log n. Moving on. Why is the median of 3 approach sometimes used? Does it use less space on disk? Does it make it harder to understand? It doesn't require randomness and impurity, or because it's easier to implement? And it is because it doesn't require randomness or impurity. I just want to be pure. Chapter 4, lesson 20. Why use quicksort? Pros. So quicksort's very fast, at least in the average case. It sorts in place, so it saves on memory. Doesn't need to copy and reallocate memory. And the cons are it's typically unstable, which means it changes the relative order of elements with equal keys, or it can change. Recursive can incur a performance penalty in some implementations, and its pivot sensitivity. If the pivot is poorly chosen, it can lead to poor performance. All this said, quicksort is widely used in the real world because the trade-offs are often worth it. It's the default in Postgres, a popular open source database. Who's I? Lane would apparently also like to shout out TimSort, which is a hybrid sorting algorithm that uses a combination of merge and insertion. It's the default sorting algorithm used by sorted function in Python. So if you need a stable sorting algorithm, which would you use? You would use quicksort. No, well, sorting algorithm is stable. None of these. Merge sort. And merge sort, if we remember, is a stable sorting algorithm, which means that the equal elements are not going to be swapped. So the original order of those equal elements are going to be preserved. So chapter 4, lesson 21. Which would you be more likely to use in a large production system? Quick sort or bubble sort? Well, bubble sort is pretty much only used to learn about algorithms. So we're going to say quick sort, as we know that quick sort is used in Postgres as the default implementation. And the rest of these are going to be optional challenges, or just one optional challenge, and you can do that on your own. We are not going to be doing that today. And we are going to be moving on to chapter 5, exponential time. Chapter 5, exponential time, starts with lesson 1, polynomial versus exponential. Broadly speaking, algorithms can be classified into two categories, polynomial time or exponential time. And this has a little diagram here made in Excalibur, it appears, to help you understand that. And technically O of n with the exclamation is factorial time, but let's lump them together for simplicity. I don't know why. Okay, because it's simpler. Okay. An algorithm runs in polynomial time if its runtime does not grow faster than n to the power of k, where k is any constant. For example, n squared, n cubed, blah, 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 and n is the size of the input. To put it simply, polynomial time algorithms can be useful, but exponential time algorithms are almost always too slow to be practical. Unless you're trying to force someone to be slow, like in the case of cryptography and security. Even when n is as low as 20, n to the 2 to the power of n is already over 1,000,000, as we can see here in this handy chart. This asks, polynomial algorithms are blank than exponential algorithms. And that's going to be slower or more complicated, less complicated, or faster. And that's just going to be, it's going to be faster. You can see here O of 1, O of n, O n log n, O n squared, O n 3, 4, blah, blah, blah. But if it's exponential time or factorial, then it's going to be much too slow usually to run practically. Or to solve, I should say. Chapter 5, lesson 2 says that back in the 1970s, some computer scientists researchers wanted to come up with a good descriptive name for the set of polynomial time algorithms. After much deliberation, they settled on the letter P. The hand-wavy takeaway is that problems that fall into class P are practical to solve on computers, and problems that don't fall into P are hard, slow, and impractical. Yes, you have like things that are reasonable that we can solve with our current state of technology and understanding of mathematics, and then other things, which is P. We'll talk about it later. Algorithms in P are blank than algorithms not in P. So are they more practical to solve with computers, less practical to solve with computers, harder to write, or easier to write? That is, they are more practical to solve with computers. That is essentially the definition of P. Chapter 5, lesson 3. We have reduction to P. Let's take an exponential time algorithm and fix it up so it can run in polynomial time. The Fibonacci sequence is a sequence of numbers where each number is the sum of two numbers before it. We want a function that, given an index in the sequence, returns the Fibonacci number at that index. Here's some implementation details to do it in polynomial time. You can look through those implementation details. Basically what we're doing here is we have the recursive solution, which is kind of a standard, for Fibonacci, like kind of naive implementation. And what any recursive solution, we can take that and we can convert it to a loop, and that's going to be faster because we can maintain the state and variables, and we don't have the function call overhead, and it's going to be polynomial time because we're doing constant work for each number in the sequence, and unlike this, we don't have to calculate the same number twice. Our assignment for this one says, our data scientists at Socialytics have found that the growth of the average influencer's follow count is roughly the same growth rate as the Fibonacci sequence. In other words, after 6 weeks of good Instagram posts, the average influencer will have 8 followers. After 7 weeks, 13, and so on. The trouble is our current implementation of the fib function takes so long. It's exponential time to complete that when our influencers navigate to their analytics page, it often never completes loading. So we need to adjust the fib function using the given algorithm to achieve polynomial runtime. And the implementation details here says we have an input n represents the index of the desired Fibonacci value. And we initialize 3 values. One will hold our current value, one will hold our parent, and which will be one before, and one will hold the grandparent, 2 before the current. We're going to hard code the first 2 values at grandparent 0 and parent equals 1. And we're going to write a loop that iterates n minus 1 times. So for example, the loop should not repeat when n equals 2. So inside the loop, we're going to update the current value based on the parents, then update the parents to their appropriate values, being that parent is 1 before and grandparent is 2 before. Then we'll return the current value once the loop completes. We can do that, leave those the same. That's fine. And then if we go current equals 0, parent equals 1, grandparent is going to, it shows us we can reset the hard code these values to 0 again. No, not 9, 0. And then we say for I in range of 0 up to n minus 1, then we're going to set the current to the parent plus the grandparent. That's the one below it, one before it, and the one before the parent. So the parent is 1 before current, and the grandparent is 1 before the parent, 2 before the current. And we know we get the Fibonacci value by adding the previous ones before that, which is why this is usually a good case for something like dynamic programming as well. And so then what we're going to do is set the grandparent to the current, and the parent. No, we're going to set the grandparent to the parent, and we're going to set the parent to the current. And so after that, we're going to return the current. So we get the current value by adding the result of the one before it and 2 before it. Instead of recursing for fib n minus 1 with fib n minus 2, we just keep track of the variables and set. So you get the result by adding the result of the first and second before it. Then we set the values to be the parent, the grandparent becomes the parent, and the parent becomes the current. So the next time through the loop, it'll do the same thing. Basically here is what it's saying is that you convert it to a loop, and we maintain that state of the variables instead of recursing. And so since we are using the result of the previous calculations and storing them, we don't have to calculate any of the numbers twice. Pass, and we submit it, and we're good. So chapter 5, lesson 4 talks about order 2 to the power of n exponential time. O 2 to the power of n is the first big O class that we've dealt with that falls into the scary exponential category of algorithms. Algorithms that grow at an exponential rate become impossible to compute after so few iterations that they are almost worthless in practicality. Sad. And our assignment here says that at Socialytics, we need to be able to compute the power set of a set of influencers. It has something to do with targeting segments of an audience with ads. I don't know. I just work here. A power set consists of all possible combinations of elements in a given collection. For example, the power set of 1, 2, 3 is the empty 1, 2, 3, one that contains 1, 2, a set that contains 1, 3, a set that contains 2, 3, and a set that contains all of them. So every permutation of the possible sets there. So we'll work with Python lists instead of sets for simplicity. An empty set will just be an empty list. Now we're going to complete we can check this off. Nice. So we complete the power set function using the following algorithm. And you can look through this algorithm. I recommend you do. But basically, we're going to have a base case, and we're going to have this recursive strategy to get all of the subsets of the power set. And then we're going to have a final solution. We're going to append all of those subsets to that solution. It says, observe, notice how the power set output gets exponentially larger with each iteration because its complexity class is O of 2 to the power of n. If we could calculate one subset per millisecond, completing the power set of just 25 items would take approximately 9 hours, and that's not accounting for the massive amount of memory we would need. 40 items would take over 34 years. It's not just like a little bit worse efficiency. It's like when we were talking about exponential time, we were talking about crazy bad efficiency. So bad, in fact, that a lot of them to do something reasonable with that algorithm would be beyond the capabilities of computers as we know them. For this one, we have a base case. We're going to implement this, and we're going to say if the length of, nope, wrong language again. If the length of the input set is 0, if it's empty, then we're going to return an empty set with one thing in it, which is just that empty set. Now we can start our algorithm here. We can say our subsets is going to equal an empty set list in this case. And we're say the first one is going to be input set at the index of 0. And then we're going to say the remaining. So we could also call this like head and tail, I would say. And we have first or remaining. and that's going to be input set all of the elements that aren't, except for the first, essentially. We do that with this notation here. And so then we're going to have our remaining subsets. And what that's going to do, so we basically pop the first one off here, right? And what we're going to do is we're going to get our remaining subsets. We call this remaining subsets. And that's going to be recursively calling it power set remaining. We know that won't infinitely loop or infinitely recurse, I should say, because we are taking the first element off and we're only calling power set with the remaining elements. And we know if the length is 0, then we're going to get an empty list, our base case. So now we can loop. We can say for subset in remaining subsets, then we're going to have to think about Python here because in JavaScript, so in JavaScript we would do something like append, push, and then we would do like first, and we would go like comma subset. But I don't. I'm trying to remember how we do it. I think in Python we just take the first here, and we could just do an addition operator for a subset. This will essentially be appending to the subsets a subset that contains the first element and all the rest of the subset. And then what we're going to do is we're going to append that actual subset as well. And then we just return the subsets. And let's see if we did it. We did. Well, it looks like we did. Yeah, we did. Okay. Big O categories review. We have O of 1, O log n, O of n, O n log n, O of n to the power quadratic, square, cubic, or cubed. And then we have 2 to the power of n, which is exponential. And then we have n with that little exclamation, which is factorial. And so we know O1 is fastest, O log n, great. Binary search is an example of that. O of n is linear. It says good, but I'd call it decent. N log n is okay, slightly worse than linear. And then we have quadratic, which is pretty slow. Cubic. And then we have exponential, which we know is terrible. And then we have factorial, which is so slow that it's practically unusable. And so generating all permutations of a list is factorial. So it says, which algorithm tends to be fastest? Is it going to be n squared or quadratic? O of n log n, which is called linear rhythmic. Oh, I did not know that. O n log n, which is linear rhythmic. O of n or O 2 to the power of n. Well, we know it's not O 2 to the power of n. That's exponential. And so O of n is linear. And then linear rhythmic is O n log n. And then quadratic down here. So O of n is actually the highest one up. And since this goes in order of best to worst, we can assume it is O of n. So we need to see what is the complexity of the function there. Get name at index here. It says names I, and as we talked about earlier, indexing directly into a list is going to be constant time or a dictionary. Indexing directly into most things is going to be an O of 1 constant time. Doesn't depend on the size of the input. It can be huge, and it's always going to take the same time very fast to do. Consider the following code. It calculates the number of times a given number can be divided by 2 before becoming less than or equal to 1. What is the big O complexity of the function? So if we look at this, we have O of n squared or quadratic, or we have O of n linear, O of log n logarithmic, or O1 constant. When you see a loop here, so you might think you see one loop, so we immediately could say it's going to be at least O of n maybe. But actually, if we think about how many steps it takes to get this for different input sizes, so if you have an input and we know that 2 is going to take 1 step, we get 2 and it says divided by equals 2, it's going to take 1 step to get from 2 to 1. If we have 4, it's going to take 2 steps. And if we have 8, it would take 3 steps. So we go 8 to 4 to 2 to 1. When you double the input size, you go from 2 to 4, it only adds 1 singular more step. So if n equals 2, it's going to take 1 step. If n equals 4, it takes 2 steps. If n equals 8, which is double 4, that's only going to take 3 steps. So we're doubling the input, but we're only adding a single step. And that's kind of the definition of logarithmic complexity there. It wouldn't be O1 because the steps increase with input size. So the input size does matter. So that immediately gets rid of constant time. And we're not going to have O of n because doubling the input only adds a single step, not the same number of steps. And it's not O of n squared because that grows much slower than quadratic time. So the answer here is going to be, you can think of each division by 2 in the while loop as one step up in binary log, which is O of log of n. This says, consider the following function for 2 questions. And we have our halved section with the rows equals empty list. We have a while loop. We have col equals an empty list. And then for j in range I plus 1, we append j to the column, and then we append the column to the rows, and then we do integer floor division on I by 2. This says, what is an equivalent but not fully reduced way to express the complexity? Ooh, okay. If you see this, it has a specific time complexity of this, and we get a hint, tricky one. Great. What a great hint. This is a tricky one. Need to take into account the shrinking size of each successive list. This kind of gives it away here a little bit. Is O, n divided by 2, n divided by 4. That's going to form a geometric series, which we learned about a little while before. It's clearly not fully reduced. We know it's not n squared, and n times n times n. I know it's not n squared, and these are nonsensical. So we can kind of reduce it down to O of 2m, which is actually just O of n, but said what's an equivalent but not fully reduced way. So that's good. Yeah, that's gonna be, so that forms a geometric series, but it's not fully reduced. What's the most reduced form of the function's complexity? Well, I just spoiled that. So it's not O of n squared, not O n log n, or linear arithmetic, not linear arithmetic, and it's not O of n. It's not. Oh, it is O of n. Sorry, or is it constant time? It's O of n, because O to n is the same as O of n, or linear. As we learned, you can reduce these big O notation by taking out constants, and we can take out the 2, leaving us with O of n. There are a couple more optionals that I recommend you do on your own. We will not be doing them today, and we're going to move on to the last chapter.
I am going to be taking over from here and covering the last half of this course. This is a very, very big course. In this chapter, we're just going to do a little brief introduction to data structures and what they are and what they mean. So data structures and algorithms are very closely intertwined ideas. A data structure is just a thing that we use to organize the data within it, to make it easier to access that data. And data structures use algorithms under the hood to implement the data structure itself, but then the data structure is also used in other algorithms. So it's really kind of hard to draw a line between like, this is an algorithm, this is a data structure. The ideas are they're very similar and very connected. So in this chapter, we're going to be covering stacks, queues, linked lists, binary trees, red-black trees, hash maps, tries, and graphs. But to start, we're just going to implement this count marketers function that uses a list. And a list is actually a data structure, right? It's a built-in data structure to Python, and all the kind of logic that makes the list work has already been implemented in the language itself, but it is a data structure. So anyways, let's implement the count marketers function. So it should accept a list of strings, job titles, and return the number of users who set their title to the string marketer. Okay, cool. To start, I'm just going to really quick, I like to often do this, just print my input and take a look at what it looks like. Okay, cool. So we've just got these arrays of strings, and we're trying to count the number of times that marketer shows up. So let's do that. So we're going to need a count variable, start at 0. And then we're going to iterate over all the strings in the list. So for job title in job titles, if job title is marketer, then we're going to want to increment our count. And then when we're done iterating over everything, we're going to return. Now we do have a problem here. In the instructions, it says locked-in users sometimes use different casing in their titles. So make sure to account for that. So right now we're only matching against the exact marketer string, but we want to make sure that we account for when someone types in like capital marketer. And so we're just going to lowercase the string that we're given and then compare it to the lowercase version. So that should catch all those edge cases. And there we go. So what are data structures? I'm going to go ahead and read to you the definition that Wikipedia gives. So a data structure is a data organization, management, and storage format that enables efficient access and modification. More precisely, a data structure is a collection of data values, the relationships among them, and the functions or operations that can be applied to the data. So, in other words, a data structure stores data, pretty straightforward, organizes the data so that it can be easily accessed and modified, and contains algorithmic functions to expose the ability to read and modify the data. Okay, so just look at two examples. So built into Python, we have lists and we have dictionaries, right? So these match this criteria, right? Stores data, right? Stores different data values, cat, dog, mouse, in this case, strings, right? It organizes the data so that it can be easily accessed, modified. In the case of a list, it's an ordered list that we can iterate over, right? For animal, in animals, like it's really the list data structure that allows us to iterate from index to index. And then each value is stored at a specific index, so we can also access it directly by the number of the index, right? So animals at index 2, right? Square brackets, we get mouse instantly. It's fast. So these algorithmic functions, right? The ability to read and modify the data, indexing into a list is an example of that, or looking up a value by key in a dictionary is an example of that. So it's all about, we're organizing data in specific structures, and those structures live in the memory of our computer. In the hardware side, this is typically RAM, right? Random access memory. So data is being stored in memory so that we can go access it again later in our code or in our algorithm. Okay, so data structures. Store data and allow access to it efficiently. Don't use algorithms, or web scale databases, or are only used by CS professors to scare business majors into dropping the class. That last one might be true some of the time, but the top one is true all the time. So they store and allow access to data efficiently, which is not a data structure. So we know arrays and dictionaries are. An array is like, so in Python, we call them lists. In JavaScript, the same concept is called an array. But if you go to like a language like C, a lower level language, arrays are kind of a lower level concept. They're still, they're still a data structure, but they have a lot fewer features. They're more kind of direct access to your computer's memory. But yeah, array, dictionary, and tuple are all in-memory data structures. Tuple in Python is like a list, but it's immutable. MySQL is not a data structure. It's a fully blown database technology. So it's going to be that one. All right. Now, let's talk a little bit more about lists. So lists have a few different operations that we care about. Again, and data structures, this is what a data structure is. It's a way that we store data in memory, but then also it has operations, right? It has ways to get data out, it has ways to add data in. And those operations are algorithms in and of themselves and have their own big O complexity. So, for example, the append operation on a list. We have, a list of, say, 5 elements. We want to add a 6th element to the end. Is order 1 on average? There are some caveats there, like if you need to grow the list and make it bigger or not, like that. But generally speaking, just adding one item to the end of an existing list can be order 1, can be very, very fast. Indexing, right? So if you have, again, let's just assume a giant list of strings, 10,000 strings, and we want the string at index 753. When we use that square bracket syntax with index 753, that's going to be an order 1 lookup. We can jump straight to that location in memory and grab the item that we need. It's very, very fast. Deleting, interestingly enough, is not as fast, at least not by default. So if we want to remove an element from the middle of a list, e.g. cars.pop2, right? So we're deleting the item at index 2. It's actually order n because we need to shift all of the elements that come after the element that we're deleting. We need to shift them back down. So imagine 10 items in a list. We want to remove item at index 5. Great, everything from 6 and up now needs to shift down. Okay, there are strategies to get around this. Like you could just mark that item as deleted in your code and not actually shift everything down by an index. That would be faster. And so there are little tricks you can play. But generally speaking, if you want to actually remove something from the list, it is going to be slower due to that shifting. And then search, right? This is like iteration. So for car in cars, then we're looking for a specific string, right? Like Ford. This is order n. The values within a list are not necessarily ordered, right? You can add strings to a list in any order that you want. So if you want to then go back and look for a specific value, you have to iterate over the whole list. So we say that lists are ordered in the sense that they have an index that's ordered, right? Item at index 0, then index 1, then index 2, like they're ordered in that sense, but the values stored within them could be appended by the programmer in any order. So to go search for a specific string is an order n lookup. We got to iterate over everything. Okay, so lists start to struggle in two primary areas. One, when you need to frequently delete elements from the middle of a list, or two, when you need to frequently search for specific elements in the entire list. All right. Now that we understand that, let's do another little assignment here. We need to display a user's last job title on their profile. Implement the last work experience function. It takes a list of our players' work history, strings, and returns the last place they worked. We can assume the list is ordered from oldest to most recent, and if the list is empty, return null. So if the list is empty, return null. Let's start there. If work experiences, if the length of work experiences is 0, return none. I am the kind of programmer that likes to take care of my like unhappy paths first and just get them out of my head. Right, so that like now I know when I get to this next line, it's already taken care of. I don't have to worry about the case where the list is empty. I can kind of work on the happy path. Other programmers sometimes do it the other way around. I just find that harder to think about. Okay, so now we just need to return the last thing. So return work experiences, length of work experiences -1. Now this is how you would write it in most programming languages, because this is the only option, right? You need to get the length of the whole list and then just subtract 1 to get the last index. Python actually does have this nice syntax here where we can just say -1, and Python knows that refers to the last item in the list. So go ahead and run that. Very good. Okay, what is the big O complexity of the last work experience function? This is very similar to the one that we wrote. I can see that they flipped the conditional and they use the other syntax, but it is basically the same function. So what's the big O complexity of the last work experience, where n is the length of the work experiences, right? Well, we're not iterating at all here. And looking up the length of a list is order 1, because that's stored on the list. And indexing into a list is order 1. So we're not doing anything here that's not order 1. Why is index lookup so much faster than iteration? So the index is stored in the back of a physical book. Nope. The computer can jump straight to the location of an index. Yes. An index is like an address of an item in a list. Yep, that is true. And the last one is an index just requires scanning the array up to a given index. That's not true. You don't need to scan when you do an index lookup. Full iteration goes all the way to the end of the list. That's also not true. When you start iteration, you can bail early. You can return early out of a loop. You can continue to kind of skip the rest of a loop's body, or you can break out. So yeah, it's not that much. Here we go. It's time to talk about kind of the first custom data structure that's not built into Python. Well, okay, it probably is built into Python, but not at the level that lists are built in. And we're going to implement it from scratch. So a stack is a data structure that stores ordered items, like a list, but its design is even a little bit more restricted. So it only allows items to be added or removed from the top of the stack, right? And it's called a stack. You can think about it like a stack of plates. Right? When you've got a stack of plates, it's really kind of hard to take things out of the bottom or take a plate out of the middle. You kind of can only put new plates on top and take plates off the top, right? So if you have a stack of 5 items, getting to the bottom one, you actually have to take the top 4 off first before you can access that bottom item. And we'll talk a little bit more about the reasoning behind like why you would use a stack later. Just know that like the main reason is because it's fast. It's really fast. Every operation when you're working with a stack is very, very fast. Sometimes you'll hear stacks called last in, first out. And it's because that's exactly how they work, right? The last item that you put in is going to be the first item that you take out the next time you take an item out. I hate those acronyms. I like just using the word stack. It's easier for me than remembering these stupid acronyms. So big fan of the stack word. In this chapter, we'll be building a stack from scratch, and we'll be doing that by implementing a stack class and then exposing all the different functionality like pushing, looking at the size and stuff as different methods on the class. And we'll be doing it on top of a built-in list. So the underlying storage of the stack is going to just be a list. This is very common when you want to build a more sophisticated data structure like a stack or a queue or a binary tree. A lot of times the underlying data structures that are simpler, things like dictionaries and lists. So we're building our stack on top of a list. And for now, we just have 2 methods to work on. So push and size. Complete the push method. It should add an item to the top of the stack. The top of the stack in our implementation is the end of the list. Cool. We could choose to do that however we want because it doesn't really matter to the user of our stack, right? They're just calling push and calling size, but we're going to just internally decide that the end of the list is the top of the stack. So that means we need to append to the list. So self.items append the item that we're given. So when a user pushes onto the stack, we're going to append that item to the end of the list. And then when a user wants to look at the size of the stack, so stack.size, we'll just return the length of self.items, right? So we're really just relying heavily on the list implementation here, using the append and the length functions that are built into Python. The theme of this assignment was, in this chapter, we'll build a stack from scratch because locked in wants undo redo functionality. So this is actually like a really common real world use case for a stack. So for example, this text editor on boot dev probably uses a stack under the hood to keep track of various operations. So for example, operation number 1, delete, that gets pushed onto the stack. Operation number 2, type some words, that gets pushed onto the stack, right? Now, if I undo, I'm going to undo the last thing that was pushed onto the stack, which was type some words. I undo again, I'm undoing the next operation, which in this case was delete that text. So stacks are really good for this undo, redo functionality. Your browser's navigation history very likely implemented as a stack because it allows you to do this kind of backwards and forwards traversal while keeping everything very, very fast. New computer science students really overthink stacks. They're just about the easiest data structure to learn though, so honestly don't stress about it. Imagine you're at a salad bar, but before you load up on bacon bits and croutons, you need a plate. Now, it's a self-serve situation, and you notice a giant stack of plates sitting on the counter. Do you grab one from the bottom? The middle? No, because you're not a complete idiot. You grab one off the top of the stack. Okay, but here's the thing. You're with your romantic partner, who you're out to dinner with, and they explain they have to leave, and you decide you just don't even want salad anymore. So do you lift the giant stack of plates and shove your plate back at the bottom? Stuff it into the middle? Again, no, you're actually a sane human being, so you just set the plate back on top of the stack. And that's it. That's how stack data structures work. You put items onto the top of the stack, one at a time, and then you remove them off the top again, one at a time. Once something has been pushed down to the very bottom of the stack, you actually have to take everything else off the top before you can get down to it. Stacks are last in, first out. LIFO. That makes them restrictive, but useful in specific situations where you're okay with that limitation. For example, undo or redo in a word processor, or the back button in your browser history. Those are real world examples that actually use stacks under the hood. And the real benefit of stacks is that they're super fast. Pushing and popping items onto a stack are both order 1 operations. All right, stack speed. Here's the really cool thing about stacks. So they only support a few different operations, right? Push, which we just implemented, pop, which we haven't done yet, but that's the one that removes the item from the top of the stack and returns it. Peek, which just returns the top item without actually removing it from the stack, and then size. So all 4 of these operations, this is the cool part, are all order 1. So even if you have 10 million items in your stack, the stack's operations are still really, really fast. So which operation is order 1? Size, push, pop, peek, it's all of them. Where can items be added to and removed from a stack? Top, middle, bottom, any old place? It's gonna be the top. All right, pop and peek. So we've already done push and size. Those ones were really straightforward. Now we've got peek and pop. Complete the peek method. It should return the top item from the stack without modifying the stack. If the stack is empty, return none. So I like doing my edge cases first. So if length of self.items is 0, then just return none. Okay. Otherwise, we're going to return self.items. We've been over this, right? At -1. There's returning the last element in the list, which we've defined as the top of our stack. Cool. And we're going to have some failed tests here because we haven't yet done the pop, but where's our peek being done? No, it might just be easier to implement peek or just implement pop rather, and then see if we pass all the tests. So complete the pop method. It should remove and return the top item from the stack. If the stack is empty, return none. So we can do the same thing here, and then we need to actually capture the last item, right? So let's go ahead and just save that in a value that I'll just call val. So now we're going to save it. And now we need to actually modify the list and remove the last item, right? So this just copied the last item into the val. So if I just did this and then return val, right? All we've done is returned a copy of the last thing in the list. We want to actually remove it. My guess is this tip will be useful. So the del keyword in Python can be used to remove an item from a list by index, right? So after we copy that last value, we can probably do delete self.items. The del keyword can be used to remove an item from a list by index. I think the syntax is this: del self.items at -1 and then return val. Let's run that. And yep, looks like we're passing. So we push Charlie Tech Corp, we push, and then we pop. Very good. That should be good. Okay, let's go ahead and submit. What can be stored in the stack? Your mom's phone number, objects, integers, in fact, anything, including your mom's phone number. All right, if you want to get an item at the bottom of a stack, what is the big O to retrieve that item? So remember, this is not a supported operation of a stack. Like you're not allowed to just go straight to the bottom of a stack and grab something out. So the only way to get at that item, if you're restricted to using a stack, is to actually pop everything off the top, right? So what's the big O to retrieve that item? Order n squared because plates are heavy and lane is weak. Order n because all the other items need to be popped first. Order log n because stacks can be searched using a binary tree. No. Order 1 because the pop operation is order 1. So the pop operation is order 1, but that's only if you're trying to get the thing off the top. So you actually have to call pop n times if you want to get something at the bottom of the stack. It's actually order n. And then it's worth noting here some of these use cases that I just want to show. So stacks are often used in the real world for function call management. So later when you take our C course and we talk about the call stack, that's a stack, right? So very useful for kind of modeling function calls within programs. Again, undo, redo functionality, browser history, and the evaluation of expressions like mathematical or programming expressions not can be done with a stack. All right, using a stack. LockedIn supports a basic scripting language. It allows technically savvy HR managers to write scripts that can automate repetitive tasks on the platform. The language makes use of parentheses to group operations together. We need to be able to check if the parentheses in a script are balanced. So here's some examples of balanced parentheses. It's one of those things that like makes a lot of sense when you just look at examples, right? Like you've got open and close parentheses, open, close, like these are all balanced. Unbalanced would be like you're missing a closing parentheses, right? It's the kind of thing that your editor would yell at you for, like your coding editor. Okay, complete the isBalanced function. It takes a string as input and returns true if the parentheses in the string are balanced and false otherwise. Okay. Use an instance of the provided stack class in stack.py to keep track of the parentheses. Cool. So we've got access to our stack that we built here, and now we can use it to implement this function, this algorithm. Very cool. So the very first thing we're going to do is initiate or instantiate a new instance of our stack class. So s equals stack. And I'm pretty sure our stack takes no arguments in the constructor. We've just got an empty stack that we can push onto. So next, what I'm going to do is iterate over every character in the input string, which in Python is really easy. We can just do for. I'm just going to call each character C for C in input string. We're going to push the character onto the stack. S.push C. Okay. Takes a string as input and returns true if the parentheses in the string are balanced and false otherwise. Use an instance of the provided stack class in stack.py. Great. You only need to consider the characters left paren and right paren for this challenge. Great. So we can assume that this input string, like we can ignore everything that's not left or right parentheses. Great. Let's think about how this could work for a second. If every time we encounter an opening parentheses, we push it onto the stack, and then every time we encounter a closing parentheses, we pop off the stack, by the end, we should end up with an empty stack if the parentheses are balanced. So like, let's take the simple example. We push the left paren, we pop the right paren, the stack is empty. Push, pop, stack is empty, right? So in all these cases, push, now we're at 2, pop, we're at 1, push, pop, right? So our algorithm can be push left parens, pop right parens. At the end, if the stack is empty, it's balanced. If it's not, it's unbalanced. And that's all we care about, right? We're just returning a Boolean is balanced. Okay. So we shouldn't just push everything onto the stack. We should do something like if C is open parens s.push, and it actually doesn't really matter what we push. In fact, just to be cheeky, I'm just going to push the none value. Else if C equals close paren, then we'll just do an s.pop, which does return something, but we don't actually care. We don't care about it. We don't need an else because we just do nothing else. If it's a different character, who cares? And then at the end, we want value to equal s.peak. And if the stack is empty, peak will return none, right? So we can just return val is none, because if it's none, the stack is empty and therefore it's balanced, right? Let's go ahead and run that. Oops. Else if C equals, oh, I forgot a colon. Still missing something. Else if C equals this. Oh, I'm writing Python. Excuse me, I'm writing Python. There we go. Ooh, one failed. What do we fail? Input. That. Expecting false. Actual true. Oh, interesting. Okay. For some reason, we're always returning true. Val is none. Let's do this. Push. C. Pop. C. It happens when I do this. Okay. So here we pushed popped actual true. Very good. Pushed this. That's all that happened. We never popped. Reasonable. And then we returned true. Is our peak broken? How does peak work? Peak. If the length of self.items is 0, return none. Ha ha! Oh, this is so good. I wrote the correct algorithm, but because my stupid head decided to push none, thinking it doesn't matter what the value is. It does matter what the value is in the sense that it can't be none, because I'm checking to see if the value is none. I can push literally anything else, and this works. Oh, except maybe not. What did I screw up? Pass. What did I fail? Expecting false, actual true. Okay, we have an edge case here that I didn't think of. Closing paren. We have an extra closing paren. So if we try to pop off an empty stack, that means it's unbalanced. So we need to do something like this. Val, or I should say popped, equals s.pop. If popped is not none. No, if popped is none. Yeah, if popped is none. So if we try to pop off an empty stack, then the parentheses are unbalanced in the other direction. We have too many closing parentheses. So if popped is none, we just return this, right? There we go.
Queues are one of those data structures that you probably already understand, even if you don't know it yet. Have you ever stood in line for 2 hours just to be told that Mickey had to leave and couldn't meet your daughter at Disneyland? Well, if you have, you were in a queue. You might already know about stacks, which are last in, first out, and queues are very similar, but they're first in, first out. Queues tend to be used way more often in the real world than stacks because they perfectly model so many real world systems. Amazon packages on a conveyor belt that my wife ordered for herself when I forgot our anniversary, that's a queue. People waiting for the new iPhone that has the exact same features as the last one, also a queue. The 69 bugs in your dev team's ordered backlog, believe it or not, queue. Whenever items are processed in the order they are received, that's a queue. Now, queues have 3 main operations. Enqueue, which adds an item to the back of the queue. Dequeue, which removes an item from the front of the queue, and peak, which reveals the item at the front of the queue without removing it. Now, that kind of sounds just like a Python list, right? And to be fair, it kind of is. But we actually are restricting ourselves to just these 3 operations. No iterating or searching allowed, which we could do with a Python list. But it's this same restriction that's what makes queues fast. Just like a stack, they can have order 1 time complexity both for enqueue and dequeue operations, assuming the implementation's good. That means queues stay fast, no matter how many items are stored in them. A queue stores ordered items, kind of like a list, kind of like a stack. Really, the only difference between a queue and a stack is in how the items move through the list. So instead of things coming into the queue and out of the queue in the same location, right, on the same end of the queue, things go in one side and come out the other side.
you can really, this is really a simple concept. Like I know queue kind of, especially if you're American, can feel like a really confusing word. It's literally just like waiting in line for coffee, right? You enter the line at the back. When you order at the front, you come out of the line. It really is just that simple. So what is an example of a real world queue? We've got the set of possibilities in a game of dice. No, that doesn't have any inherent ordering, entering, leaving, nothing like that. The absurdly long line of millennials without children waiting to get into Disneyland. Not only is this an example of a queue, it is very real. I was at Disneyland last year. Lane's collection of totally cool and totally not lame Lord of the Ring action figures. Very cool, but definitely not a queue. And then a stack of plates in the cafeteria. No, that would be a stack. So it's going to be this one. Okay. Queue class. So Locked In uses a queue to keep track of the order that recruiters should use to reach out to job seekers. Okay, so we've got a queue of job seekers, it sounds like. Implement the following operations on the queue class. Queue.push adds an item to the tail of the queue. So the tail of the queue is where things are entering, and the head of the queue is where things are going to exit, right? So pop removes and returns the item from the head right here. That would be like someone, finishing their order, if we're assuming that the queue class is like waiting in line to get a coffee. Pushing into the tail would be entering line, and then you're sitting here waiting. You finally make your order and exit through the head of the queue. Queue.peak returns an item from the head of the queue. So it just returns the whatever's at the head, but it doesn't take it out. And then queue.size just returns how many things are currently in the queue. And then just a little note here on vernacular. So push and pop are the words that I like to use because they're easy to say. You'll also often hear NQ and DQ though. So NQ just means push or enter the queue, and then DQ is like pop or remove from the queue. Okay, so our job here is to implement the following operations. All right, so like before, we're using an array or a list as kind of the backing data structure for the queue class. Let's start with push. So if the tail, does it tell us? Adds an item to the tail, index 0. Okay, cool. So the tail of our list will be index 0. The head of our list will be, n-1. To push something, we need to add it to the tail of the queue, which is index 0 of the list. Now in Python, I think there's a specific, probably even tells us, the .insert list method may be helpful. Let's take a look at .insert and see what it does. Insert an item at the given position. Okay, so we can actually insert directly into index 0, it looks like. So that's what I'm gonna wanna do. So self.items.insert. What are the various arguments? Insert 0 inserts the front. So yeah, insert 0x. All right. So we want to insert at index 0. Perfect. And then we want to insert the item. And then for our push method, I don't think we have to return anything. Yeah, self.items.insert 0 item. Cool. So it's important to understand that this is actually going to shift everything from index. It's going to shift everything that's currently in the list down 1 index. Next, pop removes and returns an item from the head of the queue, which is the last index. All right. So let's get that value first. So value equals, or to be consistent, we can call it item, equals self.items at -1. Let's handle the edge case here. If self.items, if length of self.items is 0, we'll just return none. Otherwise, we'll grab that item, then we will remove it from the end of the list. There's probably a nice Pythonic way to do this, is there? No, I think we just need to slice it. Probably just need to slice it. We could also delete. Actually, I think delete's probably the easiest way. So I think it's delete self.items at index -1. Oops, self. And then we just need to return the item. Peak's gonna be similar to pop, it's just without the removal, right? So we'll just do this stuff, and then we'll just return this. And then size, just return the length, self.items. Okay, that's feeling pretty good. Let's go ahead and run it. 2 passed, awesome. And we're good. Okay, queue speed. So how fast are queue operations? Well, in an optimized queue, in a queue that actually is kind of built properly, every operation can be order 1, just like a stack. Push, pop, peak, size. They can all be order 1. So again, as long as you're okay with the restriction of only putting things in one end and only taking them out of the other end, right? FIFO, first in, first out, then you can have this really, really fast data structure. But we have a problem with our queue. And the problem is our push method. So with our push method, like I mentioned when we were coding it, that dot insert at index 0, it's going to put the new item in at index 0. But because we're using an array, a backing array in memory, it's going to have to shift all the other items down by a little bit in memory, right? So that we can make room for the new thing at index 0. So it's going to take like the last element of the list, move it to a new index, right? So like item at index 5, let's just say that's the last item in the index, now goes to index 6. Item index 4 goes to 5, 3 goes to 4, 2 goes to 3, 1 goes to 2, 0 goes to 1, and now we have space at index 0. We can put the new thing in. So that's not an order 1 operation, right? That's order n. And so this is a problem if we're trying to build a fast queue, which is why using an array as the backing data structure makes it a little more challenging to build a fast queue. Whereas with stack, it was really easy. We didn't have to worry about this. So anyways, we'll actually solve this problem here in a bit. But for now, let's do the quiz. So what is the big O complexity of the push, pop, peek, and size operations of an optimized queue? They can all be order 1. And then if an item could be anywhere in a queue, what's the big O complexity to retrieve that item? So if an item could be anywhere in a queue, what's the big O complexity to retrieve that item, right? So we're trying to get an item that we know an item is in the queue. So we have a list of strings and we're trying to find a specific string. We know it's in the queue. Problem is we're not allowed to like iterate over a queue. We're not allowed to index directly into a queue. I should rephrase that. We are allowed to iterate in the sense that we're allowed to pop everything out of the queue, but we're not allowed to like index directly into the middle of the queue. So it's order n because we might have to pop everything out of the queue in order to get the one thing that we're looking for. All right, why is our list-based queues operation order n? Because you have to search for the perfect spot to insert the new element? No, it's always inserted at the beginning or at the end, however you want to look at it. It can be really confusing, by the way, when you're working with queues to remember like, wait, what side am I putting things into and what side am I taking things off of? To the user of the queue, it should be really easy. It's just push, pop. Like they don't have to worry about the end of the backing array. But when you're implementing the queue, you have to think about these things. Because you have to remove everything from the queue before you can add new elements, that's not true. And because you have to move all the elements over by one index to make room. Yep, that's the one. Okay, remember how we just talked about how our push method with the array or regular list-backed queue was order n? Well, it was. And the problem, again, is that we have to shift everything when we insert something to the beginning of a list, which is why, generally speaking, when you're working with lists, you don't want to be inserting things at the beginning of the list because it can be a really slow operation. So how do we fix that, right? And the answer is we fix that by building a new data structure called a linked list, and then using the linked list as the backing data structure for the queue, right? So our queue is going to be built on top of a linked list now, which we have to build from scratch. I mean, that's not entirely true. I'm sure there's like some standard implementation of a linked list, but we're going to build it from scratch because that's what this course is about. Let's talk about what a linked list is. So a linked list, if you squint really hard, kind of is just a regular list in the sense that it's an ordered collection of items. The difference is how you model the order specifically in memory. So instead of, with a regular list, the way it works is you've got the list itself. Let's say it's called fruits, right? That list points to some address in memory, like in hardware on your computer where that list lives. And whenever you add new things to the list, you're just adding new data in that spot in memory. So the start of the list, let's say, is at address like 100. The next thing that we add to the list, and I understand that I'm like really oversimplifying from like a hardware and a memory perspective, but like the next thing we add to that list, we're just going to put at spot 101, right? And then the next thing's going to go at spot 102. The next thing's going to go at spot 103. So we're just like laying them out consecutively or contiguously in memory. That's how a regular list works. And that's why we're able to use like numbered indexes. So I say, okay, I want fruits at index 5. Great. Go to the location in memory where the fruits array is, and then just like go over to spot number 5, right? Offset number 5. That's how they work. Linked lists are entirely different when it comes to how this works in memory. Every object in the list can be in totally different places in memory, and they just link to each other through a linking variable, or because we're using classes, we'll have a data member on our class that points one node to the next node. Okay, so take a look at this diagram here. The first node of the list has a value, in this case 69. So this would be like creating a new array or a new list in Python with square brackets and just putting 69 as the only entry in there. That's what this first node is, just one item. But now, again, instead of using a list, what we're going to do is we're going to model this as a class. So, think of a class node where its value property, so .val, is 69. And it has another property in the class called .ref. Right? And ref is actually just another node. So it's this other node here where its .val is the next value, so 42. And then that node has a .ref that, is a reference to or points to, however you want to say it, to the next node. So every node just kind of points to the next one in the list. And well, we'll talk about why this is advantageous in some instances in just a second. But that's how it works. And you'll see that when we code this out. Okay, so like I said, our nodes will be represented by a simple class with two fields, val and next, right? Val has the actual value, next is just a reference to the next node. Cool. Assignment, let's lock in and make locked in faster. So complete the nodes constructor. Set its val fields the provided value and its next field to none. Okay, so this is just setting up those two properties that we care about. So self.val equals val and self.next. So we're actually using next instead of ref here, but it doesn't matter. You could name this whatever you want. And we're starting it with none. So when someone creates a new node, they're giving us a value that they want to store, and that's it. And then we're just initializing this self.next variable to start. It's just going to be none because the assumption is this is the only node in the list. Now, what happens if they want to add another value? Right? So, and I'll just kind of write this right here. So if someone wants to create a new node, they're going to be doing something like this. Fruits equals node banana, right? So now we've got a new instance of node where banana is set to the value and the next is none. Now, if they want to add something in regular list syntax, this would be .append. What they're going to do is fruits .set next, and complete this node set next method. It should set the next field to the provided node, right? So it takes as input a node. So then we say, okay, I'm going to make another node and we're going to call this one grape. Okay, so this is the syntax that the user of our class will use to create the linked list. Okay, so set next needs to be self.next equals node. Cool. Go ahead and run that. And it looks like we did it correctly. So let's just take a look at this diagram again. So here we've got the linked list and the list side by side. Remember, the regular list is stored consecutively in memory. So the start of the list, again, let's just say exists at, this time let's say it exists at memory address 10,063. Well, that's where the first item lives. The next item would live at 10,064, right? And then 10,065, and then 10,066. Again, I'm being a little bit hand-wavy about how exactly the bytes would line up, but that's the basic idea. Each thing lives consecutively in memory. Linked list, totally different. The very first node lives somewhere in memory, let's say address 50, and it has two values stored there. The first one is the actual value we care about, 69, but then the next one is a reference to some other location in memory, which represents this node. So it might be, memory address 1,632. Doesn't matter, right? Where this next value lives and its reference. And so we have this value reference combo that keeps going, keeps linking nodes until you get to the end of the linked list. And the way you know that you're at the end of the linked list is because the ref field, or I believe in our class we called it next, is just going to be none. It's not going to point to anything. That's how you know you've reached the end of the list. Okay. So again, this is the syntax for using a normal list. Using a linked list, because we're building our own classes, is a little different. We're going to have to iterate using some kind of loop that continuously goes through the chain looking for that last node that has its next property set to none.
right? So we're just going to kind of keep following this chain until we get to one that has its ref or its next value set to none. So it's a little bit different there. Now, I do want to point out here, frankly, linked lists can be really annoying to use and incur much more overhead. So like, this is just the time where I point out, look, most of the time in your day-to-day programming, like 99% of the time, you're going to want to use a regular list or a regular array or a regular slice or whatever. And it will actually end up being more performant. It'll be faster. It'll be easier. So most of the time you're going to want to use a regular list. There's a couple reasons we're even covering linked lists. The first is because it's a good, again, like I said at the beginning of this course, it's a good thought experiment. It's good problem solving practice. But there are a few niche cases where it is super useful. And that one niche use case is the one that we talked about in our Q class, which is when we insert things into a linked list, we never have to do any memory shifting, right? So adding a node into the middle of a regular list means we have to add it here in the middle and then shift everything else over to the right, which is an order n operation, right? Especially if you're adding it into the beginning of the list, because now I have to shift the whole list. That's what was making our queue slow. The nice thing about a linked list is we don't have to shift anything at all. We can put the new node right here in the middle, and all we have to do is update 2 references. We just have to set the node that's before it. We have to set its ref property or next property to the new node. And then we have to set the ref of the node that we're inserting to the one that comes after it. So we just update 2 references and then we're done, right? And that's a much faster operation when you have like a really big list and you're trying to put something at the beginning. Now, I have swept under the rug like all the software engineering optimizations that go into this. We're talking really about the like theoretical computer science here. For small numbers of n, it's still going to be faster to use an array or a regular list like most of the time. When you pull out the linked list in real life, you'll probably want to be benchmarking, right? And running tests to see if it actually is giving you the performance gains that you want. But the computer science is sound, right? The algorithms are sound. So that's what we're doing here. All right, you can find an item in a linked list by sending up thoughts and prayers, popping an item off the list, iterating through all the nodes by following the next references, or indexing directly to the item with an index number. It's a linked list, so it's going to be following the chain of references. All right, linked lists have a faster time complexity than regular lists when it comes to iterating through the list. No, and this is actually a very important point. Iterating through these pointer chains, it's the same big O as iterating over a list, but in practical terms, it's much slower. Computers are optimized to like iterate quickly through consecutive memory. So it is important to note that like if you're doing a lot of iteration, a linked list is actually going to hurt you. Again, in practical terms. Inserting, deleting items in the middle of the list. Yep. It's not appending items to the end of the list or accessing items by index. So it's going to be this one. And that's actually another good point to like point out. Accessing by index in a linked list is basically impossible unless you're like, storing every index somewhere in memory. So like kind of by default in a linked list, you just like can't index into a list by index, like numbered index. So that's like another drawback of a linked list. All right, iterating. So even though iterating with linked lists kind of sucks compared to the simplicity of arrays or normal lists, we do have to do it. But the implementation is a little bit more complex and slow. That said, the iter method in Python, iter_, makes it at least so that the people using our class can have an easy time iterating through the linked list, right? So we have to write the iter method from scratch because we're implementing the linked list class, but what that does is it allows the users of our class to then use the really nice syntax. Here it's not giving the example of the really nice syntax, but it allows the users of our class to use this for blank in blank syntax. So the tests here are taking our linked list class, an instance of our linked list class here as input, and then the tests are iterating over that class using a for loop. And the only reason that this syntax works is because we're overriding this _iter_ method.
So this is kind of the Pythonic way to override that method and kind of give access to that syntax. Okay, one more thing we've got to just cover is that the reason all this works is due to generator functions. So the iter method itself is going to be, is it going to be a generator function? Actually, I need to look. Yeah. So complete the iter method. It should be a generated function that yields each node in the linked list from head to tail by overriding the iter method. Python will allow us to use a for loop to iterate over the linked list. Yeah, okay. So this is the syntax we're looking for. LL, initialize a new linked list, then we're going to add 3 items to it, and then we'll be able to loop over all the values in the linked list and print them one at a time because this syntax is going to use that iter syntax. First, we'll start with the init method. It should set the head field to none. Is that it? Is that all it does? Self.head equals none. No other node points to the linked list's head, the first node. So the linked list class itself just needs to keep track of it. Cool. We'll use the term head and tail like this. Okay, so the head points to the node, points to the node, points to the node, points to the tail. Okay, so important to understand that. And this can get really confusing, right? And it's called out right here because we just did queues where it's like, okay, things are going into the tail and coming out of the head, but it really is the same because we are going to be inserting things into the queue that builds on top of this linked list here at the end where the tail is. So keep that in mind. The head is the start of the list, but the tail is where we're inserting things. I think that's all we had to do for that. Self.head is none. Right. Which makes sense because if you look here, like we haven't even interacted with the values yet. All this does is initialize. The constructor just initializes an empty linked list. Complete the iter method. Should be a generated function that yields each node in the linked list from head to tail. Okay. So how do we do that? Let's look up here. It is our example of the yield keyword. So iter is a generator function. And the way the yield keyword works is you can think about it kind of like the return keyword. The difference is instead of ending function execution forever, the yield keyword is kind of like, hey, here's a value that I'm returning, but when you call me again, I want you to pick up here where you left off, right? So and what the function returns is actually a generator. So for example, create message generator returns this generator here that we've decided to name gen. And when we call next and give it the generator, it executes the function and returns the first thing that we yield. And then it pauses execution here, right? So we get back high into this first variable, and then we print it. The next time we call next with the generator, it doesn't start at the beginning of the generator function, right? It picks up where we left off. So the next time we call it, it's yielding there, and then finally it's yielding friend. This next syntax is kind of built into how generators work, and the for loop kind of uses this idea as well. So we just need to write our iterator method to go through everything in the linked list and call yield on the values. So self.head should be a node class, right? When it's not none. So how does that work with, we don't have the add method yet. Well, I think the tests are just kind of hijacking it and doing it for us to keep it simple for us. Okay. So our goal here is to say, all right, if self.head is not none, then we're going to yield, right? Yield self.head.val, right? Considering this is a node. Yeah, self.head.val. And then we need to do something like, we could probably use a loop here. We could probably do something like, we should probably do while self.head. Oh, we're going to need a temp variable. So the temp equals self.head. So we're going to copy a reference to self.head here in the temp variable. And then if the temp is not none, or what I should say is while temp is not none, we're going to yield temp.val, right? And then we need to move to the next. So we're going to say temp equals temp.next. We're calling it next, right? That'll execute the next iteration of the while loop. So it's going to keep going until temp is none. Once temp is none, it will exit the loop and stop yielding stuff. Did that work? That failed. String object has no attribute dot val. String object has no attribute val, right? So temp here is a string. Why is temp a string? self.head equals. Let's take a look at our instructions again. Yield the current node. So we're expected to yield the node, not the value stored within the node. So temp, right? Very good. Good to read instructions. I often forget to read all the instructions, even though I wrote the instructions. Okay, time to allow our linked list to add new nodes to the end of the list. Kind of like regular Python lists.append method. All right, complete the add to tail method. It adds a new node to the end of the list and returns nothing. If there isn't a head node, set the new node as the head and be done. Okay, let's start there. So add to tail. We're adding things to the tail of the list. So if self.tail, if there isn't a head node, if self.head is none, self.head equals node. That makes sense, right? If self.head is none, that means this linked list is empty. So we'll just set head to what we were given and be done. Otherwise, keep a reference to the last node in the list, right? So otherwise, keep a reference to the last node in the list. Start with it set to none. Keep a reference to the last node in the list. So the last node in the list, let me read the rest of the instructions. Iterate over the linked list. We built this already, right? So we can just do for node in nodes or whatever. Update your last node reference to the current node. Once you've iterated over the entire list. Oh, okay. So it's just being, I see. It's just telling me I should set a temporary variable. So we should do something like last node equals none. And then for node in self, right? Because the iter method is on self. So for node in self, right? We can just say last node equals node. So on the very last iteration, last node will be set to the last node in the list, okay. Iterate over the linked list, update your last node reference to the current node. Once you've iterated over the entire list, your last reference should be the last node in the list. The tail, set the next field of the last node to the new node, right. Okay, so we just need to say, now last node, its dot next reference, which was none because of the last thing in the linked list, needs to be updated to point to the new node. And that's it, right? Clearly not. Clearly that is not it. Once you've iterated over the entire list, your last reference should be the last node in the list, the tail. Set the next field of the last node to the new node, right? If there isn't a head node, set the new node as the head and be done. We missed that at least. I don't think that solved everything, but that was one problem. I wonder if I'm not iterating properly. Print self. Or print node. Oh, here's a problem. I think we're using the same word here. That's bad. Let's do this. There we go. Don't overwrite your variable names. Cool. That'll do it. All right. For added flexibility, let's allow users to add items to the front of our linked list as well. Remember, we're just building a linked list right now. We're not building a queue. So it's okay to break queue rules for a second. Implement the add to head method. It should add a new node to the front of the list and return nothing. Okay, cool. So the front of the list, self.head, right? So we'll be doing self.head equals node. Now that's not quite good enough because we need the new node, its next pointer to point to the old head, right? So we need to do something like node.next equals self.head, right? So take the new node we're given, update its reference to point to our old self.head, and now we're updating self.head to be the new node, right? Very good. Okay, now to use our linked list as a fast queue, order one pushes and pops, we need our add to tail function to be order one. Problem is, currently it iterates over the entire list before appending an item. Remember, we wrote this thing, and we did this iteration. We can fix this by keeping track of the last item with a new data member, tail, right? Dot tail. And it's also just worth kind of pausing and pointing this out. It's really common when you're writing algorithms that you want to be performant to make these little trade-offs between memory and computational speed. So in this case, we're storing a bit of extra memory throughout the algorithm, right? This dot tail reference. So our code is going to use more memory, but it's going to make it a lot faster, right? And sometimes that trade-off is worth it. In other cases, you might like be really memory constrained. And so you will be okay with your code running a little slower so that you don't use as much memory. It just kind of depends. But so here we're making that trade-off. It's a very small trade-off. It's literally 1 pointer. So like it's honestly not much of a trade-off, but okay. Locked-in's queue is working just fine on small data sets, but appending items once the list has over 100,000 items in it has started to take a toll on our servers. Implement these changes to speed up our linked lists inserts to order 1. All right. Add to head should set the tail reference to the given node if the list is empty. Okay, so right now add to head just does the node.setNext and then node.head, right? But what we also need to do is update the tail reference. So, self.tail, so if the list is empty, which means if self, wait, we only want to do it at the start, right? So if self.head is none, that's how we know the list is empty. Self.tail equals node. So when we're adding something to the head of the list, the only time we should be updating the tail reference is if this is the only item in the list. Cool. Next, add to tail should set the head and tail to the given node if the list is empty. So again, here we're just going to do if self.head has none, meaning the list is empty. We just need to also, like this is the only thing in the list. So we need to set the self.tail also to the node, right? Otherwise, instead of iterating to find the last node, use the tail reference to append the new. Oh, right. So hold on. Because we're going to be setting self.tail to the node regardless in the add to tail method, right? So we set self.tail to the new node. But first, in order to add it, we need to update the old tail to point to the new tail, right? So we're going to do something very similar to the add to tail method where we say, kind of old tail equals self.tail, and then old tails dot next, or I guess we have the set next method is going to be the new node, right? And then self.tail equals the new node. We can get rid of all this, right? So if self.head is none, we'll set self.head. Oh, and then we're going to return. That's potentially problematic. We don't need to return anymore, right? Because regardless of whether it's empty or not, oh no, if it's empty, we don't want to be doing this because we won't have a self.tail. Yeah, okay. So we're gonna do it like this. Special case for empty. If it's empty, we set both and we're done. Otherwise, we don't set head. We just grab the old tail, we update its next pointer to point to the current node, and then we set self.tail to the new node, right? That should be just fine. In fact, I don't even think we need this reference. We could just do this. So current self.tail, that's set next to the new node. Update self.tail to the new node. That should work. And it does. Oh, the constructor should set self.tail to none. I didn't do that. I should have done that though. To be fair, this isn't like necessary. As you saw, it actually worked without doing this. I like when a constructor initializes the values that it's going to use to none, assuming that none is the correct initial value, just because it makes it clear that, hey, this class kind of has these data members. You don't have to go search through all the other methods to find them. So I still think it's good to do that, even though it's not necessarily required. All right. Remove from head. We're one method away from having a fully functional order 1 queue. We just need a way to remove the first element from the linked list in constant time. And when we're finished, our linked list will fulfill the basic requirements of a queue. Right? Add to tail, constant time insert, remove from head, constant time pop. Awesome. So we're going to rename our linked list class to LLQ. That's already been done for us. Great. And remove the add to head functionality because queues don't allow inserting into the wrong end. We've also flipped the arrows in the printing representation to reflect the change. So wherever the repr is, you'll see now the arrow kind of points the direction of the queue rather than the direction of the pointers in the linked list. Cool. Complete the remove from head method. It should remove the first node from the list, which is the head, and return it. All right. So if self.head is none, that means the list is empty, and we should just return none. Easy. Otherwise, the list is not empty, and the head should now point to the next node in the list. So the previous self.head is what we're going to be returning. So let's save that for a second. So temp equals self.head. And now our self.head pointer needs to point to the next thing in the list because we're effectively deleting the old self.head. So now the self.head reference needs to equal temp.next. So we save temp, then we reset self.head to point to temp's next, then we return temp, right? The tail should be none if the list is now empty. So before we return, we should do something like if self.head is now none after we did that operation, then self.tail should be none. The old heads node should no longer point to anything. So this is just a nice little bit of cleanup here. We just want to do temp.next is what we call it, right? Is none. Because we're basically saying, okay, this thing that we're returning, it's no longer part of the list. Let's just kill its link, right? Run that, and looks like we got it. Okay, linked list quiz. Let's recap a few key points about linked lists. All right. So remember, the problem with our array-backed queue implementation was that it had order n pushes due to the shifting in memory. The linked list implementation now has order 1 pushes. Awesome. Now, here's the big caveat. Linked lists are usually a worse choice than standard arrays or standard lists. That's just the reality. When you're out writing code in the real world, regular list almost always going to be the right choice. When you're doing leet code and algorithms and stuff, you know, that's not always the case. But in like what I would consider like normal production code, you'll be working with a lot of regular lists. The problems with linked lists are they are less performant due to more memory overhead and just like fewer CPU optimizations. Like your computer assumes that you're working with regular lists, and there's a lot of implementation details that like have optimized that way of doing things. They're also just more complex to work with, debug, and reason about. And as a software engineer, you just shouldn't be adding complexity where you don't need to. Like simple is always better. When something can be simple, keep it simple, right? And then they have no random access, which means you can't index into a specific element of a linked list, which is like usually a huge problem. Like there's a lot of time you're writing code with regular lists and you just want to be able to index into a specific index. And then point number 4, there is another very similar data structure called doubly linked lists. And it's exactly what it sounds like. Just instead of just having next pointers that point forward in the list to the next thing in the list. Doubly linked lists just have a previous pointer that also points back. So that just allows you to traverse back through the list if you want to as well. They're better for, again, very specific things. For example, if you want order 1 insertions and deletions at both ends of the list. Okay, a queue made with a linked list instead of an array uses less memory. Nope, linked lists will use more memory. In fact, are simpler to implement. Again, no. Faster to search through? No, but can have order 1 pushes and pops. That is true. A queue that uses an array doesn't have order 1 pushes and pops because it's the shifting thing, right? When elements are added or removed from the first index of the array, all the items need to shift, which takes order n time. Okay, time to talk about trees. And specifically, we're going to be talking about binary trees in this chapter. But before we talk about binary trees, we're going to talk about regular trees. The interesting thing about trees in computer science is that we draw them upside down, which tends to confuse people. Don't let it confuse you. And what I mean by that is the root of the tree, kind of the start of the tree, we usually draw it at the top. So in this example here, we've got 2 up here. It's the root of the tree, and the tree kind of grows downward. And the way trees work, they're actually very similar to linked lists in the sense that you've got a node that links to another node that links to another node. Right? So we've got 2 here that links to 7 that links to 2 again. But the difference is with a tree, a node can have multiple children, right? So in this case, 2 links to 7 and 5, right? 7 links to 2, 10, and 6. So instead of just one child or one next node in a tree, you can have multiple. It doesn't work the other way though. A node cannot have multiple parents, so it only kind of spreads out on the way down. Again, kind of like a tree. You can only have like one trunk or one root of the tree. So that's how a tree works. Other than that, very similar to a linked list. All right, so multiple nodes in a tree can have the same value. Sure, why not? Parent nodes can have blank children, and children can have blank parents. Well, parent nodes can have many children or multiple children, but a child can only have one parent. Okay, so we just talked about regular trees, and the rules with regular trees are very unrestrictive, and there's a lot of things you can do with a regular tree They're not particularly useful though. Unbeknownst to our programmer humor, binary trees are actually used in the real world, not just as fodder in LeetCode code style interviews. Binary trees are the quintessential data structure. They're the ultimate tool for efficiently storing and organizing data. Unlike stacks or queues, a binary tree can be searched for a specific item and can be searched quickly. Binary trees are made up of nodes where each node contains a value and references to, at most, 2 other nodes, which is what makes it a binary tree. Those 2 nodes are called the left and the right children. The top node is the root, and the tree grows down from the root. So what makes binary trees fast? Well, it's that they're always pre-sorted. Every node to the left of a parent node has values less than the parent, and every node to the right has a greater value. Sometimes a binary tree just stores numbers, which makes greater than and less than operations really simple, but usually they store more complex data like employee information. When they do, we just need to pick an ID, which is just a number, to sort by instead. This less than, greater than structure is what gives binary trees their fast searching capabilities. Let's say you're looking for the number 6 in a tree. You start at the root and move down, and at each node, you decide whether to go left or right by comparing 6 to that node's value. Each time you make a comparison, you're eliminating half of the tree. We don't have to compare against every node in the tree, just one node in each level of the tree. This process is called binary search, and it means that even in the worst case, the number of comparisons is limited to the height of the tree. In big O terms, that means that it takes order log n time to search the tree instead of order n, or linear time. If there are 1 million items to search, and each comparison takes 1 second, then a linear, or order n, brute force search takes almost 12 days. With a binary search tree, it takes about 20 seconds. But it's not just the searching operation that's fast. Inserting, updating, and deleting are all order log n as well. That's why binary trees power databases, file systems, and even Google searches. While you don't get those sexy order 1 operations that you would get with a stack or a queue, at least you can search the thing, something that stacks and queues don't allow. There are things we model as trees, like your file system, for example, but that's not really what I'd consider like a data structure that's useful for writing performant algorithms. So binary trees are a little bit more restrictive than regular trees. They have some additional rules that we're about to talk about. And the purpose of those rules is to make the data structure fast to use. Right? So similar to how a stack and a queue gave us all these O1 operations, a binary tree is going to give us a lot of order log n operations, which is not quite as fast as order 1, admittedly, but binary trees are a lot less restrictive. We're actually allowed to search through the tree, for example. Like you can't search through a queue or a stack, right? You can just get the next item. But with binary trees, you actually can do searching and you still get really, really fast lookups, log n. Okay, cool. So what are these additional restrictions? Well, first of all, instead of an unbounded list of children, every node can have at most 2 children. So just 2 children. That's why it's called a binary tree. Additionally, the left child's value must be less than its parent's value, right? So if you have 2 at the root, whatever's to the left of the root has to be, or sorry, for you, the left of the root has to be less than 2. So 1, right? Assuming that we're storing integers. Similarly, anything to the right of that node must be greater than to the right. Sorry, I have to switch up my directions when I'm pointing. So that means that the binary tree actually ends up being an ordered tree with all the less than stuff off to the left and all the greater than stuff off to the right. And then no 2 nodes in the binary tree can have the same value. So we deduplicate stuff, kind of like a set. Cool. And then by ordering the tree like this, as we add and delete things from the tree, it keeps all the operations very fast. So the tree is always it's always in a pre-ordered state, which is what makes traversing it, adding things to it, deleting things from it very, very quick. So nodes in a binary tree can have at most 2 child nodes. Binary search trees, as opposed to generic trees, must be unordered, no. Randomized, no. Ordered, where left is less than right is less than parent, not quite, because the right child actually needs to be greater than the parent. So left, parent, right. Okay. Insert nodes. Okay. Time for us to actually start building our binary tree. And it looks like the way that we're doing this is we're building a class called BST node. Each instance of this class is going to represent a node in the binary search tree. And the way we'll know we're working with a root node is we won't, it looks like. So we could just, at any given node, we can make a tree, and that's just how we're modeling it, which kind of makes sense, right? Like each individual node only needs to know about its children. It doesn't necessarily need to know about its parent. So, when you're working with the whole tree, you'll just have to have a reference to that root node, and that will be the tree. Throughout this chapter, we'll be building a binary search tree to power Locked-in's custom database. Locked-in's management doesn't trust so-called open source, so here we are. This is a really good point. Binary search trees are used under the hood in basically every major production database, which is one of the reasons it always frustrates me when people say, like, I don't need to know anything about binary trees. I've never used one as a programmer. That's not true. You've used them all the time. You just may have not written them from scratch. It's kind of like the same thing as sorting algorithms. It's like, it's useful to know that sorting algorithms are typically order n log n, that there are a bunch of different sorting algorithms, and that they're usually a standard implementation ships with your programming language of choice. Binary trees the same way. They power a lot of things, specifically databases. We just don't typically need to rewrite them from scratch as programmers because there's already a really good implementation. But understanding why binary trees are fast makes it easier for us to understand why our databases are fast and why they're slow when they're being slow, which is a very common optimization problem in, for example, backend engineering. Let's keep going with the assignment here. So each node in our BST will represent a locked-in user. Okay, cool. So we've got this user class, and it looks like that's going to be the value that we're storing in the node. And then we've also got these left and right references that we'll be using to point to the next BST nodes, or the child BST nodes, the ones that are underneath. Okay, cool. So our job here is just to complete the insert method of the BST node class. This is how we're going to insert new values into the binary search tree. A new binary search tree starts with the value that it's given and left and right that are none. So it's just a single node. So our insert method is going to have to start inserting things below that root node. It's going to be a recursive method. We're going to start kind of following this pseudocode. So if the node doesn't have a value yet, just use the given value and be done. That's fair enough. So if self.val is none, then self.val equals val, and we can return. Cool. So that just handles the kind of the case where someone created a binary search tree and didn't provide a value, right? Which it looks like, isn't always going to happen. Looks like we've written it in such a way that you can provide an initial value to the BST, but you also could not. So it's kind of up to the user. Okay, if the node's value is equal to the given value, just be done. No duplicates allowed, right? So, okay. So if the node that we're currently on, again, remember, this is a recursive method. So we could be at the root. We could also be somewhere down farther in the tree. So if we're just on the node that already has the given value, we can just be done because it's already there. So if self.val equals val, we can just return. Now, I know that we're working with user objects, right? But if we take a look here, you can see the equals, less than, and greater than operations are actually overridden, which means we can actually just use, the equal comparison operator, and it will use this method, which is going to, return whether or not the two user objects are effectively equal, which is what we want. Okay, so if they're equal, we'll return. If the given value is less than the node's value, and the node doesn't have a left child, what's in this tip, by the way? Oh, okay, it's just telling me to use pen and paper if I need to. Okay. If the given value is less than the node's value and the node doesn't have a left child, create a new left child node with the given value. So if the given is less than the node's value, so the given value is val, is less than self.val, and the node doesn't have a left child. Let's do this. I'm going to nest these if statements. So if value is less than self.value, and if the node does not have a left child, so if self.left is none, create a new left child node with the given value, right? So self.left equals BST node with the given value, okay? So if the value is smaller than us and we don't already have a left child, we're going to create a new left child. Seems good. And I think that means we can then return, right? Okay, so what happens if the value is less than self.value, but we do have a left child? Are we gonna handle that right now? Let's see. Given value is less than no child that does have a left child, recursively call insert on that left child with the given value. This is where the recursion comes in. So self.left.insert value. Okay. So we know we need to move left because this value is less than us, but we already have a left child. So we're just going to move our recursion down. Sorry, I know I'm screwing up the directions. I'm just going to do that. Moving down to the left, and allow the recursive call then, right, which is then going to redo all this logic to take care of it. So then we can return. Cool. Since we already checked if the given value is equal to or less than the node, the value must be greater than the node. Oh, we got rid of, oh yeah. We got equals and we got less than. So it must be greater. Yeah. Okay. So now we should do the same logic for the other side. If we're here, then it must be greater. So self.right, if self.right is none, then we can just set self.right equal to BST node with the value and return. Otherwise, we need to recurse self.right.insert the value and return. Whew, that feels right. Let's see how that goes. Looks like we got it. Okay, so inserting into a binary search tree, like most binary search tree operations, is very fast. It's very important to understand. Think through the recursive method that we just wrote. In fact, I'll pull it back up on the screen really quick. How many times, right? First of all, there's no loops in here, right? There's no iteration. There's just recursion. So the question is, how many times do we recurse, right? Do we recurse for every single node in the tree? And the answer is no, because at any given point as we walk down the tree, we're never calling insert twice for a given node, right? So like from the root, we don't recurse down into both the left and the right children. We're recursing into one or the other, the left or the right child, which means we only recurse once per level of the tree, right? So say there's, 3 levels of the tree that could support 1, 2, 3, 4, 5, 6, 7 different nodes, right? We only have to recurse 3 times, which is actually log base 2 of n, right? So the big O of the insert method is actually log n, which is very, very fast. On small trees, it's kind of hard to picture, but as the trees get bigger, it makes more and more sense. Like take a look at this visual and let me, I'll blow it up a little bit for you. So with just 3, levels 0, 1, 2, and 3, this is a lot of nodes. 1, 2, 3, 4, 5, 6, 7, 8, plus 8, that's 16 nodes, right? 16 nodes, but only 4 levels. And as the tree gets deeper and deeper, it gets even more crazy, right? With 1 million nodes in the tree, it would actually only be 20 levels deep, which means 20 recursive calls. So this is why binary trees are so fast. It's because as you add more and more nodes, they typically actually don't get much deeper, right? As long as the tree is balanced, which is something we'll talk about later. But then when you go from 1 million to 2 million nodes, you only add 1 more level to the tree, right? So again, this is why databases use binary trees under the hood to keep lookups fast, because order log n isn't quite constant time. It's not quite order 1, but in most practical cases, it feels like it's constant because the log of a number is just so small. What is the average big O complexity of the insert method? We've kind of beat the dead horse here. It's log of n. Okay, min and max. Some of the simpler BST algorithms are the getMin and getMax methods. Now that we can add users to our BST, our systems team wants us to start implementing search functionality. Okay, so we need to implement the getMin and getMax methods, which should return the min and max values in the BST respectively. Let's think for a second, picture our tree, right? Where in the tree is the minimum value? Well, we know that to get a smaller value, we have to move left. And if we want to keep getting smaller and smaller values, we have to keep moving left. So the smallest value should be the very leftmost item, right? And then the greatest value should be the rightmost item in the tree. Am I doing that right? Left, right. Yeah. I think I'm doing that right. Okay. So that means we just need to walk down the left pointers to get the minimum, and then once we reach the end, we just return that value, right? So let's see what that looks like. To walk these types of lists, we've had to use temp in the past, right? So something like temp equals self.left, right? And then we do something like while self.left is not none, then we update temp to be self.left. So we'll just kind of iterate we'll kind of keep iterating through this. We could use recursion here, but I think it's nice to kind of shift between the two different ways of doing things. Using iteration, using recursion. So, anyways, we'll use iteration here with the while loop. So every time self.left is not none, we will move self.left, right? And then by the end, self.left will be none. And so we need to, while temp is not none. So every time temp is not none, we're going to update temp to be self.left. That's a problem, because then by the end, we'll actually just have none, which is not what we want, right? So I think what we want to do is say temp equals self, and then while temp.left is not none, we update temp to be temp.left, right? So then by the end of this, temp should not be none unless we started with like an empty tree, in which case, self would just be none. So like that would be a problem. And then we want to actually return the value. I think that's right. Cool. And then get max. I should just be the opposite. So temp equals self, while temp.right is not none. Temp equals temp.right, and then return temp.val. Okay, how is that? I think we got it. Now we need a way to remove users from our binary search tree, or delete nodes, right? Which is going to be another recursive method. It takes a value as input and deletes the node with that value if it exists. Okay. Each call returns the new root of the tree or subtree after deletion. Okay, this is a really important part, and this is honestly the most confusing part. The delete method, we're writing it in such a way that it needs to return the new node at that location, right? So it's a recursive method. So imagine I call it on the root of the tree, and the root of the tree needs to be deleted. It needs to return the new root of the tree, which might be like the left child or the right child or some other node down within the tree that is now the new node that's at the root after the deletion happens, right? So we're gonna like fill in that spot and return that node so that the caller of that function knows like where the new thing at that spot is, right? So if we look at how it's actually called, like the new BST equals BST.delete and then like character, right? Let's jump right into it. So check if the current node's value. So if self.val is none, we're just going to return none. Easy enough. Nothing to delete, right? If there's nothing there, there's nothing to delete. If the value to delete, so if val is less than self.val, check if there's a left child. So if self.left, if there is a left child, we need to recursively call delete on the left child. So self.left.delete val. Right, so what we're saying is if the thing I need to delete is less than me, so I need to go left, and I already have a left child, I need to recursively call delete on that left child, because it's not me that needs to be deleted, it's my child or, my child's child. So let's move that way in the tree. Okay, and that's going to return the new self.left, right? Oops, self.left. Right? Again, because the delete method returns the new thing that's going to be at that spot. And then either way, whether we have a self.left or we don't, we need to return the current node. So we're done with the deletion at this point. We just need to return self. In the case where we have a left-hand child, we're going to recursively call delete on it. Otherwise, we're just going to return our self, right? That makes sense. Okay. Do the same but mirrored for right. So if val is greater than self.val, then if self.right equals self.right.delete val and return self, right? And again, the reason we're just returning self here is because if it's greater than us, we don't need to do any additional deletion of ourselves, right? So if we get down to this point, right? If we've bypassed both these cases, it means val equals self.val. So it's actually us. It's the node that we're currently on that needs to be deleted. Now, if there's no right child, return the left child. Okay, that's easy enough. If self.val, or sorry, if there is no right child. So if not self.right, if there's no right child, yeah. If not self.right, return self.left. And then we need to do the same thing for the left child, right? If not self.left, return self.right. Now you might be thinking, well, what if there's not a self.left or a self.right? Well, that's actually okay, because if there's not a self.right and self.left is also none, we'll just end up returning none here, which is actually what we want because we're trying to delete ourselves. So if we don't have any children, we can just return none because there should be nothing at this spot now, right? Okay, but what happens if we, the case we really care about now, so we've essentially handled 3 cases. We've handled no children, we've handled no right, no left, and now we need to handle the case of both. So if there are both left and right children, find the minimum larger node. It suggests using the min larger node by setting it equal to self.right. So we want a larger node, so it's going to have to be in our right-hand side tree, but it's actually going to, or I should say our right-hand side tree. Sorry, I'm going to get the directions all mixed up. It's going to be in our right-hand side tree, but it's actually going to be the leftmost node in the right-hand side tree. So we can do something like while min larger node dot left, min larger node equals min larger node dot left. Okay, so that should be it should be the node in the tree that is one value greater than our current value, right? We just want like the next thing. So if we have like, a tree of numbers and we're 5, we're trying to find 6, which won't necessarily be our child. It'll be our child's leftmost child, our right child's leftmost child. I'm screwing up the directions. Okay. So we found that. Next, replace self.val with min larger node .val. Okay, so this is important. We're not actually updating the node references. We're just changing the values. So we're saying, okay, me and my spot, I'm now going to just change my value to be the same as that node's value. And then what we're going to do is go delete that other node, right? So we didn't have to update all the pointers. We just copied in the value that we cared about, and now we're going to go delete the old one. So we do self.right dot delete min larger node dot val. Now remember, the delete method actually returns a node. It returns the node of what should now be in that spot. So we need to do self.right equals self.right dot delete, and then we need to return what should be in our current spot, which is self. Cool. How's that? Looks like it's working. Very good. So you can see, here's our tree. Let's go up to one of the first ones. We've got a tree. It's got these different users with their IDs, right? And the IDs are what we're actually using to determine what's greater and what's less than. So for example, here we've got 10 at the root. So John has to be less, 5, right? And Brownfield has to be greater, 16. And then Lipman has to be greater than Brownfield. Imagine that this tree, if you want to visualize it top to bottom, you just kind of have to flip it. And then what we did is delete number 5 and number 10. So Venet got deleted and John got deleted. And the new tree, after our operation is done, you can see Venet and John are gone. But importantly, the order is still preserved, right? Burry is still less than Brownfield, Lipman is still greater than Brownfield, and Blake is less than Burry, right? And it works even on these larger and larger trees in the later tests, which is pretty cool. Okay, deletion review. So the delete method is order log n, because like most binary tree operations, we don't have to search the entire tree. Again, we only had to recurse the depth of the tree, just like the insert method. Super cool. So the depth of the tree on average is equal to log base 2 of the number of nodes. So again, this doesn't matter as much in a small tree, right? 2 nodes, 1 depth, 4 nodes, 2 depth, 8 nodes, 3 depth. Feels like, it doesn't actually matter that much that it's log n. But look, if our binary tree had 4,000 nodes in it, the depth is only 12, which means we would only have to make 12 recursive calls or 12 iterations, right? To make a deletion, which is really, really cool. Because production databases have lots and lots of rows. I mean, we have tables in our database on boot dev that have many millions of rows, right? So you just got to watch, we need these sort of algorithms if we want our websites to be fast at scale. All right, what is the approximate depth of a tree with 16,000 nodes? Okay, so if 4,000 has a depth of 12, then 8,000 would be a depth of 13, and 16,000 would be a depth of 14. Cool. What's the average big O of the delete method? Still log n. A pre-order traversal is a way to visit all the nodes in a tree. It's called pre-order because the current node is visited before its children. So for example, given this tree, again, if you prefer to visualize top to bottom, you just gotta flip it, would be traversed in this order, starting at 4, then 2, then 1, then 7, then 6. It's called pre-order because the current node is visited before its children. Right, 4, 2, 1, 7, 6. Sometimes it's useful, albeit a bit slow, to iterate over all the nodes in a tree. But this way of traversing the tree in a specific order is very useful. I mean, again, imagine a database. Sometimes you need to get a set of users within a range, right? Like give me all the users that were created in this date range. You still want to be able to access the values in a specific order. And so sometimes you do need to traverse a tree this way. All right, implement the recursive pre-order method. Returns a list of the values in the order they are visited and takes as an argument the ordering of values we visited so far. Here's the algorithm's steps. Visit the value of the current node by appending its value to the visited array. Okay, so by appending its value, so visited.append self.val. Okay, so the visited array is just keeping track of what we've visited so far so that we don't revisit it. Okay, recursively traverse the left subtree. So it's going to be something like self.left.pre-order, right? Visited, something like that. Recursively traverse the right subtree. Okay, so this is very important, right? For each node, we need to then traverse both sides of the tree. So this is important because now this algorithm is not log n, right? Because it's going to go through the whole tree. So it actually is order n. So self.right.preorder visited, and then return the array of visited nodes. So return visited. Now, let's see. We need to handle the case where like this is none, right? So I think we need to do if self.left. Oops, if self.left, and then if self.right. So again, order of operations here. This is a pre-order traversal, which means first we visit ourselves, then we visit the left-hand side, then we visit the right-hand side, then we return the visited. Let's see how that looks. Looks good to me. Okay, post order. So again, this is just a way to traverse all the nodes in the graph. The order is just a little different now. We're going to visit in this order. So 1, 2, 6, 7, 4, which really just means we're visiting the current node after we're visiting the children. So I think we're going to go left, right, self. So it'll be something like if self.left, self.post order visited. If self.right, self.post order visited, and then visited.append, self.val, and then return visited, right? Uh-oh, I failed. Did I do my lefts and rights out of order? Oh yeah, self.left.post order, self.right.post order. Is that right? Yeah, there we go. In order traversal, I think this is our last traversal. So this is the one that actually makes the most sense and the one that you'd probably use most of the time, which is just like, given a binary tree, return the nodes in order. So, given 4, 2, 1, 7, 6, we return the actual array 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 1, 2, 3, 4, 7. 1, 2, 4. There's no 3 there. 1, 2, 4, 7, 6. Okay, cool. This one, we actually do left, then self, then right, which makes sense, right? Because left is like the lowest value, then our self, and then right is the greater value. So if self.left, self.left dot in order visited, and then visited dot append self.val, if self dot right, self dot right dot append self dot right dot in order visited, return visited, right? And run that and submit it. Very good. One thing that might be worth pointing out here is just that, so you might be noticing that I'm not capturing the return value of in order here. And the reason for that is that lists in Python are passed by reference. So actually when this inOrder method updates the visited list, that update also happens to the visited list that I have here. But it doesn't, like, if I want it to be extra clear, and to be honest, I actually prefer to write this way, I could do this, right? Because now it's more clear that I'm mutating and then recapturing the value of the updated array. That should, yeah, it still works just the same. So, but I do actually think the second way of writing it is a little bit clearer. Okay, node exists. In Logged In, it's common for one user to navigate directly to another user's profile. We even creepily give the stalked user a notification that someone's looking at their profile. Weird. To make this feature work, we need to be able to quickly check if a user exists in our tree. All right, complete the exists method. It should take a value as input and return true if the value exists in the tree and false if it doesn't. This is a recursive method. We're gonna have to traverse the tree, but again, it's gonna be log n because we won't need to traverse the whole tree. Okay, so let's think through how this will work. We just need to return true or false at every iteration. So let's go through the base case. So if self.val equals val, then return true, right? That's pretty straightforward. If val is less than self.val, then we need to go left, right? And we should just be able to do so if self.val is less than us, we need to know whether or not we have a right-hand child or left-hand child. So we actually should do something like and self.left. And then we want to return self.left.exists val, right? Similarly, if val is greater than self.val and we have a right child, then return self.right.exists val, right? And then down here, this would just be the case where it's less than us and we don't have a left. So we actually just return false here, right? How's that work? And we got it. Okay, so we've done binary trees. Now, binary trees have this problem. They have this problem that's unaddressed by the implementation that we built in the last chapter. And that's that they can actually become very unbalanced. So take a look at this binary tree right here. So this tree has 1, 2, 3, 4, 5, 6, 7 nodes, but it already has 5 levels. It's already 5 levels deep. And that's because this is an unbalanced tree, and a regular binary tree doesn't protect against this. If you keep inserting items in order, they'll just keep going down the list. Like with this tree, if we were to insert 36 and then 37 and then 38, it'll just keep making a long line. And eventually what it does is it basically degrades down to a linked list, right? Because again, the speed of the binary tree depends on it having few levels, right? Because the big O is actually directly correlated to how many levels the tree has. So what you want is a nice balanced tree like this, right? Where as new things are inserted, they kind of go into the spot in the tree that keeps the tree shallow. You want it wide, not shallow. Okay, so that's the problem. And we'll talk about the solution in just a second, but that's the problem. And that's why we don't like unbalanced trees and we do like balanced trees for speed. So the quiz here is, if 100 sorted items are inserted into a BST in order, what will be the big O complexity of the lookups? And the answer is order n, because it kind of degrades into this linked list where you'll just have to traverse that whole branch of the tree every single time. Assuming the tree remains balanced, will a balanced tree's operations ever degrade past order log n? And the answer is no. As long as the tree is balanced, everything should be log n. So will it degrade? No. Cool. So regular old binary trees have a problem. They have no built-in protection against unbalance. If you insert an ordered list into a binary tree, you'll end up with a single branch in your tree, which is no better than a linked list. Your efficient order log n lookups degrade right down to order n. But a balanced tree is a fast tree. And by balanced, I just mean it's about as wide as it can be. It doesn't have these super long branches that take forever to iterate down. So how do we keep our binary trees balanced? Well, the red-black algorithm, or the red-black tree data structure specifically solves this. Here's the big idea. When items are inserted and removed from a red-black tree, we have one little extra step. Take insertion, for example. After inserting a new item into a red-black tree, we have a fix step. And in the fix step, we check the state of the tree, and if it's starting to become unbalanced, we perform a rotation, which is basically just where we take the longer branch of the tree and fold it back into the rest, which flattens the tree as a whole. Now, first of all, don't let the colors red and black confuse you. They're really just a Boolean value that we attach to each node, true or false. The only reason we use the words red and black is so that it's easier to draw out and visualize. The idea is that every node in a red-black tree has this extra bit of data, it's color. And we use those colors to know if the tree is sufficiently balanced or not. There are just a few simple rules. First, each node is either red or black. Second, the root is black. Third, all nil leaf nodes are black. Fourth, if a node is red, then both its children must be black. And fifth, all paths from a node to any of its descendant nil nodes, the bottom of the tree, must go through the same number of black nodes. Now, that last rule, that all paths from a node must go through the same number of black nodes to reach the bottom of the tree, that's the ticket. When a branch starts to get too long, we rebalance the tree by performing a rotation to make sure it still follows the rules. So let's focus on the rotation. That's really the most interesting part of a red-black tree. Now, rotations can work both right and left, but let's look at a left rotation. A right rotation is just the mirror of it anyways. So first, we start with this tree. 4 is the pivot, and 2 is the pivot's parent, and these are really the nodes that we're rotating around. First, we update the pivot's left child reference to now point to what was its parent, 2. Next, that left child that we just orphaned, 3, we make it the right child of the old parent. And that's it, we're done. Let me show that to you one more time. Now, it's important to understand this actually happens inside of a tree. So here's a visualization of the exact same thing happening inside a larger tree. And here it is again one more time. Okay, so the problem of balanced trees and unbalanced trees, or really just the problem of unbalanced trees, is solvable, luckily. The algorithm for binary search trees just needs to be tweaked a little bit, and then we can account for this balancing problem. We can ensure that even if a user of our binary tree inserts, each node kind of in order, by using a red-black tree, we can continuously rebalance the tree as we go so that it stays balanced. And then that way our later like delete operations, update operations, get operations, they all stay order n. So what it does is it adds a little bit of overhead on every like insertion and deletion because we need to rebalance the tree. But it keeps the tree balanced so that everything's fast. And luckily that rebalancing is also order n. So we're essentially trading a bit of constant time to keep our red-black tree really, really fast, or to keep our binary tree really, really fast. Cool. Okay, so how does it work? Let's take a look at this diagram. So here we have our binary tree, right? What we're essentially doing is we're adding a couple things here. First is we're adding coloring to the nodes. So we're saying that every node in the tree is now either a red node or a black node. And we're also adding kind of fake leaf nodes to the bottom of the tree. We're calling them nil here, that are also kind of considered black nodes, right? So this will all make sense in a second, but just for now, understand that the reason it's called a red-black tree is that we're adding kind of these fake colors. Now, the actual color doesn't matter. We could do purple and blue. It's just a label. It's just a way for us to visualize what's happening. The important thing is there's now 2 types of nodes, right? And we just happen to be calling one of those types black and one of those types red, right? So, okay, just understand there's two types. And we now also have these little nil nodes at the bottom. And again, what this means is every regular node now has 2 children that are either other regular nodes or
nil nodes. So there's like no regular nodes anymore that have like none as their children. They always either have another node or one of these special nil nodes. So like, why does this work? The reason this works is when we insert or delete or whatever into a red-black tree, we're going to put the new node in and then fix the tree so that it stays balanced. And the algorithm for doing so relies on the red and the black markers. Let's jump into it. It'll start to make more sense. Okay, so as it turns out, let me shift this over here. As it turns out, we've been inserting user records into our tree with incrementing numerical IDs, right? This is very common for databases. Pre-sorted data, which means the app's user lookups are starting to get really slow because we're effectively building a linked list instead of a binary tree, right? The RB node class, what we got here, is already implemented for you as well as its init constructor, right? So you notice this constructor is a little bit different than the last BST node that we were working on. The main differences are now we have a pointer to our parent. That's new. Before we didn't keep a reference to our parent, right? Parents only kept references to children. We've updated that. And then we also have this self.red property that is initialized to false. So that basically just means this is black, right? So if self.red were true, it's a red node. Otherwise, it's a black node. Okay, cool. The RB node class is already implemented for you, as well as the constructor. There's also a data member self.nil created for you in the constructor. Okay, so let's take a look at nil right here. So this is the RB tree class. So we've got two different classes here now. We've got the RB node and the RB tree. So, I mean, this is a perfectly fine way to model this. We could have done this in the last chapter with binary trees, right? Where we had like one class that's explicitly the entire tree and one that's just the individual nodes. We chose to just do the nodes themselves. The only difference here, of course, is like here we're being more explicit about it. Like this is the whole tree. And then when we recurse, we'll just be working with the individual nodes. So, okay. So when we create a new red-black tree, we're just creating, like the thing that's happening is we're creating the root of the tree and setting it equal to this self.nil. Okay, so up here in our diagram, all these little leaf nodes, those are nil nodes. When we create a new red-black tree, the root is a nil node. And the nil node, we're actually just going to save it as a data member. So they'll all technically be like the same, they'll all be copies of the same nil node. And it's just a red-black node that doesn't have a value. Okay, very straightforward. It's also a black node, right? It has no children. And so self.root in our RB tree is going to be set to that nil value to start. Okay, so that's the starting position. Complete the insert method. It should take a value as input and add the value as a new node in the tree if the value doesn't already exist. Whew. Okay, so this is going to feel a lot like a regular binary tree at first, and then I think we'll see maybe some differences. So create the new node. So first we need a new node that's an RB node, and we give it the value, right? That's how that works. Yep. Okay. The new node should not have a parent yet. Okay, that's easy. We just don't set a parent. The left and right children should be nil. So we want to do, right now they're none. So we want to do new node dot left equals self dot nil and new node dot right equals self dot nil. Okay, the new node is red. So new node dot red, set that to true. Okay, now we've got our new node. Find the parent of the new node if there will be one. Okay, so first we're just going to initialize a new parent and set it equal to none. We haven't found it yet. Initialize a current variable. It's the root node of the tree. All right, so we're going to need a current, and we're going to start it at self.root. While current is not a nil node, so while current does not equal self.nil, set parent to the current. So while current is not equal to nil, set parent to the current. Parent equals current. So it starts at the root. If the root is not nil, we set the parent to the current, right? So this is gonna, so starting at the root of our tree, if it's not a nil node, we're setting the parent to that current. And then we need to, if the new node's value is less than the current node, so we're gonna like move down the tree until we find our parent, right? So
let's see, if new node.val is less than current.val, and we know that it's not nil, so it's got to have a value. Okay, if new node.val is less than current.val, set current to its own left child. So current equals to its own left child. So current equals current.left. We also probably need to handle the case. So if new node.val is less than current.val and current.left does not equal self.nil, then we move left, right? Or actually, no, it's okay. It's okay, because if we do set it to self.nil, that's what actually breaks us out of this loop, right? Which I need a colon on. Okay, if new node's value is greater than current.val, then we set it to its right child, right? Otherwise, if the values are equal, just return because this value is a duplicate, right? That makes sense? Just return. So we do something like elif else. Okay, let's think through that really quick. So the whole reason we're trying to find a parent here, right, is so that we can insert the new node and update the parent's pointer to point to the new node that we're creating. And so if they're equal, then we just want to return. Otherwise, we're just going to keep updating this pointer. Then by the end of this loop, current should equal, well, it should equal self.nil, but it should have a parent. No. Okay, let's read. Parent should now be a reference to the node that will become the parent of the new node. Oh, right. Parent equals current. Right. Okay. So current's going to be self.nil, but parent should now be the correct parent because it's essentially lagging behind in this loop. Okay. So by now, right, parent is the new node's parent. Assuming we got this far. Okay. Insert the new node by setting the parent's child, right? So parent dot, now which way are we gonna go, right? Set the new node's parent to the parent we just found, right? So, okay, well that part's easy. New node dot parent equals parent by setting the parent's child. If the parent is none, we're dealing with a new root. So set the, oh yeah, right, we need to handle that. So if parent is none, we're dealing with a new root. So set the tree's root. So self.root equal to new node. Parent's the parent we just found. Right. That can happen either way. If parent is none, self.root equals new node. Okay. Otherwise, compare the values of the parent and the new node and set the parent's left or right child right. So this is where we say whether it's going to be a left child or a right child. So if new node.val is less than parent.val, so if it's none, we need to actually set it and return, right? New node.parent equals parent. If parent is none, right, it's okay for the root to have a parent that's none. So that should be fine. If new node.val is less than parent.val, then parent.left equals new node. And we already covered the case where they're equal. Did we cover the case where they're equal? If they're equal, we did nothing, right? Or did we handle that? That was right here. Right. So they shouldn't be equal at this point. It makes me nervous that like that's far away. I don't love when like a missing conditional is like far away in the code. If new node.val is greater than parent.val, parent.right equals new node. And then what I'm going to do is I'm going to make these guard clauses. And then I'm just going to say like, hey, if we get here, I'm going to like raise exception, be like, this should never happen. Let's see what happens there. And it looks like we got it right. So I just want to talk through this bit here. So, okay, first of all, I just want to be clear. We just rewrote the insert method basically from the last chapter. We have done nothing fancy here with red black trees other than the fact that we've properly set nodes to be, well, I shouldn't say properly, but we have set nodes to be red. So we're just like getting introduced to this concept of there being a coloring at all. Other than that, this is a very normal binary tree where we also have parent pointers, right? But we haven't done any rebalancing of the tree yet. So this will still result in an unbalanced tree. That's okay. And then again, the reason I did this was because it just makes me nervous when I have, a comparison that does a less than and then one that does a greater than, and then I don't have an equal to. And it's okay because I was taking care of that up here, but that's just like far away. And so what I'm doing by adding this raise exception is it's just me telling myself, hey, I should never really get to this line. And if I do, something's wrong. And so if it does happen, this will be thrown and I can go, oh, like there was a bug in my logic, right? I made an assumption that's not true. Okay, so now let's take a look at the rules of a red-black tree. So in addition to all the rules of a binary search tree, a red-black tree must follow some additional rules. So each node is either red or black, straightforward. The root must be black. So this rule sometimes is omitted, but since the root can always be changed from red to black, but not necessarily vice versa, this rule does have not a ton of effect. But I believe in our implementation, the root is going to be black, right? All nil leaf nodes are black. They're always black. Okay. If a node is red, then both its children must be black. And all paths from a single node go through the same number of black nodes to reach any descendant nil nodes. That's an interesting one, right? So, okay, the root's always black and the nils are always black. And the path to go from any single node, all paths from a single node go through the same number of black nodes to reach any descendant nil nodes. So, for example, I could take this 17 right here. It needs to go through one black node to get to this nil. It also only needs to go through one black node to get to this nil. One black node to get to this nil, right? Same with this 13, right? One black node to get through this nil. So it's like you can go through as many red nodes as you need to get to the bottom, but you have to go through the same number of black nodes to get to any nil node, right? And this is where that balancing starts to become enforced, right? Because we need to make sure that the tree is at least balanced enough. It needs to be balanced enough so that rule remains true. And you go, okay, well then couldn't you just use all red nodes? Well, that would be breaking rule number 4. If a node is red, both its children must be black. So you start to get these alternating levels, right? Okay, red-black trees are perfectly balanced. Red-black trees actually are not perfectly balanced. They're just balanced enough, I think. Let me make sure I'm reading my own definitions correctly. The rebalancing of a red-black tree does not result in a perfectly balanced tree, right? However, its insertion and deletion operations along with the tree rearrangement and recoloring are always performed in O and log n time. Okay, so a perfectly balanced tree, I think we'll talk about this later, would be we would never have even just a little bit of unbalance, right? So this tree isn't balanced. We've got this extra node over here. What the red-black tree guarantees is order log n time. So the easy way to think about this is that a red-black tree guarantees enough balance for the performance that we're looking for. And we'll talk more about perfect balance later, but that's honestly more of a theoretical construct than what actually matters for it being fast. Okay, so they perfectly balanced? No. Red-black trees always have worst case order log n insertions, deletions, lookups, and arrangements. That is true. It doesn't get worse than log n for red-black trees. Okay, now it's time to actually rotate the tree. So like I mentioned in the last assignment, our insert method just inserted kind of like a normal binary tree would work, just with these additional red and parent members, right? Now what we're going to add is some rotation methods, and these are the actual mechanism of the red-black tree. They're what look at the colors, the red and the black colors, and decide based on the coloring how they're going to rearrange the tree to keep it balanced. That's the high level thing that you need to understand. The rotations keep the tree balanced. And the way they work depends on the classification of the node, whether it's red or black. Okay, so let's take a look at this explanation. Every time one branch of the tree starts to get too long, right? So imagine the example we gave at the beginning of the chapter where we've got kind of one branch of the tree getting super, super long. We rotate those branches to keep it shallow. So we kind of fold it back into the tree. And a shallow tree is a healthy, fast tree. So a properly ordered tree pre-rotation remains a properly ordered tree post-rotation. So every time
like we will hit a place in the growth of our tree where we'll decide, okay, it's time to rotate. And whenever we rotate, we are starting with a valid red-black tree and we're ending with a new but still valid red-black tree, right? It adheres to all the rules that we talked about before. When rotating left, so let's take a look at this example of a left rotation. The pivot node's initial parent becomes its left child. All right, let me blow this up. Okay, when rotating left, so there's left rotations and there's right rotations. When rotating left, the pivot node's initial parent becomes its left child. And the pivot node's old left child becomes its initial parent's new right child. So here's the visualization. So we got this tree and we're pivoting on node number 4 right here. Number 2 is the pivot's parent. It can get a little confusing trying to keep track of both the pivot and the pivot's parent, but just work with me here. So pivot's number 4, its parent is number 2, right? Start the left rotation on the pivot. The old left child, right? The old left child of the pivot gets replaced by the parent, okay? So the old left child, number 3, right, is getting replaced by the parent. So 2 is coming down here and it's becoming the left child of 4, right? So pivot is moving up, parent's coming down and becoming the new child, right? So just forget about 3 for a second. We've essentially discarded 3 and we said, okay, parent, now you're the pivot's left child. So pivot comes up, parent comes down. Great. Old left child becomes the new left child's new right child. Whew. Okay. Old left child becomes new left child's new right child. So what does that mean? 3 is coming over here and becoming 2's new right child. So old left child, that was the pivot's old left child, that was number 3, right? Becomes the new left child, which was the parent, right? 2. It's no longer the parent, but it was the parent. It's the new left child. It becomes its new right child. So kind of see that visualization, right? Pivot comes up, parent comes down. Old pivot's child is now what was the parent's child. The parent-child like vernacular starts to get really confusing, but the visualizations actually, like if you just like look at each image, it starts to make sense how that works. Okay, let's actually code it up and follow this pseudocode. So now that we can add users to our new red-black tree, we need to add the rotation functionality that will keep it balanced and fast. Okay, complete the rotate left method. Here we are. It takes a single node, pivot parent. So it's taking the pivot parent as input. This is important. So like in this visualization, it's actually taking like 2 as the input. Got it. And rotates the tree with its pivot node, which in this case is the right child. So we're doing a left rotation. So the pivot parent's right child is the pivot. Got it. All right. So if pivot parent equals self.nil, or pivot parent's right child is nil, we just return. Okay. So or pivot parent dot right equals self.nil, and we just return. Cool. So this is just there's just nothing to rotate in that case. It's like an invalid rotation. Let pivot be pivot parent's right child. So let's just do that. Pivot equals pivot parent dot right. Right? We're just following this visualization up here. That's the pivot. Okay. Next, set pivot parent's right child to be pivot's left child. So pivot parent's right child to be pivot's left child. So pivot parent dot right equals pivot dot left. Pivot parent dot right equals pivot dot left. Okay. Pivot parent dot right equals pivot dot left. So this is where we're setting 3, right? Because pivot parent dot right is pivot. And then pivot parent dot right needs to now be the pivot dot left, which is 3. So in this operation,
We're moving 3 up over to become the parent's right child. Cool. If pivot's left child isn't a nil leaf node, so if pivot.left is not self.nil, set pivot's left child's parent to pivot parent. So we're setting pivot's left child's parent. So, right, pivot's left child's parent to pivot parent, right? Which again makes sense because we're moving it over here. Moves in right there. Okay. Set pivot parent to pivot parent's parent. So pivot.parent equals pivot parent's parent. You can see how like not naming the variables accurately would get it's already confusing enough, but not naming the variables accurately would get really, really confusing. Okay. If pivot parent is the root, set the root to pivot. If pivot parent equals self.root, set the root to pivot. So again, if this was the root, pivot now needs to become the root. That only matters in the case that we're actually rotating around the root. You can, like, rotations happen all throughout the tree, but we do need to handle the case where we're pivoting around the root and we need to keep track of this root pointer. Otherwise, so we'll do elif if pivot parent is its parent's left child. So if pivot parent equals its parent's left child, set pivot parent's left child to pivot. Okay. Otherwise, pivot parent is its right child, is its parent's right child. Oh, wait. If pivot parent is its parent's right child, if pivot parent is its parent's right child, set pivot parent's parent to pivot. Wait, pivot parent, right child. Right. I was like, that's the same as this one. Okay. Okay, we got those. Oops. Set pivot's left child to be pivot parent. Set pivot's left child to be pivot parent. Pivot.left equals pivot parent. And then set pivot parent's parent to be pivot. Now, I'm going to pause here. You might be thinking, Lane, you didn't like just off the dome rattle off this algorithm. Why didn't you do that? And the answer is because I can't. There are people that can, for sure. You could grind enough leet code problems that you're like pretty good at red black trees. You could memorize this algorithm, right? My personal take on this is that it's not worth your time to memorize the algorithm. Probably. Like, it's 2025. I don't think you should be memorizing the algorithm. I do think you should code it from scratch, line by line, following some pseudocode, and you should be looking at the visualization and understanding what's going on. Because given enough time, right, you just let me stare at this visualization like, yeah, I can code it back up. It's a little harder. It's a lot easier to follow pseudocode than it is to follow the visualization. But the important part is to understand the visualization, understand what's happening, understand that there is a rotation, that this is how the tree stays balanced, and then to actually code it out by hand and debug it should you screw it up. That's the way I look at it. Other people might have different opinions. They might think that you really should like just look at the visualization, try to like do it from whole cloth. I don't think it's necessarily worth your time if your goal is to become, a software engineer. I think just doing the practice once and understanding the concept is good enough. Okay, so that's the rotate left. Now, what happens here? Are we screwing it up because of the rotate left? Let's see. Starting tree, rotating left, expecting tree, actual tree. Oh, okay. So it looks like it worked. Looks like our rotate left worked. Rotate right obviously isn't working because we have not done rotate right yet, I think. Wait, are those the same? Shipley, Williams, Mitch, 7. Yeah. Okay, so let's go ahead and code pivot right. or rotate right now. And it's gonna be, do I dare? Do I dare copy paste this and just change all the directions? Let's see. First of all, it needs to be called rotate right. All right. Left, basically anywhere where there's a right. Oh, this is gonna get dangerous. Here's what I'm gonna do. This is smart computer science things. I'm gonna call right temp for a second, and we're just gonna replace all the rights with temps, and then we're gonna replace all the lefts with rights. This will be cool if this just works, right? And then we're gonna replace all the temps lefts. Some good old swapping. Boom. Did we just nail it? Moving on. Okay, fix insert. So you probably noticed that all we did was implement the rotate left and rotate right functionality. And all that does is take a spot in the tree and say, hey, perform a rotation at this spot. The question is, when do we need to rotate the tree so that it stays balanced, right? The rotation folds in a longer branch back into the tree to keep it more balanced, but we need to know when and where to actually do the balancing. So now we're gonna fix our insert method so that it actually does it. Rotations are only useful if we can use them, right? When new nodes are inserted into the tree, they can break the red-black properties. We'll fix that by rotating the tree as new nodes are inserted, ensuring the tree remains balanced. When we're done here, we'll have a fully functional, albeit insert only, red-black tree. As you can see, if you look at the bottom of the test suite, we'll be inserting numbers into our tree in order. So if I just take a look at the tests here, where are the numbers? Where are the numbers? Where are my test cases? Okay, so 4 and 10. So it's just inserting the numbers for, where is it actually happening? Where is it actually happening? Print tree, insert, for user and users, tree.insert user, users equals get users, num users, right? So we're taking like the number 4 and the number 10 in here, and then we're calling get users, which I'm assuming just returns, let's get users in here. Yeah, it just returns a number of users. So they're all gonna get inserted in order, which is problematic for a normal tree, right? It would result in something like this. But our red-black tree will continuously rotate as things are inserted and stay balanced. Cool. In our implementation, we'll perform a normal insert, and then we'll call a fixed insert method that will recolor and re-rotate the tree as necessary. So, and I think does that happen in the insert method? Yeah. We're gonna write fix insert, and then we're just gonna automatically call it at the end of the insert method so that our users don't need to like explicitly call fix insert. It just happens, right? Our users of the RB tree class. All right, first, update the insert method. Got it. Call our new fix insert method with the new node. So self.fix insert. And we need to call it with the new node at the very end of what you've written so far, and it's just the new node that we just inserted. So calling fix insert, we're handing it, hey, this is the node that I just inserted. Cool. Complete the fix insert method. While the new node is not the root of the tree, and its parent is red. While new node does not equal self.root. It's actually probably written better as is not self.root, and its parent is red. And new node dot parent dot red. And its parent is red, right? Yeah. Let parent be the new node's grandparent. Let parent be the new node's, let parent be the new node's parent, new node.parent. So this will just make typing a little bit easier. And let grandparent be the new node's, actually the easier way to do this is just do parent.parent, right? Okay, if the parent is the grandparent's right child, so if the parent is the grandparent's dot right, then let uncle be the grandparent's left child. Uncle equals grandparent's dot left. Okay, you can see we're just really milking the parent-child relationship analogy. Okay, uncle equals grandparent dot left. If the uncle is red, change the uncle to black. Set the parent to black. Parent dot red. Set the parent to black. That's false. Set the grandparent to red. Update the new node to be a reference to the grandparent. Ooh. The new node is now reference to the grandparent. This will allow the loop to continue the recoloring process up the tree. So let's just like pause for a second, think about what we've just done. So what's happening here, right? This is like the important part, is that we're recoloring the different layers of the tree, right? And as you can see, we're setting the grandparent to red and then the uncle and the parent to black, right? So visualize that. The 2 levels up is now red, 1 level up, that layer is now black, both our direct parent and the uncle, which is our grandparent's other child, right? So we're recoloring kind of the 2 levels above us. Very good. Okay, otherwise if the uncle is black. So elif, uncle, elif, well actually let me just do else because there's really only options here. So otherwise the uncle is black. If the new node is its parent's left child. So if new node is parent dot left, update the new node to be referenced to its parent. New node equals parent. Rotate the tree right. Okay, so this is where we actually are doing a rotation now, right? So rotate the tree right with the new node as the pivot parent. So self, this is the tree, right? Rotate right. Passing in, let's go take a look at our rotate right method. Passing in the pivot parent, right? With the new node as the pivot parent. So the new node is the pivot parent, right? So the pivot's going to be like the child of the new node. Self.rotate right, new node. Okay, we got that. Rotate the tree right with the new node as the pivot parent. We got it. Set parent to be the new node's parent. All right. Now we got to set the parent to be black. Grandparent, oops. Now needs to be red. Rotate the tree left with the grandparent as the pivot parent. Yeah. So self dot rotate left with the grandparent as the pivot parent. Cool. Got all that done. Okay. Otherwise, if the parent is a left child. Whoa, wait, where are we here? So how deep am I nested? If the parent is the grandparent's right child, okay, we did that. So I actually need to come all the way out to there. One more. There we go. Otherwise, if the parent is a left child, if the parent is a left child, otherwise if the parent is a left child, if the parent is the grandparent's right child, right? So we need to say if parent equals, or if parent is grandparent dot left, right? The parent is a left child. Let uncle be the grandparent's right child. So we're basically redoing what we just did now for the other side. If parent is grandparent dot left, uncle, let uncle be the grandparent's right child, grandparent dot right. And then if uncle dot red, uncle dot red equals false, it's going to be black. Set the parent to black, parent dot red equals false. Set the grandparent to red, grandparent dot red is true. Update the new node to be a reference to grandparent. Okay, handled the coloring. Otherwise, if the uncle is black, else. If the new node is a right child, if new node is parent dot right, update the new node to be a reference to the parent. Rotate the tree, self.rotate left with the new node as the pivot parent. Set parent to be the new node's parent. Okay, set parent to black. I know somewhere in here I typed dot black, and that is hilarious. Okay, so this is supposed to be parent dot red equals false, and this is supposed to be grandparent dot red equals true, I think, right? Parent to black, grandparent to red. Down here, yeah, set parent to black, grandparent to red, rotate. Yep, right. Yep. Here we're setting
Parent to black, grandparent to red again, and then rotate the tree right. Rotate the tree right with grandparent as pivot parent. So self.rotate right, grandparent. Whew. Finally, very last thing we need to do, make sure I've got my correct level of indentation. When all the iteration is done, just set self.root.red to false. Whew! What are the chances we typed all that correctly? That's a lot of code. So, and again, I just want to kind of point out what's actually happening here, right? So we already inserted the node into the tree. Now we're fixing the insert, and this is the node that we just inserted. What are we doing? We're going and finding the references to the new node's parent and grandparent, which it already has, right? Because we already inserted it, so it has a parent and a grandparent. Here we're recoloring the layers, right? And then here we're actually doing the rotations. And again, this is just for the other side. We're recoloring the layers, then we're doing the rotations. See how we did. And we got it. Yay for pseudocode. Okay. Let's take a look at what we just did. Okay, is the tree displayed a valid red-black tree? Let's take a look at the rules again. Each node is either red or black. That's correct. The root is black. Yep. All nil leaf nodes are black. Yep. If a node is red, then both its children are black. Yep. All paths from a single node go through the same number of black nodes to reach any of its descendant nil nodes. One black node. One black node. None, 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 none. That all matches. Yeah. No! What did I miss? No black nodes, no black nodes, no black nodes, no black nodes. One black node. One black node. Black node. I'll pass for I'm guessing it breaks rule 5, but I want to know. Oh, what? Breaks rule 4. If a node is red, then both. Wait, if a node is red, both its children are black. There it is. Yeah. Silly me. All red nodes have to have a black child. So no, it breaks rule number 4. Cool. To be a valid red-black tree, a black node must have red children. No. Black node doesn't have to have red children, right? If a node is red, it has to have black children, but a black node does not have to have red children. False. Doesn't matter. Okay, let's talk about hash maps. Now, there's kind of a joke in like real life programming world that like if you need speed, what you want is a hash map like all the time. And there's a lot of truth to that. As I mentioned before, like red-black trees, binary trees, linked lists, these things do have use cases, especially binary trees. But when you're writing application code, right? So like when you're building web apps, it's unlikely that you'll need to kind of build your own implementation of a binary tree or linked list to get done what you need to get done. Unlikely, there's standard implementations, or even more likely, the technology, the library that you're using under the hood uses one of those things. So hash maps are similar in that, again, you probably won't need to implement one from scratch. And actually building a robust hash map can be fairly complex. But hash maps are like standard in every language. A dictionary in Python is a hash map, right? In Go, they're just called maps. In Ruby, they're just called hashes. It's key value pair mappings. So you already know what a dictionary is. Congratulations, you know what a hash map is. The hash map data structure is kind of what works under the hood to make sure that the lookups in the dictionary are fast. So when you look up, key Bob in a dictionary and you get back the value Ross, well, when there's 10 million items in that dictionary, what makes that lookup fast? Like, how does that actually work, right? It's not magic. There needs to be some sort of algorithm under the hood that's making that lookup fast. That's what a hash map is, okay? And then just worth mentioning, of course, they are order 1. When we look up values by key with a hash map, we are working with an order 1 algorithm. Okay, let's take a look at how this kind of works. So Hash maps are typically built on top of arrays, or in the case of the hash map we're about to build, which won't be the most robust hash map in the world, but it will work. We're going to build it on top of just a normal Python list. So hash maps are built on top of arrays or lists. And the way they work is they use a hash function to convert a hashable key, right? So in the case of like string keys, Bob, right, or Pablo, these are hashable keys, into an index in the array, which is an integer. So it's like essentially we're converting like Bob to say index 3, and then we're going to store its value, Ross, in index 3 in our backing array or in our backing list. Maybe Pablo maps to index 2, right? Maybe Leonardo maps to index 473, right? The idea is that we need some function that maps the key string, in the case of strings, it could technically be other types of values, but let's just assume strings for a second, to an integer, and then we can use that integer as an index in the array. Okay, that's what the hash function does. Okay. So from a high level, all that matters to us is that the hash function takes a key and returns an integer. Great. It always returns the same integer for the same key, right? So if I pass in Bob to my hash function, I should always get the same index, right? Index 3, index 3, index 3, index 3. That way I'm always able to go get the right value that's stored in that index. And it always returns a valid index in the array. So it should never return a negative number, and it shouldn't return a number that's larger than the size of my array or the size of my list. Right? Okay, so to store value Ross at key Bob in our hash map, first we run the hash function, we give it Bob, and it returns us the number 3. And then we insert the value Ross at index 3. Boom, right there, right? And then later when we need to get that value back out, we just run our hash function again on the key. It gives us the index 3 again, and then we can go grab the value back out of index 3 in the backing array. Cool. That's the basic idea behind hash maps. So hash maps use blank under the hood. They use arrays or Python lists. What's the big O complexity to iterate over all the keys and values in a hash map? And this is a trick question, right? So getting and retrieving items from a hash map by key is order 1, but iterating over all the keys and values in a hash map can't be less than order n, right? Because we have to iterate over everything. Okay, hash maps can, in most cases, map blank keys to blank values. Hashable keys to any values. So the only restriction on a key typically is that it's hashable. So we need some way, our hash function needs to be smart enough to convert that key that it's given to an index and to do it consistently. And hashable is kind of defined by the implementation of the hash map. You could build a hash map that only works with strings as keys. You could build a hash map that works with strings and numbers, one that even takes objects. Like there's different ways that you could build it. Hash function. Let's build a toy hash map in Python. Heck yeah. As it turns out, the binary search tree was overkill for profile lookups on the Locked-In website. We don't need any of the fancy order traversal or range queries after all. And because Locked-In is such a business failure, we can store every user in memory. So this is a very important point that there are hash maps that work on disk and things like that. But one thing when you're doing optimization within your program and you're trying to just do order 1 lookups with a map, just one thing to consider is that when you're going to use an in-memory map, you do have to actually store all the stuff in memory, right? Whereas if you were using an actual database like a MySQL or a Postgres, that stuff gets written to disk and isn't going to take up all the memory of your application server itself. So maps are really great, but you just do need to kind of keep an eye on how much memory you're using. Okay, complete the hash map's key to index method. So this is our hash function, right? It takes a key, which is in our case always going to be a string as input. Add the Unicode values of all the characters in the string using Python's ORD function. Okay, let's look at the ORD function. Given a string representation of one Unicode character, return an integer representing the Unicode point of that character. For example, ORD A returns 97. Okay, cool. So I just give it a character, gives me back a number. Very good. So we want to add all the Unicode values of the characters up together. So let's do sum equals 0 for character in key. Sum plus equals ORD of the character. Okay, so now we've got a sum.
Now we're going to mod the sum by the size of the hash map. So what's the size of the hash map? Well, we've got self.hashmap, which looks like it's just an array, right? None for I in range size. Yeah. So this is like fancy Python syntax to just say, give me an array of size and fill it with nuns. So we need to make sure the reason we're modding, right? So the modulo operator is like divide by a number and give me the remainder. So we want to do mod the sum by the size. So sum mod self length self.hashmap, right? So we're going to divide, wait, is that what we want? Yeah, that's what we want. So let's just say that our sum is like 500 and the length of our hash map is 400. What the mod's going to do is divide 500 by 400, which is 1, and give us the remainder, which is 100. So it ensures that that remainder will always be between 0 and the length of the hash map, which is exactly what we want, right? We want our index to always be between 0 and the length of the hash map. So sum mod length hash map. Cool. And that's just the index, and we'll return that. And I think we got it. Okay, insert. Now that we have some building blocks for our hash map, we need a way to start inserting values. So all we did was build our hash function. Now we need to actually like put stuff into the backing array. Complete the insert method. It takes a key, which is a string, and a value that can be of any type, and stores them in the map as a tuple. Okay, so we need to use our key to index method under the hood so that our users don't have to. So our user will just like call, they'll call something like hm.insert like Bob Ross. That's all they're going to do. And under the hood, we need to do the whole hash map and store in the array for them, right? And then they're going to do like hm.get or something Bob, and they're going to expect to get back, they're going to expect to get back Ross in the name value. Here. Okay. So first thing to do is get an index. So I equals self dot key to index key. Now this is kind of interesting to note. You'll notice that our key to index function actually didn't even use the self. Oh no, it did. It did. Sorry, I'm being dumb. I'm like, it didn't even use our self at all, but it totally did. So it does need to be a method. We could have written this as a function outside of the class that like as one of its parameters takes the size of the map, right? But anyways, that doesn't matter. Okay, we got our index that we need to insert into, and it said to insert it as a tuple. So now we just do self.hashmap, which remember is just an array, so we can use square brackets. Self.hashmap at I equals value. Nope. We need to actually store as a tuple, key value. So you're wondering maybe, why do we do this, right? We don't actually need to store the key here. We could just store the value. The reason we're storing the key, I believe, is that so when we print the map, so we probably have like some repr here. Yeah. So we have some representation here. And when we enumerate over all the values in the map, we want to be able to print the keys back out. So that's why we're storing the keys in their string form. So that when someone iterates over, imagine iterating over a dictionary in Python, right? You want to be able to iterate over the key value pairs. You want to know what the keys are as well. So that's why we're actually storing the key alongside the value in the index. That should be all we need. All right, time to get. Complete the get method. It takes a key and returns the value stored at the location. This is going to be really similar, right? I equals self.key to index key. And then we just return self.hashmap, which is an array at index I. This is interesting. We got one little kind of extra bit of logic here. If the value doesn't exist at that index, raise an exception. Okay, so this might be none, right? If nothing has been put into that location yet. Because remember, our backing list is of a given size. Like it could have like 128 kind of buckets in it, but it's not full yet, right? It's just like 128 buckets where each bucket has none in it. What we want to do here is if the thing is missing, we don't just want to return none, which is what this would do. We want to actually raise an exception. So let's just grab the val equals self.hashmaps.i. If val is none, raise, well, we can just copy this, raise that exception. Otherwise, just return the val. Oh no, what did I screw up? Okay, Hashmaps, size 512. Inserted Ricky. Inserted Shelly. Get Ricky, fail. What did I screw up? Expected Ricky ID 1, actual Ricky. Oh, I forgot. This isn't the val, right? This is a tuple. So what we really need is, I'll just call this tup so that I remember. And if tup is none, that's fine, but we need to actually return tup at 1, right? Because tup at 0 is the key, tup at 1 is the value. That's why we're getting these tuples here instead of what we actually wanted, which is I think it's a user object. Okay, let's try that. Very good. Okay, now let's take a look at this review. So hash maps are really cool. Like I said at the beginning of the chapter, this is why like every language comes with one. Like Python dictionary is a hash map, right? Just use a hash map when you can. It actually is like, you're going to use it all the time. Lists and hash maps. Like this is what application code is usually built out of. In Python, that's dictionaries. In Go, it's maps. In JavaScript, it can be object literals or just like the built-in map type, which is a fairly new thing, but works really well. Okay, let's talk about what makes a hash map good, because we kind of built a toy hash map that like you wouldn't use in production. There's better maps already built into your language, but it's really good to build a toy hash map so you can kind of understand what's happening under the hood. Okay, so a good hash map has fast lookups, right? Should be order 1 for lookups, insertions, and deletions. Great, we actually did achieve that, so good for us. Unordered hash maps. Typically, there are such things as like ordered maps, but typically they don't have any particular order to their keys. And, you know, if you add ordering on top of it, that's like a new data structure altogether. You've added like additional logic and complexity. No ranging. So while hash maps are great for like retrieving a specific thing from a specific key, they don't have a way to look at like a range of keys, right? So like give me the top 10 or give me the last 10. They're not good for that. It's literally just key value pairs. So you need an exact key. Collision resistant. So this is a problem that our hash map definitely has, our toy hash map. What collision resistant means is that no two keys should map to the same bucket in the backing array. So like imagine we have the key Bob and we have the key John, those two different strings. Well, if we're just summing up their Unicode values and then like doing a mod, there's a pretty good chance that those two strings will actually map to the exact same bucket, the exact same index in the backing array, especially if you have a super small backing array. Imagine you have a backing array that only has like 5 entries in it, right? When you mod by 5, there's a 1 in 5 chance that those two strings are going to collide into the same bucket. So a good hash map has ways to handle these collisions when they come up. And there's a lot of strategies. We're not going to go into all the strategies in this course, but there are strategies to where like, first of all, you make it so that the collision's unlikely, but then when a collision actually does happen, you can kind of like hop around. You can do like these second order things to make sure that there actually is space in the backing array for the new thing. Because in practice, like a Python dictionary or a Go map should never have collisions at all. If I'm using 2 different keys, I should never have a collision where they're overwriting each other, right? That just doesn't happen in a good implementation. But like I said, it's fairly complex to make that happen, or at least it's complex enough that we're not going to cover it in this course. Just know that those algorithms are like solved to some degree, and there's really good solutions out there. Okay, efficient resizing, right? So I can't remember how the solution code was implemented in the assignment that we did because we didn't write this code. But like if you just start your hash map out at a size of like, 1024 items in it, and then you only use 4 items, like that's not very efficient. You probably want to start out your hash map with just like a few buckets. I don't know, 8 buckets, 16 buckets, 32, some smaller number. And then as your hash map starts to fill up, you start growing that backing array, right? Making the backing array larger and larger and larger to make sure that you never run out of room for new keys. For new key value pairs. And then uniform distribution, again, this kind of has to do with, minimizing the number of collisions and then also just optimizing speed of the overall hash map. So our toy hash map has this hash function, and this is a very naive hash function. All it really does is guarantee that the key is going to be between 0 and the length of the map. Doesn't handle anything with collisions or whatever. Okay. What happens in our toy hash map if A, B, and BA are both used as keys, right? So think about this algorithm that we wrote. We're summing the Unicode representation of each character. So A, B, and BA, those are different strings, but they are guaranteed to collide because if A is 5 and B is 10, then we sum this, we get 15. We sum this, we get 15. It'll map to the same I. It'll map to the same index. So we're definitely going to get a collision. Okay, which is a major drawback of our hash map as opposed to a more robust implementation? Basic insert and get operations are slower than order 1. That's not true. We had order 1. We did that. It isn't ordered and doesn't support range lookups. So it isn't orders and it doesn't support range lookups, but neither do most hash map implementations. So that's fine. It allocates a large list in memory even when we haven't filled all the indexes. That is true. We were just kind of naively making, 1,000 buckets or however many we decided to at initialization time. Let's talk about tries. Tries are actually one of my favorite data structures. Not every data structures and algorithms course in university is even going to cover tries. In fact, mine didn't. But I really like them. And I think part of the reason I like them is that I've actually used them in the real world. Like I actually have built tries from scratch that went on to be used in production code. In fact, even one of my interviews for a job that I went on to work at, the problem that they gave me in the interview was most efficiently solved with a try. So they're pretty cool and they're really useful for text processing. So if you work anywhere close to like AI, sentiment analysis, text processing, there's a decent chance that tries will be useful. Okay, so what is a try? From a high level, you can think about it as kind of like a set of strings, right? So you've got your traditional Python set where it holds unique values, right? A try is a set of strings. So it holds unique strings, like for example, hello, help, hi, right? They're not stored in order, right? So you don't think about it as like, oh, hello comes before help, comes before hi. No, they're just in the try. That's why I say kind of think about it as like an unordered set. But the interesting thing about a try is that it stores these words on a character by character basis like this. You can see it here in this visualization. And what that does is it allows us to look up which words are in the try by prefix, right? So for example, you could query into this try, instead of just saying like, hey, does the string hello exist? We can do that. But what you can also do is say, hey, what strings exist that begin with the word HEL, right? Are there any words that begin with HEL, right? Are there any words that begin with H at all? So like I could say, what words begin with HEL? And it would go, oh, okay, we've got the word hello and we've got the word help, right? So it's very much a kind of prefix matching engine. Okay, so and then what do these different symbols mean? Okay, so at the top level of the try, we essentially have all the different like first letters stored in the try. And in this case, because we're only storing these 3 strings, hello, help, and hi, the top level, right? So these are all just nested Python dictionaries. If I didn't say that before, sorry, I probably should have said that earlier. These are all nested Python dictionaries. The first level, we only have one key, H, and it maps to kind of the next level of the try. And the reason it's just H is because all of our words start with H, right? So the second level, we have all the second letters in the words, right? So HE and HI, right? So now we've got 2 keys because we have 2 words that start with HE. And so their following letters are deeply nested under the HE keys. And then HI has its own kind of branch of the tree. What's this asterisk, right? We're going to choose to use asterisks that map to the Boolean value true just to signify, hey, a word ended here, right? So for example, HELLO obviously spells hello, and hello is in the try. But HELL is a valid English word, right? Hell. But we don't have an asterisk at this level. And so what that tells us is the word hell was never explicitly stored in this try, right? So you can kind of count up the number of asterisks to see like overall how many words are actually stored in this try. So let's go ahead and start building this thing. Hopefully that makes sense. Basically nested dictionaries representing all the letters in the try. Sorry, I guess I should mention one more thing. Tries can kind of be, in a weird way, memory efficient. That doesn't always end up being true in practicality because, dictionaries and references can take up a decent amount of memory. And so it does kind of depend on like the patterns of words that you're storing. But like, for example, storing hello and help, technically like the H, E, and L are all reused because, they match the same prefix. So if you have like a lot of very similar words, there could maybe be some space savings there. That said, if we're working with, even like all the words in the English language is only like, 40,000 of them. So it's actually like, I don't know. I'm probably mentioning something that doesn't matter. So forget I said it. Forget I said anything about saving memory. All right, we're going to use a try to add prefix searching to locked in. For example, a user will be able to type dev into a job search bar and see autocomplete suggestions, developer, development, DevOps, right? You can see how this could be useful. Autocomplete suggestions are everywhere. They're in all sorts of apps. And so what is essentially happening here is we're saying, okay, there's certain things that we know that people search for on locked in, like commonly searched terms. We're going to store those in the try. And then when a user types, we can walk down the try using the prefix that they've given us and kind of narrow the search results to whatever is coming up, right, in the try. Cool. Complete the add method. It takes a word as input and should add it to the try. Okay. Assign the root dictionary of the try to a temporary variable current. All right, so let's take a look at our constructor. It looks like, so the root of the try is just a dictionary, and it's going to be a dictionary that stores other dictionaries, right, with either a letter or an asterisk as the key. And it looks like we've kind of got this end symbol here, so we don't have to like kind of use magic asterisks everywhere. Okay, assign the root dictionary of the try to a temporary variable current. Okay, so current equals self.root. So this is like the current level. In fact, I'm going to be even more explicit and say current level. Okay. Loop over each character in the word passed to the add method, right? So for C in word, so we're going to walk over essentially the prefix that we've been given. If the character is not a key in the current dictionary, add it and assign a new empty dictionary to it, right? So if C not, I think we can just do not in for dictionaries. C not in current level, then current level at C equals empty dictionary. So we're saying, okay, we were given the prefix dev, for example. Well, actually, that's a bad analogy. Let's say we were given the word, right? Because we're adding a word to the try, DevOps, right? So we're going to start with D. Okay, D, is it in the root of the try? No, it's not. Great. We need to add a D. And then we need to move to the next level, right? Update the current dictionary to point to the child dictionary corresponding to the character in the loop, right? So now current level needs to equal current level at C. Okay. Once you've ensured all the dictionaries exist, add the self.end symbol to the dictionary of the last character in the word, right? So if it's not in the current level, so again, let's take the example of DevOps. We have an empty dictionary. We look at the first level of our try, right? To use our visualization up here, we're looking at this very top level. Does it have a D yet, right? It doesn't? Great. Add D, give it a new empty dictionary, and move into that dictionary. Cool, right? Because we're reassigning current level into that nested dictionary, right? Now we're at the second level. And we're on to the second letter, which is E, right? See if there's an E there. Rinse and repeat until we get to the end of the word, right? If C is in the current level, right? If there is already a D at the top level, what do we need to do? Well, we don't need to create a new empty dictionary, but we do still need to enter that dictionary. So I actually need to dedent here. All this does is say, if it's not there yet, add it, create an empty dictionary, and then no matter what, we need to move into it. Cool. All right, last step. Once you've ensured all the dictionaries exist, add the self.end symbol to the dictionary of the last character in the word. Okay, so current level should be the level of the last letter, which means we just now need to add an asterisk, right? So current level at self dot end symbol equals true. And this just says, hey, a word ended here. Cool, let's run that. Looks like we got it. All right, exists. So we just wrote the logic to insert new words into the try. Great. So now we need to complete this method that takes a word and just checks, does this word exist in the try? And we'll probably talk about big O in a second, but looking up whether or not something exists in a try, it's tempting to think that's ON, and you'll see why, because there's a loop in it. But if N is the number of things in the try, it's not order N. If you define N as the length of the word, then yes, it is order N. But like realistically, what you're probably thinking about is either the number of words in the try or the number of words that you have to check against the try, in which case it's basically constant time, right? Because like the average length of word is just always going to be like, 5 or 6. So 5 or 6 characters. So we'll talk more about that later. Okay, complete the exist method. Takes a word as input and returns true or false based on if it's in the try. Okay, starting with the root of the try, assign the current dictionary to a variable, right? So we need to start with current, set it equal to self.root again, right? Because we're going to start walking from the first level of the try. Loop over the letters in the word again, for C in word. This is looking very similar to what we did last time. If the current letter is not in the current dictionary, just return false, right? Super simple. If we're looking for the word DevOps, and at the first level, we don't have a D, then DevOps is not in the try. Okay, so if C not in current, just return false, we're done. Right? Otherwise, we have to move current down to current at C, right? So we're gonna move the dictionary down one level and try again. Once you get to the last letter, so once there's no more letters in the word that we're checking for, right? So let's take the example of, let's say we're looking for the word dev. And inside the try, there is the word developer. So we go DEV, great. Now we're on that last layer of the try, or I should say we're at that layer where the V is. If the word dev is in the try, there actually needs to be an asterisk at this level. Right? If not, then we can assume that the word developers is in the try or some other word that starts with DEV, but not DEV itself. So we need to explicitly check for the asterisk. So we could actually probably just return a self.end symbol in current, right? If the self.end, can I spell symbol? If the self.end symbol is in the current level of the dictionary, that means this word exists in the try. If it's not, it doesn't exist. We're just at some prefix. Got it. Okay, prefix matching. So up till now, our try probably just kind of feels like a weird hash map, right? Like we're just going to all this trouble to split up the letters, and all we can do is insert stuff into it and check if stuff exists. Like, great, we could have done that with a hash map. But the reason, or I should say one of the reasons that hash maps are so useful is that you can do prefix matching, right? You can look up whether or not, there's a list of words that match a certain prefix, right? In this example, there's 2 words that match the prefix HEL, right? Help and hello. Cool. So hash maps can be used for suffix matching, prefix matching, exact matching, all of these. It's tempting to just say prefix matching, but we know that it can be exact matching. So the question is like, okay, wait, hold on. How could it be suffix matching? It's like, hash maps. Sorry, we're talking about hash maps. I was thinking about tries. Hash maps can only be used for exact matching. They can't do anything else. But just to finish my train of thought, you could use a try for suffix matching, but then that try would only be useful for suffix matching, right? You just have to insert everything in reverse. Checking whether or not a word exists in a try is an order M operation where M is, okay, so I talked about this a little bit earlier. Tries are not really order N, even though there's a loop in there, because N, you typically would not define that as the number of letters in the average word, but that is the length of that iteration loop. And so it's if you define N as the number of letters, the average number of letters in the words, sure, it's order n, but that's not a very useful way to think about it, because the better way to think about it is probably where n is the number of words in the try, right? Because that's how we think about it with like binary trees and linked lists and everything else. It's probably using order m here to kind of really drive that point home, that you have to think about what n or m could be. Let's just read the answer. So the number of words in the try, we know it's not that. It couldn't be order m, where m is number of words in the try, because you can add lots and lots of words to a try and it's still super, super fast, right? It's still going to take like 5 steps to get to the word you want. The number of pointers in memory, again, no. You're going to ignore most of the pointers, right? You just go down one branch of the try. It's actually going to be the length of the word, which again, like, yes, that is technically a variable. Like the average length of the word does matter. And like, maybe they're not English words. Maybe they are like super long words, in which case, yes, it is like, you do have to think about that big O. But like, if you're doing what I did at my job with tries, which is like, you're doing standard English words, then the average length of a word is like 5 characters and it just doesn't change. So you can basically think about it as constant time. Okay. Words with prefix. So in a try, hello, help, and hi be represented as this. Yes, we went over that. Complete the search level function. This recursive function collects all complete words starting from the current try level. Okay, cool. So this is where we're actually going to get all of the words. We're actually going to get all of the words that start with a specific prefix. We're going to get those out of the try. So search level function. First, we need to check for complete words. If the current level contains an end marker, add the current prefix to the words collection. Okay, so we need some sort of like variable to keep track of the words. So words equals, let's just do, oh, we're given it. Okay. Wait, am I starting with the right one? Yeah, search level. Okay, so we're given a list of words. If current level contains an end marker. So what we should actually do is if self.end underscore symbol in current level, add the current prefix to the word collection. So search level is being called by our words with prefix function. So we're essentially building a helper function right now. So search level is only called at a specific level in the try and with a specific prefix. And our job is to say, okay, at this level with this prefix, these words are here. So if there's an end symbol in the current level, we need to add the current prefix to the words. So words.append current prefix. Cool. Next, process each character in the current level in sorted order. So for sorted, I think I can do this. The current level, so it would be something like current level dot keys for sorted current level. Okay, so C in. So current level dot keys should give me back all the keys in the current level, so all the letters, right? And then sorted is going to give them to me in sorted order. Then I'm going to iterate over them. Okay, extend the prefix with the current character. So new prefix equals current prefix plus C. Okay, so we're like going down into all the different next levels. Recursively search the child level with the extended prefix. Okay, so I don't think I need to return anything here because all we're doing is like, we're just making changes to this list. So self.search level, we need to send in the next level, right? So it would be current level at C, would be the next level. We need to send in the next, or the new prefix, and then the same words array. Return all words found. Oh, okay, so we do return the words. And so I'll capture that here. Okay, that looks right. Now we need to complete the actual words with prefix function. So this is basically the helper function, right? That handles like each level in the try. Words with prefix function. This finds all words in the try that begin with the given prefix. So initialize an empty collection to store matching words. Cool. List. Keep track of the current try level, starting at the root. Okay, so the current level equals self.root. Iterate through each character in the prefix. Yeah, we've been here before. For C in prefix. If the character doesn't exist in the current level, return an empty list. No words start with this prefix, right? So that makes sense. If we like at any point hit an empty level, we're just done. So for C in prefix, if C not in current level, return empty list. Otherwise, current level equals current level at C. So this is going to walk us down the try until we get to the end of the prefix, right? So again, imagine a try with like developers, DevOps, like they're all in there, and we're looking for words with prefix dev. This is just gonna walk us down to DEV, and then by the end of our loop here, we'll be at the level of that last character in the prefix. Cool. But now the current level should be the last character in the prefix. Call the search level function to find all words starting from this level and return them. Cool. So we just return self.search level, and we need to provide it the current level. We need to provide it the current prefix, which is just the full prefix, right? And we need to provide it our list of words, which in fact, we don't even use the words array way up here. It's kind of confusing, so I'm just going to put this down here, and we'll just pass that bad boy in. Now you might be thinking, whoa, what's the point of just like initializing an empty array and then passing it in? And in fact, we could just do this. But again, you might be thinking like, why even do this? Well, we do need to pass it in for these recursive calls. So just on the first one, we're going to start with an empty list. And then after that, at each level of recursion, it'll keep building on top of it. Because remember, this one's the recursive function. This one's not. Okay, let's run that. And I failed. What did I screw up? Let's look at some of these. So in this try, we've got the word designer in there. We've got DevOps, looks like. We've got director, a bunch of stuff. And we want words with prefix DE, expecting dev, DevOps, designer. Argument of type bool is not iterable. Cool. Argument of type bool is not iterable. Where did I screw up my syntax? So what am I iterating over that could be a bool? Or C in sorted current level dot keys. Am I doing my keys wrong? Argument of type bool is not iterable. Prefix should be a string, which is iterable. So this is the only other one that's not iterable. So sorted, for C in sorted. Let's do this. Let's print current level dot keys. I might be screwing up my stuff. No, yeah, we get dict keys. Very good. What happens if I print the sorted ones? And that. Yeah, okay, it's sorting them. That's reasonable. An argument of type bool is not iterable. Here I'm passing in a new letter. I'm passing in, first of all, I should be able to spell prefix. Okay, so that seems reasonable. So for C in sorted. So that one should be working, right? What if I just print C? Yeah, seems reasonable. Why am I returning a Boolean? What is evaluating to a Boolean context here? EO star. So that's my try. What was my prefix is just C. Okay, so my prefix comes in as C. That's happening. I'm finding my current level, which is the first letter. And then I'm iterating from C in sorted current level dot keys, which apparently was, well, no, that is interesting. Why is it EO star? That would be CEO. So it's doing the first word, in this case, CEO. And then it's failing, right? Because it should be iterating over all of these words. The keys at C, right? Well, let's do this. Because current level, so it starts off C maps to T, C maps to F, C maps to E. That looks good. And it looks like we go into E, then we go into O, and then we go into, I'm so silly. Okay, so the problem here is that when we finally get to the end, right? When we finally get to the end, we've got a true here. So we need to handle that case where we get to the end and it's no longer, like current level is now a Boolean value. It's true. It's no longer a dictionary. Okay, so let's fix that. We want to come in here and basically add a base case, right? So if self.end symbol in current level, well, but just because we reach the end doesn't mean we don't have to keep going back further. So it needs to be up here. It needs to be something like if current level, is it instance of? I'm getting my JavaScript and my Python mixed up. We want to know if current level is true, I think is the best way to do that. Then we just want to return words. right? Because in the previous iteration, we would have appended the current prefix, self.end symbol, in current level. We could also catch it here. I think we just want this. Let's run that and see what happens. Okay, yeah. I think that's all we needed. Cool. All right, find matches. So tries are super efficient when it comes to finding substrings in a large document of text. So for locked in, we want to be able to find all the instances of bad words in chat messages and filter them out. All right. Complete the find messages method. It takes an entire document. So now we're going to actually use the try, right? We're going to accept a document. Like in the case of my old job, this would be like a full tweet or something, or like a blog post. And then we're going to match that document against the try, which is super fun. It takes an entire document strings input and should return a set of all the words, this is just a standard Python set, of all the words from the try that occur in the document. Cool. So we're going to iterate over all the words in the document, and we're going to run them against the try to see if that word exists in the try. Cool. So matches is a new set. Loop over all the indexes of the characters in the document. Oh, that's interesting. Loop over all the indexes of the characters in the document. Okay, I'll just take your word for it. So for I in range length of document, do 0 to range length of document. Create a temporary level variable to hold the current level, a dictionary, and initialize it to the root of the try. Interesting. Okay, level equals self.root. Use a nested loop to iterate over all the indexes of characters in the document. Use a nested loop to iterate over all the indexes of characters in the document. So we're doing that again. Okay, so something like for j in range 0 to length of document. But start at the current index of the outer loop. Okay, start at I. Okay. So we've got our starting character I, and then we're going to do an inner loop and start from I. Okay. I don't need to do this. If the inner character is not in the level dictionary, break out of the inner loop. If the inner character is not in the level dictionary, break out of the inner loop, right? So if this would be document at j, the inner character, is not in level, then we break. Otherwise, set level to the dictionary for the current inner character. Dictionary for the current inner character. Okay, so level equals level at. Now, just one thing I'll point out here. Remember, we're doing find matches, so the assumption here is that self.root is already a full try. Like in the past, we've been building the try, now we're not building the try anymore. It already has stuff in it, right? Okay, so level equals level at document at j. So document at j is the actual character, right? So let me do that. Let's do c equals document at j. So if c is not in level, break. Otherwise, level equals level at c. Right? So this is okay, if j is in the current level of the try, then move one layer down the try, right? Otherwise, get the hell out. This isn't a match. Okay. If the inner character's level contains the end symbol, add the word to the matches set, right? So if the inner character's level, if self.end symbol in level, add the words to the matches set. So matches.add C. You can calculate the word by slicing the document using the indexes of the outer and inner loops. Oh, right, we're adding the word, not the character. So we need to do document from I to J, right? Do we need to do, J would be exclusive, so we need to do +1. Okay, so it's just and then of course we'd return matches here. So let's just rethink through this really quickly. So we're gonna iterate over every character in the document. At every character, we're going to look at our trie, right? And we're going to reset ourselves to the we're going to reset ourselves to the top of the trie. That's the right way to think about this. Then we're going to begin iterating from the character that we're on, right? Begin iterating from the character that we're on, and we're going to move down through the trie. And we're going to keep going until either the word that we're on is not in the trie, in which case we'll break out and move on to the next top level letter. Or we'll eventually hit an end symbol and then add that word in the document to the trie. The cool thing about this is you may have noticed, we're not doing like the naive thing of splitting on white space and then like checking against a hash map. That would be like the simpler thing to do, but this is kind of cool because it'll actually find matches that contain white space. You could like search for a phrase here, not just a word, right? You could actually search for a full phrase that has spaces in it and it would still work, which is pretty cool. Invalid syntax. What did I break? If C not in level. I don't know why I wrote that is. Ooh, did we get it first try? Let's go. Okay, find matches review. Let's review the code that we just wrote. What's the big O complexity of the find matches method? Okay, this is interesting. So we have some nested for loops here. Might be really tempting to look at this and go, oh, it's order n squared, right? But I don't think this is order n squared. Because we're not just like looping over the length of the document twice with no breaks. We are breaking out early and we're actually breaking out very, very often. Okay, so not n squared. Let's think about like when and how we're breaking out. First of all, this one has no breaks. So we are looping over the entire document at least once. So it is going to be at least order n, where n is the length of the document. We know we're at least like maybe here or here. All right. We're not here because we can't be order log n, that'd be too fast. And we're not here, that'd be too slow because we're breaking out of this second loop. So order nm, where n is the length of the document, that sounds good. And m is the depth of the trie. That sounds right, right? Because if we ever get to the end of the trie, we're done, right? We're also done even sooner than that if the word happens to not be in the trie. But like in the worst case, we're basically getting to the end of the trie. Okay. And this might be more correct to say like an m is the average depth of the trie or something like that. But okay. And then order n log n, where n is the length of the document. Would it be the log of the length of the document? No. This loop, even though it technically goes to the end of the document, if like nothing goes wrong or nothing goes right, however you want to think about it, it's not ever going to be the log of that. The length of the document doesn't matter for how deep we're going. What matters is the depth of the trie. So it's going to be this one. Okay, why don't we just use a simple dictionary lookup to find out if substrings are in the document, right? So this is kind of what I alluded to as we were building it, which is like, well, we could take the document, split on white space, have our list of words in a hash map, and then like iterate over all the words, check if they're in the hash map, or check if they're in the set, right? That would work. But it won't work on substrings that are smaller than the space of a word, and it won't work on phrases that are bigger than one word, right? The really cool thing about what we built is that it'll match phrases, it'll match substrings, right? So like this will work for like building a control F functionality, right? Where there's partial matches on words or there's matches on multiple words. Pretty cool. Something that you just wouldn't get from a hash map. Okay. Because we would need to check every substring in the document, right? And storing every substring in a hash map would be insane. So yeah, it's not that. Think about every permutation that you'd need to store in the hash map. Because dictionaries don't use hash maps under the hood, that's not true. And because dictionaries are too slow when it comes to exact match searching, that's not true. So and we're on to graphs. Time for graphs. Okay, cool. Graphs are awesome. Graphs are a little bit more, I like to think about them as they're a little more unstructured, or I should say they're a little less structured than like the trees and the tries that we've been working with. If you take a tree and you allow the nodes to also connect to multiple parents, like now you have a graph. right? So a graph, it's a set of vertices connected by edges. But importantly, not all the vertices have to connect to all the edges, right? In fact, that's an important data point about a specific graph is like which vertices connect to which edges, right? A very common reason to use a graph would be like if you're trying to model roads in a city. So you can think about all the different vertices as like buildings within the city. And then the roads are, okay, which roads connect which buildings to each other, right? Google Maps, I'm sure, uses plenty of graph data structures under the hood. Okay, so there's a couple different ways that you can model a graph in the memory of your program. And we're going to start with what's called a matrix, right? So take this example here of this table, and the x-axis here and the y-axis here represent the vertices, right? So 0, 1, 2, 3, 4. And the true false booleans represent whether or not there is an edge that connects those two vertices, right? So in this case, 0 and 1, there is an edge. So at 0, 1, the node at 0, 1 contains a true to say, hey, there is an edge between these two vertices, right? Between 0 and 0, that doesn't even make sense. So you'll notice there's a false there, right? 1 and 1 doesn't make sense. 2 and 2 doesn't make sense. There's a false there. And then the interesting thing about modeling it this way is we have to also make sure the reverse is true. So if 0, 1 is true, right? Because there's an edge there, we just also have to make sure that we mark 1, 0 as true because the edges are bidirectional in this graph. There's no directionality to the edge. And so just, as a result of modeling it this way, we kind of have duplicate data within our graph. So anyways, that's how it works. And then in Python, the way that we're going to model this is just with a list of lists containing Booleans, right? So this list of lists is how we're going to represent this graph in our program. Locked in, like all social networks, has a social graph, right? Social networks are also a very common use case for a graph. Think of all the vertices as users, and the edges, right, can be whether or not those users are friends in the social network. Okay, cool. We want to represent this graph as a matrix. Our users each have a unique ID, which is an integer that we'll use for their vertex number, right? So just to keep things simple, we're going to use user IDs are integers. That's how we're going to represent our graph. All right, complete the init method. Create a data member called graph. It should be an empty list. All right, self.graph is an empty list. Fill the graph with n lists, where n is the number of vertices in the graph. All right, so we're given the number of vertices here as a parameter to our constructor. So, for example, we want to make this graph up here. We're going to have the number 5 as num vertices, and we basically need to build out this, right? Okay. So for I in range num vertices, we'll do self.graph.append empty list, right? Fill the graph with n lists where n is the number of vertices in the graph. Each of these lists should contain n false values. Okay, so then what we need to do is make a little nested loop. Well, one way we could do this is make a little nested loop. Let's call it nested. Is an empty list. And then for j in range num vertices, nested.append false, because we're just filling out the graph with all falses. So we're just making the vertices right now. The way we'll create the edges is by flipping some of these Booleans from false to true. A nested.append false, and then we'll just append that nested list into the overall graph. So now we have this two-dimensional list. Okay. Complete the add edge method. It takes 2 vertices as input, u and v. It adds an edge to the graph by setting the corresponding cells to true. Okay, cool. So this is saying, okay, got it. So the user of our graph is going to call this when they want to say, like, hey, look, there's an edge between 0 and 1. They're going to pass in 0 and 1, right? Okay, so how can we do that? Well, I think we can do self.graph at u at v equals true. And then self.graph at v at u equals true. That should take care of it. There's probably a couple edge cases we want to think through though, right? For example, what happens if the user of our graph passes us a number that's out of bounds of the list, right? So we probably want some guard clauses in here. Things like, if u is less than 0 or v is less than 0, let's just return and do nothing. I'm guessing that's we could raise an exception, but I think the right call in this case at least is just to bail. And then similarly, if u is greater than the length of, oh wait, hold on. Let me think for a second. Well, no, it should always, the length of self.graph, because we have control of the constructor here, should always be the same as the length of the nested list, right? So we should just be able to say if u is greater than the length of self.graph or v is greater than the length of self.graph, again, just return. Cool. So by this point, as long as no one's done anything malicious with our graph, both of these should be within the bounds of their respective lists. And what did I screw up? For I in range, num vertices. For I in range. I've lost connection to the server. Oh no. Let's refresh. Whoop. Okay. Try again. For I in range, num vertices. What am I screwing up here? Oh, range is a function. What am I doing? I've been writing too much JavaScript recently is the problem. Okay, cool. And we got it. Adding edge 0, 1, adding edge 2, 0. 1, 0 exists. True, true, false. Okay, great. All right. Graphs must have a root vertex. Okay, so this is an interesting thing about graphs, right? As opposed to trees. Trees have a root. Graphs don't really have a root. You could kind of arbitrarily, like when you're traversing a graph, you do kind of have to start somewhere, but they don't have an explicit root. What's the maximum number of edges that a graph can have? That's a good question. Well, there's no absolute limit, but it is going to be bounded by the number of vertices we have, right? So let's take a look at this explanation over here. First, let's just go over these common use cases for graphs. So common use cases for graphs, social networks, right? Vertex would be a user, connection would be an edge. Road maps, vertex might be a location, the edge would be the road. Actual networks, right? Vertex might be the computers and the edge would be the cables. Game dev might have tiles on a map, right? And then the path between the tiles could be the edges. And then an AI decision. Oh, this is interesting. So like forget LLMs for a second, but think about like, just an artificial intelligent agent trying to make a decision. The vertexes could be the various states or like consequences, and the actions could be, right, the actual, like which ones you're allowed to take between the nodes. Okay, so properties, graphs can have any number of vertices. An undirected graph can have up to n times n minus 1 divided by 2 edges. That's the formula, right? Let's just think through that for a second. So if we had 3 vertices, we know that that's like a triangle. So you'd have 3 edges at most. 3 times 3 minus 1 is 2. So 3 times 2 is 6 divided by 2. That's 3. Interesting. So which answer is it? Slightly less than half of n squared, where n is the number of vertices. Slightly less than half of n squared. Yep, that's what this is, right? N times n minus 1, so that's slightly less than half of n squared. Divide by 2, that's half. Yep. Okay, what are the maximum number of edges that graphs with 2, 3, and 4 vertices can have respectively? Okay, so if you've got a graph with 2 vertices, you can only have 1 edge. It's got to be one of these two. A graph with 3 vertices can at most have 3 edges. A graph with 4 vertices, if we use our formula from before, it's 4 times 3 is 12, divided by 2 is 6, right? There we go. All right, adjacency list. So in the first assignment, we created a graph using an adjacency matrix, right? And as I mentioned before, that kind of had a bit of duplicate data in it, right? Granted, I think this one does too. But what we're going to try to do now is use an adjacency list instead of an adjacency matrix. And it works just a little bit differently. So rather than storing like all the falses and all the trues in a list of lists that is always of fixed size, what we're going to do is use, I believe, a dictionary. Yeah, we'll use a dictionary to hold each like first vertice. And then that dictionary's key will map to a new dictionary that holds all of the edges that it connects to. Okay, so like key 0 maps to a dictionary with 1 and 4, or maybe it's a set. Maybe it's a set. We'll have to figure it out. But it maps to the values 1 and 4, right? Or maybe a list. I don't know. We'll get to it, I'm sure. Okay, but the point is we're basically using a dictionary. We're using a dictionary and the actual values rather than a matrix of true and false. Okay, let's rebuild our graph class using an agency list. Complete the constructor. It should create an empty dictionary called graph as the data member. Fair enough. Self.graph equals empty dictionary. Complete the add edge method. It takes 2 vertices as inputs, U and V, and should add an edge to the adjacency list. Okay, cool. Yeah, we are using sets. I think that's the best way to model that. Fair enough. So we just need to do self.graph at U. Well, we need to, like, the first question, of course, is there already a set here? So we need to do something like if self.graph at U, if not self.graph at U, let's do this. If not self.graph at U, self.graph at U equals an empty set. Yeah. Okay. If not self.graph at V, self.graph at V equals empty set. Okay, so now if we were missing the set for that vertice, we now have the set. It is empty, but we have it. Cool. So now we need to just add the thing to the set, right? So self.graph at U is now guaranteed to exist. So we can just do dot add V and oops, I can't spell apparently. Self.graph at V dot add U. Cool. Make sure the set exists, add the other vertex to it. Cool. How's that work? Woof. We screwed up. What do we got? If not self.graph at U. If not self.graph at U. Yeah, that's not the right way to do that. If not U in self.graph, right? If not V in self.graph. Right? There we go. Cool. Now we've got an adjacency list. How does an adjacency list represent the absence of an edge? The nodes list will not contain a reference to nodes that it doesn't share an edge with. Yeah, the nodes list. We did use a set, but it could be a list. The nodes list will contain references to other nodes that don't share an edge. No, a false node in nodes list. Nope, no Booleans anymore. An adjacency list would be best stored as a dictionary of vertices that map to a set of vertices. Yeah, and that's just because we have no ordering. Right? There's no order there's no inherent order to our graph of like this node connects to these other nodes in this order, right? It just connects to them. A connects to B and C. It doesn't connect to B first and then to C. Just connects to B and C. Okay, now that we understand our graph data structure, it's time to actually use it for an interesting algorithm. And we're going to start with breadth first search. So this is how we're actually going to traverse the graph, right? And kind of introspect it, see which vertices connect to which edges and travel across it, right? Breadth?
Nope.
Breadth?
Nope.
Breadth? Breadth first search, or BFS for short, is one of those graph traversal algorithms that you're just going to encounter time and time again as a developer. Picture this. You're at a party. Unlikely, I know. But you want to spread some juicy gossip. And you're not a monster. You want to do it efficiently. That's really what breadth first search does. It spreads out across a graph in a fairly efficient manner. And it does so by going wide instead of deep. Let me show you what I mean. Let's pretend we have this graph. Now, BFS has to start somewhere. Let's just choose to start at A. So we'll add A to our to-visit list, and then we'll actually visit it. When we visit it, we cross it off, and we add its neighbors to our to-visit list. In this case, B and E. Next, we actually visit B, cross it off, and add its neighbors, C and F, to our to-visit list. Then we go back to the next, or I should say the first uncrossed off node on our list, E, we visit it, cross it off, and add its neighbors to our to-visit list. We can ignore F because it's already on our list. Next, we visit C and add D and G. Then we visit F and add J. We visit I and add L. Then we visit D, which adds actually no new neighbors to our list. We visit G, which adds H and K. Next, we visit J, L, H, and K, none of which add new neighbors to our to-visit list, which means we've traversed the whole graph. Now, breadth first search has a time complexity of order V plus E, which is kind of weird. You might not be used to seeing big O in terms of V and E. You're probably used to N. But V just stands for vertices, right, or nodes in the graph, in this case, all the letters. And then E stands for the edges, the connections between the nodes in the graph. So in the worst case, E can get quite large if every vertice is connected to every other vertice, which effectively makes it order V squared. But again, that's only if every node is connected to every other node. So when might you use BFS? Well, sometimes it's used to find the shortest path in a graph, and it's often used for things like web crawling, where you probably want to start at something like a home page, which is probably very, very likely trafficked by lots of people. And then you want to go breadth first through the site, right? Going to every interlinking page on the site, but down from the root where things are most authoritative. In other words, you don't want to dig all the way down to some obscure blog article first. No, you want to go through all of the most highly ranking pages on the site first. So web crawlers are a very common use case for breadth first search. Kind of as a rule of thumb, breadth first search is really good if the solution you're for, or the nodes you're looking for in a graph, tend to be really close to your starting point. And that doesn't always mean it's the best choice. Depth first search, which is kind of the inverse of breadth first search, is really good when you think that the solution is far away. Maybe you're making your way through a maze. Depth first search also doesn't require as much memory as breadth first search, because it doesn't need to keep track of this giant to-visit list. It's a less stateful algorithm. But that's a story for another video.
Like that's ever gonna happen.
Okay, so breadth first search is an algorithm for traversing or searching tree or graph data structures. Starts at a root, in the case of a graph, which doesn't really have a true root, it can just be an arbitrary node, and explores all the neighbor nodes at the present depth before going on to the nodes at the next level of depth, right? Okay, just a note here that's going to be useful for our assignment, I believe. So stable sorting, non-integer sets are not stable in Python. So the order of elements is not guaranteed to be the same each time you iterate over it. So if I do 4num in some set, that's not going to work the same way every time. So in order to get it to work the same way every time, we're going to use the sorted function on our set when we iterate over it. Graphs are useful at locked in for more than just representing social connections. We'll also use it to build our geographic search feature. We have a graph of cities where each city is a vertex and each road connecting the two cities is an edge. Cool. Complete the breadth first search method on the graph class. This method traverses a graph level by level, starting from a specified vertex, and returns all the vertices in the order they were visited. Okay. This breadth first approach ensures we explore all vertices at the current distance from the start before moving further away. So imagine you have like just a map of the United States, right? And you're starting in California. With breadth first search, you're going to visit, let's just pretend that the states themselves are the vertices. Starting from California, you're going to visit Oregon and Nevada and Arizona first because they're close to California. And you're going to move out starting from the west side of the United States, and you're going to visit like all of the West Coast. And then you're going to visit all of the middle of the country, and then finally all of the East Coast. Depth first search, which we'll get to in a bit, would take a different approach. It would go deep into the graph. So it would go like, Utah, Colorado, and move all the way straight over to the East Coast, like before backtracking and then taking like a different, you can almost think of it as like a different, Y value before like moving up into Oregon and like doing another line. So depth first search moves far away from the root very quickly and then backtracks and goes down another branch. Breadth first search visits everything near it first and then moves out. Initialize the tracking structures. Create a list to track the visited vertices. So visited equals empty list. Create a list to use as a queue for vertices waiting to be explored. So we'll do something like to explore. It's another empty list. All right. Begin the search. Add the starting vertex to the queue. So our starting vertex is V. So we'll do to explore dot append V. Cool. Process the queue until empty. So while next, I guess, while next in range. No, in range. Is that what we want to do? While next into explore. Is that the right way? Let's see how it goes. While next in to explore, remove the first vertex from the queue and add it to the visited list. So we'll do to explore dot, let's see, if I did append and pop, that would be a stack. Whereas we actually want the thing at index 0, right? Which is what next is. That's what next is, right? So we want to remove it from the queue. So we need to do like a, what would it be? To explore dot, is it remove? Dot remove? No, we should do a del. We should do delete. Delete to explore at index 0. But we still have a reference to it here in next, I believe. We'll move on and see what happens. Remove the first index from the queue and add it to the visited lists. So we do visited dot append next. Get a sorted list of this vertex's neighbors. Okay, so we do something like neighbors equals sorted self.graph at v. Right? Neighbors. I don't think I know how to spell neighbors. Next to us. Can I spell neighbor? That's probably right. Neighbors. Let's do that. For each neighbor, if it hasn't been visited or queued yet, add it to the queue. So for neighbor in neighbors, if neighbor not in visited and neighbor not in to explore, then to explore dot appends neighbor. When complete, return the visited list containing vertices in the order they were discovered. Right. So return visited. So let's think about this for a second. I think I screwed this up. Let's run it. Yeah. Definitely screwed it up. So this is supposed to act like a queue. We're appending things to the end. We're deleting from the beginning, right? I think what we want to do is make this let's just be a little bit more low level here. Do something like while length of to explore is greater than 0. So this will just keep going as long as there's stuff in it. And then we want to do next equals to explore at index 0. Then we delete to explore. Then we do the rest. How's that? We're getting closer. Added edge, New York, London, added edge, New York, Cairo, New York, Tokyo. Okay, visiting New York, expecting New York, visiting Cairo, expecting Cairo, visiting London, expecting London, visiting Tokyo, expected Tokyo. Failed? I got all the right visiting and expecteds. What's going on? Oh, we missed one. New York, Cairo, London, Tokyo, Dubai. We missed Dubai. Okay, we missed one. We ended too early. Tokyo should connect to Dubai through, so New York, we should have visited London, Cairo, and Tokyo. London, Cairo, and Tokyo, we did. But the problem is we didn't recurse. Probably because we haven't written any recursion. Right? Did I miss this? Right. Yeah, we didn't do any recursion. Process the queue until up to remove the first vertex and add to the visible. Get a sorted list of the vertex neighbors. We did that. For each neighbor, if it hasn't been visited or queued yet, add it to the queue. Okay, we added it to the queue to explore.append neighbor. So we deleted. Well, okay, there is no recursion in this algorithm because we're supposed to just be pushing things into the queue. So like we should have pushed Dubai into the queue when we visited London here. But for some reason, we didn't get Dubai. If neighbor not in visited and neighbor not in to explore. So this could mean that did we already have it in visited? Let's do this. Let's just start printing stuff. Print next and neighbors and run again. Okay, so first we went to New York, which connects to Cairo, London, Tokyo. Cairo, London, Tokyo, London, Cairo, London, Tokyo. That's odd, right? We're getting the same list every time. That's not accurate. Sorted self.graph at v. Right. We're not updating we're not looking at we're not indexing into the graph in the right way. We're supposed to be looking at the neighbors of the next thing, right? We're starting at v here, but we need to be updating our neighbors to be the neighbors of the one we're currently on, right? That should fix it. And there we go. Complete graph. Take a look at this diagram. Okay, so a complete graph is a graph where every pair of vertices is connected by an edge, right? We kind of talked about this in the last chapter, where like this is the maximum number of edges that you can have between all the different kind of numbers of vertices, right? And we went over this formula, n times n minus 1 divided by 2. How many edges will a complete graph with 6 vertices have? Does one of these have 6? This one does right here. But I don't really want to count them, so I'm going to do the math instead. So 6 times 6 minus 1, so 6 times 5 is 30 divided by 2, so 15. There we go. A complete graph must have more vertices than edges. That is not true. More edges than vertices. That is almost always true, except in the case of 1 and 2. Or sorry, two vertices and 3 vertices. But it should have edges connecting every pair of vertices. Okay, we did breadth first search. Now let's do depth first search. Let's take a look at this. So remember, with breadth first search, we pick a node. Let's just pretend, and before I talk about depth first, I just want to recap breadth first. Let's say we started at E. In breadth first search, we would visit B, then we would visit F, then we would visit H, then we would visit G. Only then would we go out to the next layer and visit the neighbors of those first 4, like A and what's that one right there? D, right? And then we would visit Z, and then we would visit C. That's breadth first. In depth first, we just go as far as we can in one direction, right? So let's assume that we start at A, and then, you know, again, like the actual order in which you choose your neighbors doesn't really matter, but let's say that we go B first. Instead of going B and then Z, like we would do in breadth first, or what's that one again, D. Instead of going B and then D and then Z like we would in breadth first, we go B, E, G, H, F, D, right? We follow this long and winding branch until we run out of things, right? It's like, oh crap, we already visited A and all these other ones. Now we backtrack, whoop. Then we go down another branch, so Z, C. Okay, so that's the difference. Breadth first and depth first search are like the 2 most basic ways to traverse a graph and make sure that you get through every node. So our breadth first search algorithm was not recursive. We just used a while loop and a queue, right? Depth first search is going to be a recursive algorithm. All right. The locked-in executives want us to add a depth first search feature to geographic search. So complete the depth first search and depth first search are methods. Depth first search is a recursive helper method for depth first search. Okay, takes a start vertex as input. All right, so this is the same as last time. Traverses the graph in a depth first manner and records the vertices it visits in a list and returns it. It should create an empty list to store visited vertices. So visited, fair enough. Calls depth first search recursive with the empty list and the start vertex. So self dot depth first search R start vertex, and then returns the list of visited vertices. Depth first search takes the start vertex and the visited list. Cool. Complete the depth first search R function. It takes a list of vertices that have been visited so far. Good. And a current vertex. Good. It should visit the current vertex by adding it to the list. That's easy. Visited dot append. Oops. Visited. Get a sorted list of the neighbors. So neighbors equals sorted self dot graph at the current vertex. Okay. For each of those neighbors, if the neighboring vertex has not been visited yet. So for neighbor in neighbors, if it hasn't been visited yet, visit it. So if neighbor not in visited, visit it by recursively. Visit, this is important. We don't visit it by appending it to the list. We visit it by recursively calling depth first search with the visited list. And now the current vertex is that neighbor. So this is what's going to move us throughout the graph. This is kind of cool because, like, I would argue this is to me, this is a simpler algorithm. Like, it's easier to write depth first search, in my opinion, than breadth first search. And the main reason is there's no queue to think about, right? We don't have this 2-visit queue that we're pushing things into and pulling them out of. So for that, I mean, there is recursion here, and people are like, oh, recursion's so hard. I think this recursive algorithm is easier than the imperative algorithm that we wrote before that involved the queue, but that's just me. Oh, except for, it's so hilariously ironic that I just said that it's easy and then I failed. Okay, maximum recursion depth exceeded while calling a Python. Okay. Gotta watch out. And the irony of it actually being a recursion bug is so funny. Okay, where do we go wrong? We're recursing too much. So we probably are not handling a base case. So self depth neighbor for neighbor in neighbors. If neighbor not in visited, well, that's interesting. I mean, that should be what stops the recursion, right? Is if we've already visited this neighbor, then we won't recurse anymore. So what I should probably do here is print something like visited, right? Boop. Okay, so it's just a giant. I mean, it's not actually printing anything useful here, but you can see this is the problem. Looks like we got a list of lists. It's not what we want. I'm just being dumb. Man, chat. If I had a chat, they would have called this out immediately. We don't visited.append visited. We visited.append current vertex. There we go. Which search strategy would you prefer if the solution is likely very shallow in a tree-based graph? So let's assume that our graph is a tree. And that is, all trees are graphs, not all graphs are trees, right? Let's just assume a tree, so it'll be easier to visualize. Basic takeaway is, if you suspect that the thing you're looking for as you traverse the graph is close to the root, right? So if the root is 1 and we're looking for like 5 or 9 and we have to search through the graph to find them, breadth first search is better because we're just going to find it on that first iteration of that first level in breadth first search, right? Whereas depth first search goes down the full branch, right? So as like a general rule, and breadth first search and depth first search are not necessarily the best ways to find specific things in a graph, especially assuming you have like some additional information about like which direction you should go. But generally speaking, if you know the solution is close to the root, you should prefer BFS. And if you know it's farther away, you might want to prefer depth first search. Another thing to consider is, does the graph have wide levels? So imagine a tree-like graph with 10 vertices. So like the first node connects to 10, and then each of those connect to another 10, right? So you get this really, really wide tree. Well, because breadth first search stores every horizontal level in memory, you can actually run out of memory, right? So while you might just favor breadth first search because you're more likely to get a solution that's close to the root, one big problem is that breadth first search can become very memory intensive. But another problem with depth first search is, what if the search space is infinite? What if your graph is like unbounded, right? In that case, you could actually be recursing forever in the depth first search algorithm. So it'll just keep going down an infinite branch and never come back. Again, in which case you'd want to prefer breadth first search. So which search strategy would you prefer if the solution is likely very shallow in a tree-based graph? That would be breadth first search. Which search strategy would you prefer in a search space with infinite depth? Well, depth first search is going to be a disaster because it'll never end. Which search strategy would you use less memory in a very wide graph? Likely depth first search, because it doesn't have to store that queue in memory. And we're done.
That's going to be P versus NP.
The question of P versus NP. Probably the favorite problem of every computer scientist. Now, I hate acronyms, so let's break down what P and NP actually stand for. P stands for polynomial time. It's just a classification of algorithms that are fast enough. NP stands for non-deterministic polynomial time, which is a very confusing term, but what it really means is a lot simpler. To quote from the Introduction to the Theory of Computation, a book, it says NP is the class of algorithms that has polynomial time verifiers. Now, the whole bit about non-determinism, there is like a technical reason for why that terminology is used, but the important thing to understand is that algorithms in complexity class NP their solutions can be verified in polynomial time. And we'll get to what exactly that means in just a second. So first, just what is polynomial time? Well, let's take a look at all of our different big O classifications. We've got order 1, constant time. We've got order log n, logarithmic time, order n, linear time, order n squared, order n cubed. And then after order n squared and n cubed, we kind of hit a wall where all the algorithms go from being practical. Like, n squared and n cubed are slow, but they're not that slow. Like, you can still run these algorithms and get reasonable results. But you kind of hit a wall where order 2 to the n and order n factorial, these algorithms grow in slowness at an exponential rate. They get so slow so quickly that even for small input sizes, for small numbers of n, they become impractical. Like, you run this on modern hardware and it's just never gonna stop. Your computer will be frozen for the rest of your life. And that's where we draw the line between the polynomial time algorithms and the exponential time algorithms. So for an algorithm to be in complexity class P, it just needs to be in one of these. We just kind of lump them all together, say this is polynomial time, these algorithms are practical. All these other ones, they're too slow, they're exponential. Okay, so what's this bit about NP and verification? Let's just imagine that we have a problem where there's 10 different cities on a graph, and our job is to find the path through all 10 cities, if one exists, that is less than 100 miles in total. Well, the algorithm for finding out whether one of these paths exists or not is actually n factorial. We have to check every single combination of paths through all 10 cities. And the number of paths to check is n factorial, which is a massive number. I mean, just 10 factorial is already over 3 million. So this algorithm is not NP, it's an exponential algorithm. But occasionally you'll have one of these algorithms where it takes exponential time to solve, so it's not NP, but it is still in NP, because if we are given a solution, a path in this case, we're able to verify that the path meets the criteria in polynomial time. Hard to solve, easy to verify. For example, if someone says, hey, this path here from D to E to A to B to C, that path, that one is less than 100 miles. I'm just telling you that. Hey, can you check for me? Great, now all we have to do is follow that one exact path, sum all the distances, and if it's less than 100, great. We solved the algorithm. So this is an algorithm that when given a solution, we can verify that that solution is correct in polynomial time. And whenever we have a verifier that is quick, that runs in polynomial time, that algorithm is in NP. Okay, so we understand P, that's algorithms that can be solved quickly, and NP, algorithms that can be verified quickly. So what's this bit about versus? Why is it P versus NP? Well, that's because there's this very interesting unsolved problem in computer science, which is, hey, are every algorithm that's in NP actually also in P? In other words, if we have a polynomial time verifier for an algorithm, is there also a polynomial time solution for that algorithm? And in practical terms, no. Just like the problem I just presented to you, there's a lot of algorithms, or I should say a lot of problems, where we have polynomial time verifiers, but not polynomial time solvers. And so it seems like P and NP are not the same. However, no one's ever been able to prove that all these problems in NP don't have polynomial time solutions. And so we're all kind of left wondering, well, maybe one day we'll have a breakthrough and we'll be able to solve all of these NP problems in polynomial time. But no one really knows yet. We suspect that they're not the same because so many people have been working to solve these problems for so long, and we just haven't gotten a solution, but no one's proved it yet.
Non-deterministic polynomial time, or NP, is the set of problems whose solutions can be verified in polynomial time, but not necessarily solved in polynomial time. Now we're getting into some deeper algorithmic stuff, the content here. I wanted to save a little bit of time here because I know that this part of it gets a little bit hairy and a little bit more difficult to understand. Because what does it mean to verify in polynomial time but not necessarily solved? Hopefully we'll learn here. P is in NP Because all problems that can be solved in polynomial time can also be verified in polynomial time, all the problems in P are also in NP. P is inside of NP. And you can remember this pretty easily because if you see NP, well, that has a P. It's non-deterministic polynomial time, which includes polynomial time. It's right there in the name. Still has polynomial time in it. This talks about the oracle. A good way of thinking about problems in NP is to imagine that we have a magic oracle that gives us potential solutions to problems. Here would be our processor finding if a problem is in NP. Present the problem to the magic oracle. The magic oracle gives us a potential solution. We verify in polynomial time that the solution is correct. The point being here that you don't solve the problem, right? But you can verify that the solution is correct. That's the verify, not necessarily solved. So if you can verify, so say some magic being can automatically give you an answer. You didn't need to solve it on a computer, but you can verify it on a computer. And if we can do the verification in polynomial time, the problem is in NP. Otherwise, it isn't. A nice little video for you. And this is NP is a blank of P. And since P is NP, and you can think about this like TypeScript is a what of JavaScript. Well, it's not truly, but okay. But neither here nor there. So NP is a superset of P, just like TypeScript is a superset of JavaScript that adds types. So the idea being that everything that's valid JavaScript is also valid TypeScript, not the other way around. Everything that is polynomial is also non-deterministic polynomial, not the other way around. Problems in NP can be blank in polynomial time. Can it be yeeted, written, verified, or solved? So if it could be solved in polynomial time, that would be P, which would be in NP, but not necessarily NP. And that's going to be verified. We know if we can verify it in polynomial time, that is NP. This is the traveling salesman problem. It says a famous example of a problem in NP is the traveling salesman problem, also known as TSP. I've never really called it TSP. The version of the problem that we will solve can be stated as: given a list of cities, the distance between each pair of cities and a total distance, is there a path through all the cities that is less than the distance given? And so we have A, 20, 34, 35, 12, 30 to B. So we have a graph here. It says, for example, with the above graph, the problem could be, is there a way to travel through A, B, C, and D in less than a distance of 67? The answer would be yes, by way of A, B, D, C. So it takes 20 plus 34 is 54, plus 12 is 66, which is less than 67. For this assignment, it says our influencers need to travel to conferences to shill their sponsors' products. Very nice. Since none of them trust Google Maps, they want to put in their proposed route to Socialytics, and we will tell them if their route is short enough to be worth their time. Yeah, nobody trusts Google Maps. They're going to use Socialytics for sure. So they're going to complete the TSP function by performing a brute force search using the provided algorithm. The brute force search will unfortunately take factorial time, which is O of M with that little exclamation, because you will need to try all possible paths and keep track of the shortest. So the provided permutations function will give you all the possible permutations of a list. You can see here, similar, not the same as how we did like the supersets thing. So the pseudocode that tells us we get a cities, which is a list of numbers starting from 0 that represents a city. They each represent a city. We get paths, which is a matrix where each point represents the distance between two cities. Just for, so you know, this is a matrix, an array of arrays, a list of lists, essentially. And the dist, which is the distance we are trying to beat. So we get an example of the paths matrix, a list of lists. Each list represents the distance from that city to all the other cities. For example, paths is 0, index of 0, index of 1. Holds the distance from 0 to city 1. So you see the paths example here. And list shows the distance. List 0 shows the distance from city 0 to cities 0, 1, and 2. And then list 1 shows the distance from cities 1 to city 1 to city 0, 1, and 2. Same thing for the next one for city 2. All the routes and their distances. Shortest distance between all cities is from city 0 to city 1 to city 2, which is 27. So the algorithm here is going to be used the permutation function to get a matrix of all possible paths through the given cities, where the first path 0, 1, 2 represents moving from city 0, city 1 to city 2. We need to iterate over each possible path or each permutation, and sum the distance between each city in the path using the paths matrix to look up the distances. So if the total distance of the path is less than the given distance to beat, I would call it, we return true. And if no short paths were found, we return false. All right, easy enough. So what we're going to do here is we're going to say, call this perms, as in permutations. And we call that, we don't touch anything below that line. We're using the permutations function on cities to get that. And then we're going to say for perm and perms, the total distance, we'll set the total distance to 0 because we're summing that basically, right? And then we're going to set for I in range 1 to the length of perm of that permutation. And the reason we're starting at 1 is because we don't need to include that first city. We're just getting the city from it. So the total distance is we're going to add to the total distance. We're going to add to the total distance the paths, and we're going to get the permutation at I minus 1 and then at the index of I. Paths at the index of perm index I minus 1, and then over here, it's going to be at the index of perm I. Getting a little confusing. Okay, we know how to get the distances. That's going to be paths. Paths are already calculated here, and so we just need to get the permutation at the index that is the distance between those two cities. And then we're going to say if the total distance is less than the distance, that's going to be the distance to beat. Then we're going to return true. Otherwise, we're going to. Okay. So if the total distance is less than the distance, we're going to return true. Otherwise, because we know we can break early, because if any of the total distances is less, we can just break out early there. Otherwise, we're just going to continue going through that loop. Now that for perm and perms, check the next permutation and see if its total distance is less. Otherwise, we're going to return false if none of them are shorter than our target distance here. Alrighty. We need all the permutations there. We need to do every permutation because we need to try every possible order of the visiting cities to find if any path is short enough. And this is not great because it's factorial time. It is what it is. It's going to take a little while to run, I'll bet. All right, now we have chapter 6, lesson 4, and that's to verify the traveling salesman problem. It says TSP takes factorial time to solve, but because we're forced to try every permutation. Just said that. For example, given 4 cities, A, B, C, and D, we need to try blah, 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 every combination. So it says, although it takes factorial time to solve TSP and NP is in NP because we can verify a solution much faster. So we're going to write a verifier here. It says complete the verified TSP function by implementing the algorithm below. Notice that it runs in polynomial time. Our input's going to be paths, which is a matrix where each point represents the distance between 2 cities. For example, paths of city A. City A is the row and city B is the column. That holds the distance from city A to city B. And then we have the distance is the distance we're trying to find a path shorter than, the distance to beat. And then the actual path, the path we're trying to verify. So our algorithm here is just going to be to loop over each city in the actual path, get a sum of the distance between each city in the actual path. And if the sum is less than the distance, we return true. Otherwise, we return false. Much, much simpler. We're going to say total equals 0. Because we're just we're summing, and then we're going to say for I in range of the length of the actual path, the answer that we're verifying, and then we're going to say if I does not equal 0, then the total is going to be, we're going to add that to the total. Where we said the paths of the first, same thing as kind of the before. The paths of the first city is going to be, the row is going to be the first city, and the column is going to be the second city. And so paths of, let's make one, it's called A equals actual path index of I minus 1, and B equals actual path I. Yeah, okay. And so now we can get A and B. We could say if total is less than dist, then we return true. Otherwise, we return false. But really, what we can just do, cut that shorter, and just return if whether or not total is less than dist. Alrighty, so we just loop through the path once. We add up the distances between consecutive cities using that paths matrix. And then we check if the total distance beats the target. And we did it. TSP review. Consider the TSP algorithms that we wrote, right? The solving and verifying. The big O of TSP and is blank, and verified TSP is blank. We have O of n and O factorial, or O n factorial, or O of n, or we have O2 to the power of n exponential and O of 1 constant, or O of 1 constant, or O n squared. If we think about so it says big O of TSP is blank. Let's find out what that one is. So if you remember, doing all the permutations and getting all the permutations and then iterating over every permutation is factorial time. Terrible. So we know that the first one, big O of TSP, is factorial, the worst it gets. And then verify, we can look and see total equals 0. All we're doing is one for loop. And then if I does not equal 0, then the total plus is loops through the path once, add up the distances between consecutive cities using that paths matrix. So that's just going to be O of n, single loop. We need to go over every single item in the path. So O, it's factorial time and linear time. The TSP function is in class Underwater Basket Weaving 101, P and NP, P or just NP. Since we know that solving it is the TSP function, not the verified TSP function, but the solving TSP, that's factorial. And then verifying it is linear. Sorry. And verifying it's in linear time. So that means that if we can't solve it in polynomial time, but we can verify it in polynomial time, then it is in NP. But it's not in P because we can't solve it. And it's not P and NP because we can't solve it in polynomial time, which linear time is part of polynomial time. So NP is going to be our answer. Now we are on to NP complete. This says that some, but not all problems in NP are also NP complete. And I encourage you to check out NP complete. Check out all the links. These are a lot of great things. A lot of great resources to read to dive deeper into all of this. This is a problem in NP is also NP complete if every other problem in NP can be reduced to it in polynomial time. Let me see what. Sorry there. So that's reducing in complexity. So what does reduced mean? We won't dive deep into the subject of reductions in this course, but we'll cover the basic idea. Any problem, let's call it problem A, can be reduced to a different problem which is already solved, problem B. If there is an algorithm called the reducer that turns an algorithm that solved problem B into an algorithm that will solve problem A. Alrighty. So algorithm to solve B, we have a reducer, and we get an algorithm to solve A. However, the reducer itself needs to be fast. Problem A is reducible to problem B if the reducer can run in polynomial time. It's a little more complex here, especially since we're not really going over what reducer is. Basically, you can derive the algorithm that you use to solve one problem into another algorithm that can be solved another problem. If what you're using to derive that new algorithm can be solved in polynomial time, then that is going to be NP complete. So who cares? Well, this means that if we can find an algorithm that solves any of the NP complete problems in polynomial time, then all problems in NP can also be solved in polynomial time. Super duper smart computer scientists have proven it. Trust me. Or read more about it. Yeah, we can just trust Lane on this one. There's people who care, for sure. So for a problem to be NP complete, all problems in NP must be able to reduce to it. And is that going to be in the quantum realm, in space-time, in polynomial time, or in exponential time? And we know this is all about doing things in polynomial time. So it says that if we can find an algorithm that solves any of the NP complete problems in polynomial time, then all problems in NP can also be solved in polynomial time. As we'll see, I think in a little bit, that is not necessarily the case. We are moving on. A solver for blank problems can be quickly reduced to solve all problems in blank. So it just said it. It says if we can get a solver for NP complete problems, then we can solve all problems in NP. Verifying solutions. Let's circle back to this idea of slow to solve, fast to verify. Even when we aren't specifically talking about P and NP, the concept of slow to solve, fast to verify is very important in real-world software. As a trivial example, imagine the password on an email account. When a user inputs a password like that, it's easy to verify if the password matches the one we have saved on file. It's literally as easy as should grant access equals user input. Does the user input equal the saved password? The useful bit is that it takes much longer to guess the correct password. So the password example demonstrates the guess verify concept well, but when it comes to storing passwords in plain text, this example is very insecure. Yeah, don't do that. Okay, so this assignment says that the influencers who use Socialytics are worried about account security. We've assured them that their passwords are long and strong enough, but they want data. Complete the getNumGuesses function. It takes a password length as input and returns the number of guesses required to ensure that a password of that length or shorter is guessed. Assume a brute force guessing strategy on the part of the attacker. A guesser needs to guess all possible passwords up to and including the given length. For example, blah, 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 blah. You know, just like if you were naively guessing a password, and you're like, I'll just start with the letter A. I go A, you know, and then A, B, you know, and then after you get through the alphabet, you go AA, and you keep going all the way. Assume that only the 26 lowercase English letters can be used in passwords. Here's some example outputs. So input 1 would take 26, because there's 26 letters in the lowercase English alphabet, and that would, if you have one input of 1, if the length of the password was 1, you would just have to guess 26 times. However, this is going to be a factorial time solution, and so if we have multiple, if the input, as the input gets longer, it takes significantly more guesses that you'll need to get it right. And with only 3 letters, it would take 18,278 different combinations. So this is a brute force guessing strategy. I'll let you look that up on your own, or actually I believe there's a link to it over there. And so all we're going to do here is we have we can say letters. No, we're not going to do that. So we say total equals 0, and then we're going to do we're going to loop over it, and we say for I in range of length, we say the total is going to be, we're going to add to the total. That's 26. How do we? Exponential, and this would be I plus 1. So we just return the total. 26 letters in the alphabet, and it's going to get exponentially larger. I will get larger based on the length. Then it's going to be 26, but it's 26 to the power of I plus 1. Alrighty. Chapter 6, Lesson 10. Does P equal NP? The P versus NP problem is a major unsolved problem in computer science. Again, nice little link there for you. Further reading. It asks whether every problem whose solution can be quickly verified is in NP can also be solved quickly is in P. The question is, are all NP problems really just P problems that we maybe don't know how to solve yet? And the answer is, we don't know, but probably not. So why do we care? All problems in NP, hard ones like the traveling salesman problem, solving the traveling salesman problem, have been proven to also be solvable in polynomial time if we can find a solution to just one NP complete problem. Again, if you remember, if we find a solution to one NP complete problem, then we can make it. Then the reducer will be in polynomial time, and we can therefore write polynomial time solutions to any NP problem. So if a single NP complete problem can be solved quickly, that means that all problems in NP can be solved in polynomial time. That would be a huge deal because it would break digital security systems that rely on the difficulty of certain NP problems. So this asks, what happens if we find a polynomial time solution to an NP complete problem? Well, we learned nothing. Some of us, maybe. P equals NP, or P does not equal NP. And that would mean if we find a single solution to a NP complete problem, that would mean that P equals NP. It most likely does not, but we don't really know. And again, it's a major unsolved problem. You might see people saying, once we get AGI or something that, it will know because it can solve P equals NP, yada, yada. Next question. Chapter 6, Lesson 11. Does P equal NP? Is it yes? We don't know, but probably not. No. Or it's impossible to know. Ooh. I would say maybe impossible to know, but no. The answer is we don't know, but probably not. It's impossible for me to know. All right, moving on. The negative case. We do not know for sure if P equals NP because we can't find any polynomial time solutions to NP-complete problems. Additionally, we have been unable to prove whether P does not equal NP. We suspect P does not equal NP because it has been so difficult to prove that P equals NP. That said, it's actually more complicated to prove the negative case. That's kind of the case in most things in life, right? It's easy to prove that. It's easy when you have evidence of something existing than it is to prove the evidence of something not existing, but that's neither here nor there. To prove the positive case that P equals NP, we simply need to solve an NP-complete problem, like the traveling salesman problem, in polynomial time. In order to prove the negative case that P does not equal NP, we would need to exhaustively prove that there is no possible way to solve TSP in polynomial time. That's a lot trickier. You're working with unknowns there, and you want to try to verify every unknown. P does not equal NP. Is it we don't know? Or is it true or false? And the answer is we don't know. So it's simpler to prove P blank NP than P blank NP. And that's going to be, it's simpler to prove P equals NP than P does not equal NP, as we just talked about. Chapter 6, Lesson 14, NP hard. All NP complete problems are NP hard, but not all NP hard problems are NP complete. The determining factor between NP complete and NP hard is that not all NP hard problems are in NP. So we have a little graph here. P not equal NP. P equals NP. We have our P and we have our NP. And then we have our NP complete. And then we have our NP hard. All NP complete problems are NP hard, but not all NP hard problems are NP complete. The determining factor between NP complete and NP hard is that not all NP hard problems are in NP. So some of these NP hard problems might not even be in NP here. Which means they're not in P either, because P is in NP, and the NP hard problem might overlap with NP, but not everything. So you can have an NP hard problem that is not NP. So the definition here says that a problem is NP hard if every problem in NP can be reduced into it in polynomial time. This is compare this to the slightly different definition of NP complete, which is a problem is NP complete if it is in NP and every other problem in NP can be reduced to it in polynomial time. And a problem is NP hard if every problem in NP can be reduced into it in polynomial time. And NP complete states that a problem is NP complete if it is in NP and every other problem in NP can be reduced to it in polynomial time. All NP complete problems are NP hard. So it could be NP complete and NP hard, but it's only NP complete if it is in NP. Otherwise, the requirements are the same. The difference is that NP complete problems must be in NP. Or in other words, they must be verifiable in polynomial time, whereas NP hard has no such restriction. So NP hard problems must be blank in polynomial time. They have reduction from all NP problems, be web scalable, be verifiable, or be solvable. So if it was be verifiable, that would mean that it would be just an NP problem. And it doesn't have that restriction, and doesn't need to be solvable because that would just make it P. Web scalable, come on. And so the answer is it means to have reduction from all NP problems. So this one says all blank problems are also blank. Is it NP hard and NP complete? Are all NP hard problems also NP complete? No. NP hard, NP? No. NP hard? No. So the answer here is so all NP complete problems are also NP hard. But it says that all NP complete problems are NP hard, but not all NP hard problems are NP complete. All NP complete problems are also NP hard. Alrighty, chapter 6, lesson 16, prime factorization. This will be fun. So we need to solve a commonly misunderstood problem in computer science, which is finding the prime factors of a number. Almost all modern cryptography, including your browser's HTTPS encryption, is based on the fact that prime factorization is slow. For now, let's focus on the speed of factorization and how it relates to P and NP. Finding a number's prime factors is an NP algorithm. We can't solve it in polynomial time, but we can verify it. So when given two primes and their product, all we need to do is some simple multiplication to verify correctness, which is in polynomial time. And then given a number, finding its prime factors is a much more difficult problem, and exponential time is the best we know of. The trouble is that no one has formally proven that there is not a polynomial time algorithm for finding prime factors. So technically, we're unsure if the problem is in P or if it's NP complete. Either way, let's build it. So we're importing math here. The algorithm says, given a large number, returning a list of all prime factors. So the prime factors of 8 are 2, 2, and 2. Prime factors of 10 are 2 and 5. Prime factors of 24 are 2, 2, 2, and 3. This is we divide n by 2 as many times as we can evenly, okay, with no remainder. And then for each division, we append a 2 to the list of prime factors. By now, n must be odd. Start a loop that iterates over all odd numbers from 3 to the square root of n inclusive. We can use math.square root. For each number I, if n can be divided evenly by I, then divide n by I and append I to the list. We repeat this in a nested loop until I can't divide evenly into m. Then we move on to the next I. If n is still greater than 2 after the loop, it must still be prime. So we just append it to the list. We're going to return the list of primes ordered from least to greatest. Okay. Our assignment is to complete the prime factors function according to the given algorithm. Notice how the algorithm gets much slower as the size of the input in bits grows. The returned list should only contain ints, no floats. So to solve this one, we're going to set up our factors, which is going to be what we're going to output there. It says the first thing we need to do is we need to divide n by 2 as many times as we can evenly with no remainder. And so we're going to say while n modulo 2 equals 0, evenly. Factor, we're going to append a 2. It says append a 2 to the list of prime factors. And then n is going to equal n inner floor division 2. And then we're going to loop from 3 to the square root of n. If n can be divided evenly by I, then divide n by I and append I to the list. So we need a loop while I is less than or equal to math.square root of n. Then if it can be divided evenly by I, which we can check by doing the modulo of I, if that equals 0, so there's no remainder, then we're going to append I, and we're going to then divide n by I like that. We can keep trying that again, so we're not going to increment. So we're just going to go continue. And then we're going to, until I can't divide evenly into it. So, and the I is going to plus equal 2. So then if n is still greater than 2 after that loop, it must be prime. So we append it to the list. We say if n is greater than 2, then factors that append n, right? And then we're just going to return factors. I think that's it. Oh, wait, what'd I do? Oh, I got to make I. So n is going to 2. So I is going to be, this says iterates over all odd numbers from 3 to the square root. So I equals 3. All right, yeah, I think that's it. So I equals 3, and that's it. Cool. We only increment it here when it's no longer a factor, and that moves us to the next I. Otherwise, we just keep trying on n, and we change n to see if it can be divided by I evenly with no remainder. I would recommend looking through that algorithm more. It's not one that I would say is that I've had much experience with. So moving on. Well, it looks like they did it a little bit different than me. That's okay. I don't know why I need to make int n. I don't know. That edge case wasn't there for me, but that's okay. Chapter 6, lesson 17. Which is this problem definitely a part of? We did that in exponential time, but we couldn't do it in polynomial time. And so that makes it like it could be other things, but we know for a fact that it's an MP because we can verify it. So if you're given a massive number and you gave me its prime factors, we could verify it just by multiplying them. But as we just saw, finding those factors in the first place is a lot more difficult. That makes it NP. And really, if this were P, not MP, then a lot of our encryption systems and the internet would be freaking out. On to the next. This is chapter 6, lesson 18. Given two large primes and a product, can we verify that the two primes multiply into the product in polynomial time? Yes, that is. We know that. Like I said, very simple. We can verify the two primes multiply in polynomial time. We just multiply them and then check if the result is the product. That's all we have to do. So we can say yes. Next question. Chapter 6, lesson 19. Oh, look at that. We're on to the last one. All right. This has been a long course, and we're right here at the edge, the cusp. Prime factoring review, big O analysis. Chapter 6, lesson 19. Prime factoring review, Big O analysis. Let us denote n as the integer input and s as the size of n in bits, so that s equals log 2 of n. Notice that our first loop iterates log of n times, and the second loop iterates square root of n times. The big O with respect to n is O square root of n. That's fast. That's polynomial complexity, which would lead us to believe the problem is in P. But wait, the problem is by definition, when computer scientists talk about this problem, they are talking about the length of n in bits, what we will call s. For example, the integer 255 only takes 8 bits. 241 is 111100001 in binary, and since s equals log base 2 of n, a complexity of square root of O square root of n is equivalent to O square root of 2 to the power of s. The complexity in respect to the number of bits is exponential. We have our prime factors code again here. What is our algorithm's big O complexity when n is the input integer and s is the size of the input in bits, respectively? When n is the input integer and s is the size of input in bits. So the first loop iterates up to the square root of n times, and that gives us O of square root of n. And if we have s, the size in bits, where n equals 2 to the power of s, that would mean that would be O of square root 2 to the power of s. So that would mean that we would get O square root of n. And so if n is the input integer, then it would be O square root of n, as you saw here. And if s is the size of input in bits, that would mean that it would be O of square root 2 to the power of s, which I don't know what that time's called. That's okay. I think this is our last one. Let's see if we got it right. The anticipation is killing me. We did it. All right, that will be it. There is a optional challenge. We're not going to do that. I encourage you to do it on your own. As with all of these optional ones, just do it. Yeah, they're hard. Yeah, algorithms is difficult. Algorithms aren't about understanding every single algorithm. Most of it is about understanding how to solve problems, understanding some similarities when you see these algorithms, and sometimes you see a problem that your mind goes to a kind of algorithm immediately, like, oh, I know a way to solve this. For instance, with Fibonacci sequence, you know that you're adding the 2 before it to get the next number. So dynamic programming might be a solution there. There's a lot of concepts that we didn't go over today, but there's a lot of further reading here. But I think that I hope that I gave you some insight into how to start looking at algorithms and how to solve. If you got stuck on any of these, I hope that I helped you get through it. That's going to be all from me. Thank you so much for joining me.